Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So my dear students, just let me know in the chats quickly if all of you can hear me, if I'm perfectly audible, visible to every one of you. Let me know quickly in the chats. Good evening people, good evening and welcome back. Good evening and welcome back. Good evening and welcome back. How are you all? Good evening people, good evening. Wassim sir şu smart gumut. Wassim sir was godnik pretty smart. So people, am I perfectly audible, visible? Am I perfectly audible, visible to everyone? Yeah? Give me some fire emojis in the chats if I'm perfectly audible, visible, if all of you can hear me perfectly. Give me some fire emojis in the chats, everyone. So people, as you all already know, today we are going to complete your class 11th Inorganic Chemistry. That too in the detailed manner. Okay? Starting from the basics, starting from the scratch. I'll consider as if you guys have never studied inorganic chemistry. In that manner, I'll be starting this particular session. Okay? So we'll be exactly starting from the basics, from the scratch. Slowly, we'll scale up the things. And in this session only, in the today's session only, we are going to complete your entire class 11th inorganic chemistry. Number one. Number two, tomorrow we have got one more session scheduled on this channel. That is your top 300 questions of class 11th inorganic chemistry. That's going to happen tomorrow exactly at 8 p.m. Right? Well, the duration of today's session is going to be almost like 7 hours. Duration of the today's session is going to be almost like 7 hours. Yeah? Okay? And duration of the tomorrow's session will be approximately 3 hours. So I'm giving almost like 10 hours to your complete class 11th inorganic chemistry in the detailed manner. Right? All the topics, all the things which have been asked till date from inorganic chemistry or which can be asked from inorganic chemistry of class 11th, I'll be discussing every single thing in detailed format, right? So before starting this particular session, sir, what about atomic structure? Atomic structure comes in physical chemistry, right? Well, I have not taken a marathon of class 11th physical chemistry yet, okay? Class 11th physical chemistry I'll be taking in next week. Okay, so today we are going to do class 11th inorganic, not physical. All right, so quickly, let me know in the chats which part of the country you guys are watching me from. I just want to know. I just want to know, first of all, which part of the country you guys are watching me from. I just want to know. There is, I think, electricity cut. Wait a second. Wait a second. Okay, now it's fine. All right, so tell me, guys, which part of the country you guys are watching me from? Quickly. Well, I can see Jharkhand, Tamil Nadu, Kashmir, Andhra, Uttar Pradesh, Karnataka, Tamil Nadu, AP, Kashmir. Okay. Telangana. Tamil Nadu, AP, Bangalore, Manipur, Kulgam, nice. Kerala, West Bengal, MP, Telangana, Maharashtra. All right. All right. Haryana, Shillong, nice. Kerala, WB. WB is Wassim, but yeah, West Bengal. Okay. Got it, guys. Got it. Bus. Done. Got it. Got it. So should we start the session then? Already? All super duper excited? Well, before starting the session, let me tell you one important thing. As you already know, your NEET 2026 forms, application form, that's already out, right? Do fill the form as soon as possible. Okay? Your application form window is open from today till March 8th. So you have got one complete month for that. Guys. This lecture will cover entire class 11th Inorganic Chemistry. Don't worry about that. Sir, use Urdu language, please. I cannot use Urdu language here because the name of the channel is Unacademy NEET English channel. Okay? I hope I'm clear to you. All right, people. So should we start then? I think we'll start with the chapter, which is easy, I believe, for majority of the students. And the name of the chapter is Periodic Classification. Periodic classification is going to be the first chapter which we are going to do in the today's session. Okay? At the same time, the handwritten notes of this particular session, the DPP of this particular session, everything I shall be sharing on my Telegram. I hope you're already the part of my Telegram channel. If not, be the part of the Telegram channel as soon as possible. The name of the Telegram channel is Wassim Chemistry Official. Wassim Chemistry Official is the name of the Telegram channel on which I keep on sharing the handwritten PDFs, the DPPs, the questions, every single thing, right? This is the Telegram channel name. If you are not the part of the Telegram channel yet, be the part of the Telegram channel as soon as possible, right? Because I keep on sharing every single thing, be it the session PDFs, be it the information about the lectures, about all the notification and stuff in this particular Telegram channel, right? So my dear students, as I told you, we are going to start with your chapter periodic table, right? Periodic classification of elements, okay? And what all things are in this particular chapter? So there are mainly 4 things which are in the chapter, which we shall be discussing in very detail. The first thing is going to be how to identify period number, group number, as well as the block of an element. This is the first thing from which questions are frequently asked. Number 1. This is going to be our first topic of the today's session. Number 1. Number 2, we'll be talking about the second thing, that's going to be atomic radius and its types and the factors that decide the atomic radius. This is going to be our topic number 2. Then we'll be talking about the ionization energy and the factors which affect the ionization energy, the variations, exceptions, every single thing will be discussed here. After that, we shall be discussing about your electron affinity, or you can call it as the electron gain enthalpy as well. This is going to be our next topic. And after your electron gain enthalpy, electron affinity, we shall be discussing about electronegativity as well. Well, these are the topics which actually come under the chapter periodic classification. Okay. These are the topics which actually come under the chapter periodic classification. Perfect. So without wasting a lot of time, let's get going. Let's get started. And my dear students, let's have a look on the present form of the periodic table. Let's see what all things we have to remember about the present form of periodic table. What are the important crux which can be asked from the present form of the periodic table. So first of all, my dear students, first of all, there are a few points which I would want you guys to remember about the modern form of the periodic table. Your modern form of the periodic table, which you keep on seeing everywhere, right? That is based on what? That's based on the Bohr-Bury's principle, number one, right? Bohr-Bury's electronic configuration and atomic number. Your current modern form of the periodic table, it's based on your Bohr-Bury's electronic configuration and the atomic number, which you shall understand in some time, right? Now, there are some points, my dear students, which you need to remember. I believe all of you would already be knowing in your current modern form of periodic table, which was proposed by Rang and Werner, there are 7 periods and 18 groups. So basically, in the current modern form of the periodic table, there are basically 7 horizontal rows, and horizontal row will be called as period. So technically, I would say there are 7 periods and there are 18 vertical columns. There are 18 vertical columns. There are 18 vertical columns in your current periodic table. And each vertical column is called as group. Horizontal row is called as period. Vertical column is called as group. In your modern periodic table, there are some 7 periods, right? There are 7 horizontal rows and 18 vertical columns. You can say 18 groups as well. Okay. And at the same time, your modern periodic table is divided into 4 blocks. Your modern periodic table, it is divided into 4 blocks. Well, the 4 blocks are, number 1, S block elements, P block elements, D block elements, and F block elements. What are your S block elements? S block elements are the ones in which the last electron enters into S orbital. S block elements are the ones in which the last electron enters into the S orbital. Your P block elements are the ones in which the last electron enters into the P orbital. Similarly, D block elements are the ones in which the last electron enters into the D orbital, and F block elements are the ones in which the last electron enters into the F orbital. Perfect. So basically, in your modern periodic table, which is based on Bohr-Bury's rule and the atomic number, which was proposed by Rang and Werner, there are 7 horizontal rows called as periods, and there are 18 vertical columns called as groups. And we divide the modern periodic table into 4 blocks: S block, P block, D block, and F block. In case of your S block elements, the last electron is going to enter into the S subshell, or you can say S orbital. P block elements, the last electron, the incoming electron, that would have entered into the P subshell or P orbital. Similarly, D block elements, the last electron enters into D orbital, and F block elements, the last electron enters into F orbital. Now, one by one, let's talk about these blocks and let's try to understand few important things which we have to remember about these blocks. My dear students, this is your current modern form of the periodic table, right? As you can see, 1, 2, 3, 4, 5, there are 18 groups. And as you can see, 1, 2, 3, 4, 5, 6, 7, there are 7 periods. There are 18 groups in total and there are 7 periods. And as I told you, this periodic table is classified into how many blocks? 4 blocks. First block is your S block. My dear students, this is your group 1 and this is your group 2. If you look at group 1 and group 2, this group 1 and group 2, this is combinedly called as, this group 1 and group 2, you call them as the S block elements. Group 1 elements and group 2 elements collectively are called as S block elements. Why they are called as S block elements? Because their last electron will be in S orbital, S subshell, right? Similarly, my dear students, from group number 13 to group number 18, from group number 13 to 18, this is your group number 13, and this is your group number 18, my dear students. From 13 to 18, what do we have? We have got p block elements. These are your p block elements. And similarly, my dear students, from group number 3 to group number 12, this particular group, right? This particular one, from group number 13 to group number 12, you call these as the D block elements. You call them as the D block elements from group number 13 till group number 12, right? And these particular elements which are mentioned separately over here, you call them as the F block elements. You call them as the F block elements. This is the broader classification of our periodic table. So we have classified periodic table into 4 blocks, right? One is going to be your S block, one is going to be your P block, one is going to be your D block, and one is going to be your F block, right? And my dear students, at the same time, when it comes to your F block elements, in F block elements, this particular series, as you can see, this particular series is called as Lanthanoid series, and this particular one is called as Actinoid series, right? Why this is called as Lanthanoid series? Because this particular series starts after lanthanum. This particular series starts after lanthanum. So first of all, this lanthanum, this particular lanthanum, it is not the F block element. But after this lanthanum, whatever elements do you see? They are your F block elements. Perfect. So first of all, this particular series is what we call as lanthanoids, and the series below it is called as actinoid series. But this lanthanum, it does not belong to your what? It does not belong to your F block elements. After this lanthanum, your F block elements are going to start. Okay? Right? And my dear students, if you talk about these lanthanoids, after lanthanum, which has got the atomic number of 57, so from atomic number 58 till hafnium, it's going to be your lanthanoid series, which contains exactly how many elements? It contains 14 elements. It contains 14 elements. These are some general things which you need to know about the periodic table, right? S block, P block, D block, and F block. Now, one by one, we are going to talk about these blocks in detail. So first of all, if I talk about, my dear students, your S block elements, okay? As I told you, group 1 and group 2, they are called as S block elements. Why is that? Because when it comes to your S block elements, the outermost electron, the last electron that enters into what? That enters into S orbital. Okay? As you can see this, lithium, sodium, potassium, rubidium, cesium, francium, these are your group first elements, right? And beryllium, magnesium, calcium, strontium, barium, radium, they are called as your groups 2 elements. Perfect. Now, for example, if you ask me, what is the outermost configuration of lithium? I'll say outermost configuration of lithium is 2s1, right? Outermost configuration of sodium, it is 3s1. Potassium, 4s1. Just increase the shell number here. Outermost configuration of rubidium, 5s1. This is 6s1. This is 7s1. So now, if I ask you, what would be the general electronic configuration of group first elements? General electronic configuration of group first elements will be ns1, right? ns1, because there's 2s1, 3s1, 4s1, 5s1, 6s1, 7s1. So general electronic configuration of your group first elements is ns1. If you look at your group second elements, the outermost configuration of beryllium is 2s2. Outermost configuration of magnesium is 3s2. This would be 4s2. This would be 5s2. This would be 6s2. This would be 7s2. So the general outermost configuration of group second elements would be ns2, my dear students. And since you know your group 1 and group 2, they are combinedly called as S block elements. So I would say the general outermost configuration of S block elements, will be ns1 is for group 1 and ns2 is for group 2. So it's from ns1 to 2. This is the general outermost electronic configuration of your S block elements. I believe this is clear to everyone. Yes? Now similarly, my dear students, there is something called as P block elements as well. As I told you already, your P block elements starting from group 13 till group 18. Group 13 to group 18 elements are called as your P block elements, right? Group 13 to group 18 elements are called as P block elements. And let me tell you, this is the only block in the periodic table which contains metals, non-metals, as well as metalloids. This is the only block in the periodic table which contains your metals, non-metals, as well as your metalloids. My dear students, if you look at these elements which I've already highlighted, they are your metalloids. Right? And above these metalloids, we have got non-metals. And below these metalloids, we have got metals. Let me tell you, this is the only block in the periodic table which contains metals, non-metals, as well as your metalloids. Now, people, if you look carefully, this boron, this is a group 13 element, this is group 14, this is group 15, group 16, group 17, and group 18, right? Now, if you look at their electronic configurations, for example, if you ask me, what is the outermost configuration of your boron? What is the outermost configuration of your boron? I'll say the outermost configuration of boron. Boron has got atomic number 5. So 1s2, 2s2, 2p1. Correct? Its outermost configuration is 2s2, 2p1. Its outermost configuration of carbon. This is 2s2, 2p2. Right? This will be 2s2, 2p3. This will be 2s2, 2p4. You just have to add one electron. This is 2s2, 2p5. This will be 2s2, 2p6. Correct? 2s2, 2p6. Similarly, now, if you ask me, what is the outermost configuration of aluminium? Since it is 2s2, 2p1, so it is supposed to be 3s2, 3p1. This is supposed to be 4s2, 4p1. Same replica, 5s2, 5p1. Correct? If you look at the outermost configuration of silicon, carbon has 2s2, 2p2. So this will be 3s2, 3p2. Right? Similarly, 4s2, 4p2, 5s2, 5p2. Similarly, if this is 2s2, 2p3, this is going to be 3s2, 3p3. Right? For example, this is 2s2, 2p5. This is going to be 3s2, 3p5. For example, this is 2s2, 2p6. This is going to be 3s2, 3p6. Understood? Understood, people? Now, my dear students, remember a few things. What are those things? See, first of all, boron has got the configuration of 2s2, 2p1. Carbon, 2s2, 2p2. 2s2, 2p3. 2s2, 2p4. 2s2, 2p5. 2s2, 2p6. So, if I talk about the general outermost configuration of these p block elements, it is simply going to be ns2, np is from 1 to 6. ns2, np from 1 to 6. This is the general outermost configuration of your p block elements. As simple as that. Okay. Now, my dear students, let's talk about your d block elements. Let's talk about your d block elements. First of all, your d block elements. Right? If you look at all these elements, they are your d block elements. Now, what are the important conclusions? What are the important crux which we need to remember about the d block elements? First of all, why do we call them as the d block elements? Because their outermost electron, the last electron, would have entered into d subshell. Because that last electron would have entered into d subshell. For example, talk about scandium. The outermost configuration of scandium is 3d1, 4s2. Outermost configuration of titanium, it will be 3d2, 4s2. Right? This will be 3d3, 4s2. Chromium, 3d5, 4s1. Manganese. Chromium is exceptional electronic configuration. I hope you know it already, right? This will be manganese 3d5, 4s2. 3d6, 4s2. 3d7, 4s2. 3d8, 4s2. This is again exceptional one. 3d10, 4s1. And this is 3d10, 4s2. Perfect. I believe this is clear. Now, this particular first series, the first series of elements do you see here, right? We call it as the 3D series. Why we call it as 3D series? Because as you can see, the D subshell is slowly getting filled, right? 3D1, 3D2, 3D3, 3D5, 3D5, 3D6, 3D7, 3D8, 3D9, 3D10, something like that, right? So your D subshell is getting filled, so we call it as 3D. Perfect. Then the next one comes 4D, because in this particular one, 4D subshell will be getting filled. Then again comes the next one. In this particular one, your 5D subshell would be getting filled. That's why we call the first series as 3D series, second is 4D, and third is 5D, right? My dear students, if you talk about these D block elements, these D block elements, the first and the most important point about them, they show variable oxidation states. They do not show only single oxidation state. They show variable oxidation state. For example, if you talk about manganese, I believe you would have seen manganese in +7 oxidation state, +5 oxidation state, +6 oxidation state. So they show a range of oxidation states basically. They show variety of oxidation states basically. Yeah? They show variety of oxidation states basically. And at the same time, something important. 3 electronic configurations you have to remember in D block. exceptional ones. See, look at this particular group: nickel, palladium, platinum. Nickel, palladium, platinum. Well, you know, the outermost configuration of nickel is 3d8 4s2, correct? Outermost configuration of nickel is 3d8 4s2. That means the outermost configuration of palladium should be 4d8 5s2, correct? 4d8 5s2. Similarly, the outermost configuration of platinum should be what? It should be 5d8 6s2. But that's not the case here. Remember, the actual outermost electronic configuration of palladium is this one, 4d10 5s0. It is supposed to be 4d8 5s2, right? But it's not so. Same goes with platinum. The expected configuration of platinum should be 5d8 6s2, but in reality, its configuration is 5d9 6s1. So these are the two things which you need to remember directly, right? Okay, these two things which you have to remember when it comes to electronic configuration. Rest, you can write electronic configuration of any element in D block, but these two elements you have to remember for sure. Perfect. Now, my dear students, there is one more thing. There is one more important thing. What is that? We call D block elements. We call the D block elements as transition elements. Do you know what are transition elements, first of all? We call them as the transition elements. Why is that? What are the transition elements? Transition elements are the ones which have incompletely filled. Which have incompletely filled d orbitals. Which have incompletely filled d orbitals, either in their ground state, or in their common oxidation state. Either in their ground state or in their common oxidation state. What does that mean? Let's try to understand. For example, talk about scandium. Its outermost configuration is 3d1 4s2. So d orbital is incompletely filled. Titanium 3d2 d orbital incompletely filled, right? Vanadium d orbital 3d3 d orbital is incompletely filled, right? So basically, whenever you see any d block element whose d orbitals will be incompletely filled, either in their ground state or in the most common oxidation state, you call those d block elements as the transition elements. Now, this zinc, cadmium and mercury, these are not the transition elements. They are the d block elements, but they are not the transition elements. Why is that? Let's talk about that as well. Do I have some space here? Okay, let me write it over here. For example, if you talk about zinc, when zinc is in ground state, what is its outermost configuration? Its outermost configuration is 3d10 4s2. Its outermost configuration is 3d10 4s2. Is D having any unpaired electron? No, D does not have any unpaired electron. Since D subshell has got 5 d orbitals, right? Each orbital accommodates maximum 2. So 5 2s are 10. So it has got completely filled d orbitals. But my dear students, when you talk about zinc dipositive, this is the most common oxidation state of zinc. What will be its configuration now? Take 2 electrons out. It becomes 3d10 4s0. Again, if you see, do we have any unpaired d electron here? There is no unpaired d orbital here. So in case of zinc, neither in ground state nor in the most common oxidation state, it has the unpaired d orbitals, right? First of all, what are transition elements? These are the elements which have got incompletely filled d orbitals either in ground state or common oxidation state. Now, you look at zinc in its ground state, it does not have incompletely filled d orbitals. In its most common oxidation state, again, it does not have incompletely filled d orbitals. So it's not a transition element. So remember, this zinc, cadmium and mercury, they are the d block elements, but they are not the transition elements. If I'm clear, let me know once in the chats quickly. Yes? And my dear students, again comes to your F block elements. These are your F block elements. Perfect. This is your lanthanoid series. This is your actinide series. After lanthanum, lanthanoid series starts. After actinium, your actinoid series starts. If you look at your lanthanoids, Lanthanoids are basically from atomic number 58 till atomic number 71. So your lanthanoids from atomic number 58 to atomic number 71. These are what you call as lanthanoids. Similarly, if you talk about your actinoids from atomic number 90 to atomic number 103, these are your actinoids. These are your actinoids. Okay, these are your actinoids. I believe this again clear to everyone. And let me tell you, all these F block elements, they belong to which group? They belong to group 3. This again one important point which you need to know. They belong to group 3, or you can call it as 3b as well. Okay. So my dear students, this was some general information about your S block elements, P block elements, D block elements, and F. And one thing I forgot, this is your general outermost configuration of your D block elements. N-1, D 1 to 10, N is 0 to 2. Similarly, you have to remember this as well. This is your general outermost configuration of your F block elements. Okay. It can be asked. What is the general outermost configuration of F block? What is the general outermost configuration of D block? So you should be knowing all this, right? Now, my dear students, comes something very, very, very important, from which question frequently comes when it comes to your periodic table. And what is that? How do we predict the period number and group number of an element? How do we predict the period number and group number of an element? Try to understand very clearly and logically what exactly I'm going to do. My dear students, for example, you are given with a question. In the question, they have given you the electronic configuration of an element. In the question, they have given you electronic configuration of an element. Now, from the electronic configuration of an element, you have to check what is the period number of the element. From the electronic configuration, you have to check what is the period number of an element. How do you check that? Simple. Period number is equal to highest value of your quantum number. Highest value of your principal quantum number. Period number is equal to highest value of your principal quantum number. For example, look at these three examples. Let's say I'm given the question, and in the question, they have given the outermost electronic configuration like this. And from this outermost electronic configuration, you have to check the period number of an element. Right? What is the highest value of principal quantum number? It is 3. So it belongs to period number 3. What is the highest value of principal quantum number here? 4. So it belongs to period number 4. What is the highest value of principal quantum number here? 5. So it belongs to period number 5. Right? So highest value of principal quantum number, it gives me the period number of an element. As simple as that. Okay? As simple as that. Now, my dear students, how do we get the group number of an element? How do we get the group? See, period number is simple. If the electronic configuration is given, check the highest value of principal quantum number. Whatever is going to be the highest value of principal quantum number, that is going to give you the period number of an element. Now, if I talk about the group number, how do we check the group number if electronic configuration is given? How do we check the group number if electronic configuration is given? Now, my dear students, here you have to remember certain things. What are the certain things? Let me tell you, in case of S block elements, group number, period number is same, highest value of principal quantum number. What about group number? In case of S block elements, group number is equal to number of electrons in ns orbital. Number of electrons in ns orbital. What does that mean? For example, you are given with this particular electronic configuration, and from this particular electronic configuration, you have to identify things. What all things? See, first of all, see the last electron has entered into S subshell, right? So it is first of all your S block element. Number 1, right? What is the highest value of principal quantum number? That's 4. So its period number is 4. Now, what is its group number? The number of electrons in ns orbital. This is your ns. This is n-1p. This is n-1s. Do you understand? So this is your ns basically. And in ns, there is only 1 electron. So its group number is 1. So this particular element whose electronic configuration is given to us, it belongs to group 1, which is what you call as your alkali metals, right? So it belongs to your alkali metals. Now, similarly, look at this particular example. Again, you are given the electronic configuration, right? The last electron has entered into S subshell, so it's the S block element. In case of S block elements, the number of electrons in ns is equal to 2, so its group number is 2. It belongs to second group. So it's your alkaline earth metal. I hope you're understanding all this. Now, in case of your p block elements, how do we calculate the group number? Group number is nothing but it is 10 plus sum of electrons in ns and np. 10 plus sum of electrons in ns and np. For example, this is the electronic configuration that is given to me, right? First of all, check the last electron. Last electron has entered the p subshell, so it's a p block element first of all. Highest value of principal quantum number is 4, so its period number is 4. Now, what about its group number? Its group number will be, since it's a p block element, 10 plus number of electrons in ns and np. So this is np, this is ns. np contains 2, ns contains 2. So 2 plus 2 comes out to be 4. So it is the 14th group element. It is the 14th group element, right? Look at this one. Again, the outermost electronic configuration is given to me. The last electron has entered in the p subshell. So it's a p block element. The maximum value of principal quantum number is 3. So it is basically, it belongs to your period number 3. Now, how do I check its group number? It's again going to be 10 plus number of electrons in np is 5. Number of electrons in ns is 2. So 5 plus 2 makes it 7. So 10 plus 7 makes it 17. So it is a 17th group element, right? And you know already 3s2, 3p2 is basically chlorine. It is basically the outermost configuration of chlorine that's given to me. Yeah? So in case of your s block elements, group number is equal to number of electrons in ns. In case of your p block elements, group number is equal to number of 10 plus the sum of number of electrons in ns and np. I believe this is clear. Now, in case of your d block elements, how do you check the group number in case of d block elements? My dear students, it's pretty much simple. It's pretty much simple. In case of your d block elements, the group number is sum of n minus 1d and ns electrons. Sum of the electrons which are present in n minus 1d and the electrons which are present in ns. For example, this is the outermost configuration of an element that's given to me. Now look at this. This is your ns. This is your n minus 1d. This is ns. This is n minus, see, this is ns. So this is n minus 1d. So first of all, check carefully. The last electron has entered into d subshell. The last electron, it is 3d6 4s2. The last electron has entered into d subshell. So it is basically a d block element. And you know it clearly, guys, it is 3d6 4s2. It has to be iron, right? It has to be iron. Now the point is, it is going to be its period number first of all. Period number means the highest value of principal quantum number. Its period number is 4, number 1. Number 2, it is a d block element. Number 3, its group number. Its group number, since it is a d block element, number of electrons in d. Number of electrons in n minus 1d, that's 6, plus number of electrons in ns, that's 2. So 6 plus 2 comes out to be 8. So this particular element belongs to the 8th group. Okay, this particular element belongs to the 8th group. I believe again this is clear. And people, at the same time, all your F block elements, which consists of your lanthanoids and actinoids, right? From atomic number 58 to 71, your lanthanoids. From atomic number 90 to 103, your actinoids. All these, they belong to, as I told you already, they belong to group number 3. Perfect. Is this particular stuff clear till here? Let me know once in the chats, everyone. And if it is clear, then comes one more important thing, my dear students, which you need to remember. Right now, I told you one thing. I told you how to check the period number, group number, and block number. And block basically of an element whose electronic configuration will be given to us. Right now, I showed you how to check the period number, the group number, right? And the block of an element whose electronic configuration will be given to us. But what if electronic configuration is not given to us? What if directly atomic number is given to us? Yeah, do you understand? What if atomic number is given to us? From atomic number, how do I check the period number? From atomic number, how do you check the group number? How do you check the block, etc., etc.? Yeah, let's talk about that. For example, I'm telling you, I've got the element whose atomic number is 35. Tell me which group it belongs to. Tell me its period number, etc., etc. How do we check all of this? Let's get to know about that. My dear students, first of all, if atomic number is given and you are supposed to check the period number, you are supposed to check the period number. Okay? You are supposed to check the period number. Before showing you how to check the period number, these are your noble gases: helium, neon, argon, krypton, xenon, radon. Perfect. Right? This is the magic number which every one of you would be already knowing: 2, 8, 8, 18, 18, 32. 2, 8, 8, 18, 18, 32. Well, the atomic number of helium, I believe everyone knows that is 2. Right? Now, atomic number of neon. 2 plus 8 makes it 10. 10 plus 8 makes it 18. 18 plus 18 makes it 36. 36 plus 18 makes it 54. 54 plus 32 makes it 86. Right? These are the atomic numbers of these noble gases. These are the atomic numbers of these noble gases. Right? And my dear students, these are the period numbers of these noble gases. Your helium belongs to period number 1. Neon, second period. Argon, third period. Krypton, fourth period. Xenon, fifth period. So this is something which everyone should remember first of all, because this is important. Frequently, I'll be using this particular table. Now, try to understand. How do we identify the period if atomic number is given? My dear students, first of all, if atomic number is between 58 to 71, if the atomic number of an element is from 58 to 71, 58 to 71, 58 to 71 means your lanthanoids. And your lanthanoids, they belong to which period? They belong to 6th period directly. Remember it. Okay, they belong to 6th period directly. So atomic number 58 to 71. Perfect, your lanthanoids. Atomic number 90 to 103. That's your actinoids. And actinoids belong to 7th period. Lanthanoids, 6th period elements. Actinoids, 7th period elements. Perfect. Right? So directly you remember this. For example, I'm telling you what is the period number of the element whose atomic number is 93. So 93 comes in this category. So period number is 7. Atomic number of the element whose atomic number is 97. 97 atomic number comes in this particular thing, in between these two. So period number 7. Atomic number 65 comes in between these two. So period number 6. 70 again comes in between these two. Period number 6. Simple, right? Similarly, if the atomic number neither comes in this category nor is in this category, if the atomic number is neither in this category nor in this category, then how do we check the period number? My dear students, then period number is going to be equal to the period number of next inert gas. If atomic number of an element neither comes in this category nor comes in this category, then period number of an element is equal to the period number of next inert gas. For example, what is the period number of an element? What is the period number of an element whose atomic number Z is equal to 44? 44 neither comes in this category nor comes in this category, right? Now, if atomic number neither is in this category nor is in this category, then remember period number is equal to the period number of next inert gas. So what is the next inert gas after atomic number 44? After atomic number 44, the next inert gas has got the atomic number of 54. And atomic number 54 means xenon. Xenon's period number is 5. So I would say the period number of this particular element will also be 5. Atomic number 32. 32 neither comes in this category nor comes in this category. Now what is the next inert gas after 32? After 32, next inert gas is krypton, whose atomic number is 36. Its period number is 4. So the period number of this particular element will also be 4. I believe this is clear to everyone. Yeah. And my dear students, if this is super clear to everyone, then let's have a look on how do we identify the groups. How do we identify the groups if the atomic number is given? We already know how to identify the groups if electronic configuration is given. Now let's get to know how to identify the group if atomic number is given. First of all, my dear students, if the atomic number is in this category, 58 to 71, lanthanoids, 90 to 103, actinoids, all the lanthanoids and actinoids, they belong to group number 3. This is the direct thing, which you know. They belong to group number 3, correct? They belong to group number 3, right? This belongs to period number 6. This belongs to period number 7. And both of them, they belong to group number 3, your A block elements. Now, my dear students, if the atomic number is between 104 to 118, if the atomic number is between 104 to 118, then group number is equal to the last 2 digits of the atomic number. Then group number is equal to the last 2 digits of the atomic number. For example, I'm telling you, I've got the element whose atomic number is 107. Tell me its group number. 107 neither comes in this category nor comes in this category. So what do? Last 2 digits. Its group number is 7. Its group number is 7. I've got an element whose atomic number is 111. Last 2 digits is 11. Its group number is 11. So if the atomic number neither comes in this category nor comes in this category, then its group number is nothing but last 2 digits. That's it, right? And my dear students, if the atomic number neither comes in this category nor comes in this category nor comes in this category, You understand? If the atomic number neither comes in this category, nor comes in this category, nor comes in this category, how do we get the group number then? Then remember, group number is equal to 18 minus atomic number of next inert gas minus atomic number of an element. What does that mean? Try to understand. For example, I've got an element whose atomic number is 44. I've got an element whose atomic number is 44. 44 neither comes in this, nor comes in this, nor comes in this. So how do I get its group number? Its group number is going to be equal to 18 minus next inert gas after 44. Next inert gas after 44 is 54, right? Is 54. So it's going to be 18 minus next inert gas has got the atomic number 54 minus what is the atomic number Z here? Z is 44. So my dear students, 54 minus 44 is 10. 18 minus 10 comes out to be 8. So this particular element whose atomic number is 44, it belongs to 8th group. As simple as that. Similarly, Z is equal to 32, atomic number 32, atomic number 32, neither in this, nor in this, nor in this. So how do I get the group number? Again, simple. Group number will be equal to 18 minus next inert gas after 32. Next inert gas after 32 is 36. Next inert gas after 32 is 36 minus Z. Z value is 32. So 36 minus 32 is 4. 18 minus 4 is equal to 14. So this particular element belongs to 14th group, right? Now, what if by using this particular formula, answer comes out to be negative? At that point of time, instead of 18 here, you have to use 32. What if by using this particular formula, the answer comes out to be negative? So at that point of time, instead of 18, you write 32 here. Then you use this particular formula. So this was about the identification of period number, the identification of group number, if electronic configuration is given, or if atomic number is given. So tell me, till now, is every single thing clear or not? I want to know first of all. Let me know quickly, people. Everyone in the chats. Everyone in the chats. Say yes or no in the chats if all the things are super clear to you. I just want to know. I just want to know. Is it like very clear? Everyone in the chats means everyone. I'm looking at your chats. Quickly, everyone. Just say yes or no in the chats. That's it. I'll move ahead after that. Perfectly done, guys. Perfect. So let's move on to one more small topic. Okay, one more small topic here, from which again question frequently comes. What is that? Your favorite one. Your favorite one. What is that? Naming of the elements which have got atomic number greater than 100. Naming of the elements which have got atomic number greater than 100. Now, my dear students, first of all, for number 0, the prefix used is nil. For number 1, the prefix used is un. For number 2, bi, tri, quad, pent, hex, sept, oct, n. And suffix used is always ium. What does it mean? It's pretty much simple. You know it already. For example, I've got an element whose atomic number is 104. I've got an element whose atomic number is 104. Now, I want to name this compound. I want to name this particular element. First of all, this is number 1. 1 stands for un, right? 0 stands for nil. 4 is basically quad. And at the end, what do we use? As a suffix, we use IUM. So this is the name of the element. Now, how do we represent it? We represent it like this. The first letter of this is U. The first letter of nil is N. The first letter of chord is Q. So it's U, N, Q. This is how you are going to represent it. Simple. For example, you have got the element whose atomic number is, let's say, 112. 112. What is going to be its name? First of all, 1 means un. Right? 1 means un. This one also means un. 2 means by. And at the end, what do I use? I use IUM, right? Perfect. So what is going to be, how you are going to represent it? It's going to be U, U, B. U, U, B. Perfect. For example, I've got an element whose atomic number is, let's say, 115. 115. So its name is going to be un, right? Then again 1. Un, 5 means pent, and at the end you'll be using IUM. This is its name, and how you are going to represent it? It's going to be U, un, U, and P. So U, U, P is the symbol of this particular element. Right? Right, people? I believe this is clear. I believe all of this is clear. So now let's move on to something called as shielding or screening effect. Shielding or screening effect. How do we define the shielding effect? How do we define the screening effect? This is something which plays a vital role in your different questions, wherein you have to arrange on the basis of size, on the basis of ionization energy, on the basis of this, that, right? For that, this particular topic is important. So first of all, you should know what is screening or shielding effect. Thank you, Akash. That's great. Glad to know that you are in first year of your MBBS and you have learned from this channel. Amazing. God bless you. Okay. So how do we exactly define the shielding effect, screening effect? Try to understand, people, what I'm going to say. For example, this is the nucleus of an atom. This is the nucleus of the atom. And let's say this is the outermost shell of an atom, and this is the electron which is present in the outermost shell. This is the electron which is present in the outermost shell. Now, definitely there will be force of attraction between nucleus and outermost electron right now. Absolutely, there will be force of attraction. Just to make you understand, let's say this nucleus is attracting this electron towards itself with a force of 5 Newton. Just to make you understand. Let's say this nucleus right now is attracting this electron towards itself with a force of 5 Newton. Okay? Now, for example, imagine there are some inner shell electrons as well. Now, what these inner shell electrons are going to do? This is electron. So there will be repulsion between these two. Now tell me, in presence of the inner shell electron, is the nucleus going to attract the outermost electron with the same 5 Newton force? Now the nucleus is not going to attract the outermost electron with 5 Newton force. Definitely, nucleus will be attracting this outermost electron now with a force less than 5 Newton, because there are repulsions as well. Okay? Let's say this was 5 Newton force experienced by the electron in absence of inner electrons. Now, in presence of inner electrons, let the force experienced by this outermost electron now is 2 Newton. So what happened basically? I would say, due to the presence of inner shell electrons, force experienced by the outermost electron has decreased. This decrease in the force of attraction, the decrease in the force of attraction on the valence electron due to the inner shell electrons, this is something which we call a screening effect. This is what we call a screening effect. This decrease in the force of attraction due to the presence of inner shell electrons is what we call as shielding effect. Okay, is something we call as shielding effect. I believe this is clear. And my dear students, now there can be either good shielding or there can be poor shielding. Now just relate it like this. Imagine as if These inner electrons, they are behaving like a shield. They are behaving like a shield. Now think like this. If shielding is more, if shielding is more, if shielding is more, if shielding is more, my dear students, just a second. What just happened, guys? What just happened? Let me make it again. So this was the nucleus, this was the outermost shell, outermost electron, and these are the inner shell electrons, right? This is something. So first of all, if shielding is more, what would happen? If shielding is more, force of attraction on the outermost electron will be less. Shielding is more, force of attraction on the outermost electron will be less, right? Perfect. Do you understand? So can I say, due to good shielding, due to effective shielding means good shielding, due to effective shielding, force of attraction on the outermost electron will be less. That means if force of attraction on the outermost electron is less, that means effective nuclear charge is less. So you can relate these two terms now. Whenever I say effective nuclear charge is less, that means force experienced by the outermost electron is less. Right? Right, people? I believe this is clear. Sir, please wait and give questions as examples between the topics. Sir, you have been going so fast. What was all this which I was giving? Were not the questions? Atomic number 57, tell me its period number. Atomic number 62, tell me its group number. Were not the questions? The speed is perfect. Yeah, I'm not going to match your speed. You are going to match my speed. Okay? Because this is a marathon of complete inorganic chemistry. This is not a single chapter. This is your complete class 11th inorganic chemistry which I'm teaching. Just understand that. Okay? And if you have got any sort of doubts in between, you can rewind the session, watch it again. Don't ask me to repeat. I hope I'm clear. Well, these are the rules of the online marathon basically, which everyone should know. Okay? Now guys, try to understand one more thing. I told you, there can be good shielding, there can be bad shielding. That means there can be effective shielding, there can be ineffective shielding. Due to effective shielding, due to good shielding, due to effective shielding, force experienced by the outermost electron will be less. Or you can say, effective nuclear charge is less. Similarly, my dear students, similarly, due to poor shielding, due to ineffective shielding, force experienced by the outermost electron will be more. Or you can say, Z effective is more. Now relate the things like this. Whenever from now onwards I say effective nuclear charge, Z effective is more. If I say Z effective is more, what does that mean? If I say Z effective is more, that means force of attraction experienced by the outermost electron is more. If I say Z effective is less, that means force experienced by the outermost electron, by the nucleus, is less. Right? Perfectly done. Now, my dear students, let's move on. I believe these 2 points are clear. Due to effective shielding, effective nuclear charge will be less. Due to ineffective shielding, effective nuclear charge would be more. Okay? Right? And what is the order of this shielding? Your s orbital electrons, they show maximum shielding because they are closer to the nucleus. And your d and f orbitals, your d and f orbital electrons, they show poor shielding. They show ineffective shielding. Okay? Remember this particular point as well. I'll be using it frequently. S orbitals, they show maximum shielding, right? Since they're closer to the nucleus, whereas your d orbitals and f orbitals, right? They show ineffective, they show poor shielding. Okay? Remember this particular point. Now tell me, if they show poor shielding, that means force of attraction experienced by the outermost electron, is that going to be more or less? If these two show ineffective shielding, if they show poor shielding, that means force of attraction on the outermost electron will be more because of the poor shielding of d and f electrons. Yes? Perfect. Now, my dear students, let me talk about one more important thing which you need to know. What is that? Understand. For example, I have got an atom A. Let's say this atom has got 7 electrons and 7 protons. This atom has got 7 electrons and 7 protons. So I would say, my dear students, 7 protons are holding 7 electrons. 7 protons are holding 7 electrons. Now, if I take 1 electron out of it, it gets converted into A positive. Now, in A positive, there will be 6 electrons, but there will be still 7 protons. There will be still 7 protons. So earlier, 7 protons were holding 7 electrons. Now, the same 7 protons are holding 6 electrons. They are just holding 6 electrons. And I say, force of attraction experienced by the outermost electron here will be more. Earlier, 7 protons were holding 7 electrons. Right? Now, the same 7 protons are just holding 6 electrons. So, force of attraction experienced by the outermost electron here will be more. Right? So, that means Z effective is more. So, it means when the parent atom gets converted into the cation, effective nuclear charge increases. Effective nuclear charge increases. And similarly, my dear students, when the parent atom gets converted into the anion, what happens to effective nuclear charge? It decreases. So I can summarize 2 things here. More the positive charge, more the effective nuclear charge. More the positive charge, more the effective nuclear charge. More the negative charge, lesser the effective nuclear charge. So we can generalize a statement. Your Z effective is directly proportional to the positive charge and it's inversely proportional to your negative charge. Remember this particular point. Remember this particular point, people. Okay? Look at all this, N positive, N and N negative. More the positive charge, more the effective nuclear charge. Right? So this is the order of your effective nuclear charge. Simple. Positive charge, neutral, negative charge. More the positive charge, more the effective nuclear charge. Done and dusted. Talk about this. Talk about this one. H negative, Li positive, Be di positive, B tri positive. Arrange them on the basis of their effective nuclear charge. More the positive charge, more the effective nuclear charge. Simple. Similarly, all these are having the negative charge. N3 negative, O2 negative, F negative, Na positive, Mg di positive. So tell me, more the positive charge, more the effective nuclear charge. So this is the order of the effective nuclear charge. Simple. Whatever I said, I'm utilizing that in the form of questions. Nothing else. Right? So they can give you the questions. Arrange these species on the basis of effective nuclear charge. Arrange these species on the basis of effective nuclear charge. Simple. More the positive charge, more the effective nuclear charge. That's it. More the negative charge, lesser the effective nuclear charge. That's it. Okay? Now tell me one thing. In sodium atom, the screening of 3s electron. In sodium atom, the screening of 3s electron is due to. Screening is due to the inner shell electrons. Screening is due to inner shell electrons. If you talk about sodium, the electronic configuration of sodium is 1s2, 2s2, 2p6 and 3s1. Right? So, if you talk about this outermost electron, screening for this outermost electron is due to the inner shell electrons. Due to 1s2, 2s2 and 2p6. So, the direct answer is option C. We have nothing to think over in this particular question. Yeah? There is nothing to think. There is nothing to think in this particular question. Shielding is due to the inner shell electrons. Okay? I believe this is clear. And my dear students, if this is clear, let's talk about the atomic radius. How do we define the atomic radius? One of the simplest definitions. Normally, in layman's language, how do we define atomic radius? The distance from the center of the nucleus to the outermost shell. That's what we do. The distance between the nucleus and the outermost shell in an isolated atom. This is the point here. The distance between the nucleus and the outermost shell. The distance between the nucleus and the outermost shell. For example, this is the nucleus. For example, for the sake of your convenience, this is the outermost shell. The distance from here to here is what you call as the atomic radius. But atomic radius, if you look here, I have mentioned the term in case of the isolated atom. So the atom has to be isolated. What is meant by isolated? Isolated means atom should not be in the bonded state. Atom should not be in the bonded state. Then only we can define atomic radius. Atom should not be present in the bonded state. Then only we can define atomic radius. First of all, you tell me one thing. Can we define the boundary of the atom? Can we define the boundary of the atom? We cannot define the boundary of it. We cannot say exactly this is the boundary of the atom. Because you know this is electron cloud exactly. Exactly, there will be electron cloud. Right? In your atomic structure you would have studied. You cannot define the exact boundary of the atom. No way. Then the orbital concept is invalid. So if you cannot define the exact boundary of the atom, at the same time, the atom should be isolated. Can you isolate an atom? Can you isolate an atom? So my dear students, since you cannot define the exact outermost boundary of the atom, that is the reason why your atomic radius, it cannot be measured experimentally. It cannot be measured experimentally. Since your atoms, they exist in bonded form. They exist in bonded form. That's why atomic radius term is defined under which conditions? Not under isolated conditions, under bonded conditions. We define atomic radius in bonded conditions. Why is that? Because your atoms, they are in bonded state always, right? That is the reason atomic radius is defined under which conditions? Under bonded conditions. Now, between the atoms, there can be covalent bond. Between them, there can be metallic bond. There can be van der Waals bond. So that is the reason why atomic radius we classify into three types here. One is covalent radius, one is metallic radius, one is van der Waals radius. First of all, atomic radius is defined in bonded conditions. Now bonds can be covalent, it can be metallic, it can be van der Waals, right? So your atomic radius we are going to classify into three types. Your covalent radius, your metallic radius, your van der Waals radius. So your covalent radius is defined when covalent bond formation has taken place between the atoms. And covalent bond generally takes place, covalent bond is generally formed by non-metal atoms. So technically I would say covalent radius is generally defined for non-metal atoms. Your metallic radius, it is defined for your metals. And your van der Waals radius, it is defined for the noble gases or the non-metals. Now let's try to understand all of them one by one. Okay, so first of all, I'm going to talk about the covalent radius. First of all, I'm going to talk about the covalent radius for a homonuclear molecule. Covalent radius. As I told you already, my dear students, your covalent radius, it is defined for non-metal atoms. Why? If my question is why? Because covalent bond formation takes place between non-metals only. Okay. Now people try to understand. First of all, as I told you, it's defined for non-metal atoms. Now, for example, this is your atom A and this again atom A. Now, these two atoms are going to form a covalent bond. They are going to form a covalent bond like this. They are going to form a covalent bond like this. So, let me show it to you exactly. Let's say this is your atom A and this is the nucleus of the atom A. This is the nucleus of the atom A. Similarly, this is for example your atom B. Sorry, again atom A. This is the nucleus of the same atom A. Perfect. Now they are going to come closer. When they come closer, what's going to happen? Their atomic orbitals will merge into each other. And when the atomic orbitals will merge into each other, this is going to be the scenario. This is the nucleus of the first atom. This is the nucleus of the second atom, right? Since the atomic orbitals have merged into each other, electron clouds have merged into each other, and due to the merging of electron clouds, which bond gets formed? A covalent bond gets formed. So a covalent bond has got formed between these two atoms, right? Now, my dear students, the distance between the nuclei of these two atoms. This is first of all your A2 molecule. The distance between the nuclei of these two molecules is what you call as bond length. Which I represent with DAA, right? Which I represent with DAA. This is the bond length over here. Now, what we have to do? How do we define the covalent radius here? I would say covalent radius is defined as, the half of the internuclear distance. Half of the internuclear distance. Covalent radius is defined as the half of internuclear distance when it comes to your homonuclear molecule. Am I clear? So basically, half of this particular distance is what you call as the covalent radius. As simple as that. Am I clear? Am I clear, people? Now, when it comes to the metallic radius, in case of metallic radius, this is the metal atom, this is the metal atom. Now, over here, there won't be merging of electron clouds like your covalent bond. There won't be merging of electron clouds like your covalent bond. How we are going to show it instead? We show it just as if these metal atoms are touching each other, right? So these are metal atoms. Get the internuclear distance between them, divided by 2, you'll be getting the metallic radius. So metallic radius is nothing but, it is the internuclear distance between the two, right? Now, since in covalent radius, merging of electron cloud happened. So internuclear distance in covalent, the bond length in covalent is less than that of this particular internuclear distance. That is the reason why your metallic radius is greater than that of covalent radius, right? You can understand properly. If you talk about your covalent radius, merging of electron cloud happened. Then we calculate this particular distance. Just made it half. We got covalent radius. Now what is happening in metallic? I'm just showing them as if they are touching each other. Now, the internuclear distance here is more. If the internuclear distance here is more, that means half of it will be also more. That means your metallic radius is greater than that of covalent radius. Remember that. Okay. Now comes your van der Waals radius. Van der Waals radius is defined for noble gases, and the noble gases must be present in solid state, people. It is defined for noble gases, but noble gases must be present in which state? Solid state, right? For example, this is your neon atom and this one more neon atom. Both are in solid state. Perfect? Both are in solid state. When it comes to the van der Waals interaction, we do not show merging of electron clouds here. We show these atoms are far apart, but there is attraction between them. We show, is this live really? Yes, this is live. You can check the time. It's 18:17. That means 6:17. Okay. कहाँ से चले आते हैं लोग? Okay. Anyways, if we talk about the van der Waals radius, in van der Waals radius, what do we say? We say these noble gases, they must be present in the solid form. Number 1. Number 2, we do not show merging of electron clouds. We show atoms far apart from each other, but there will be attraction between them. Now, I'll be getting this particular distance, internuclear distance. Again, I'll be dividing it with 2. What do I get? I'll be getting the van der Waals radius. Perfect. Now, you tell me, guys, among van der Waals, among covalent, among metallic, which radius will be maximum? Van der Waals radius will be maximum, followed by metallic, followed by covalent. Isn't it simple? It is maximum because there is no bonded region. Now, is the van der Waals radius defined only between the noble gases? No, because I mentioned already. Van der Waals radius is defined for noble gases as well as non-metal atoms. What does that mean? Try to understand. For example, this is Cl2 molecule. This is also Cl2 molecule. If you talk about this Cl2 molecule, basically this is Cl and this is Cl. Between them, there is a covalent bond. Cl2 molecule. This is Cl, this is Cl. Between them, there is covalent bond. Now, I can say this is Cl2 molecule now. This one more Cl2 molecule. Perfect. Now, between two Cl2 molecules, there can be van der Waals force of attraction in between them. Between two Cl2 molecules, there will be van der Waals force of attraction between them. Now, the distance from here till here is what I'll be calling as internuclear distance. Now, divided with half, divided with 2, what do I get? I'll be getting van der Waals radius. Perfect. So, van der Waals radius is maximum among all. So, first priority will go to van der Waals radius. And remember one important point, van der Waals radius. That means this particular radius, I'm showing it over here. See, first of all, get this particular distance, divide it with 2, you call it as the van der Waals radius. Number 1. Number 2. The distance from here till here, divide it with 2, you'll be calling it as covalent radius. Since between these two, there is covalent bond. Among these two molecules, there is van der Waals force of attraction. Remember, your van der Waals radius is 2 times almost the covalent radius. This is again very important point which you need to take a note of. Okay. Now, my dear students, if this is clear, let's try to understand something called as cation radius and anionic radius as well. Now, if I ask you, is this particular statement correct? If I say cationic radius is always smaller than that of atomic radius, is this statement correct or not? For example, I've got the atom A, I'm converting it into cation. I told you a few minutes back, when a cation gets formed, effective nuclear charge increases. Effective nuclear charge increases means the force of attraction between nucleus and outermost electron increases. If force of attraction between nucleus and outermost electron increases, I would say outermost electron would have come closer, right? So size would have comparatively decreased. So among the parent atom and the cation, which one will have smaller size? Cation will have smaller size than that of parent atom. That's what is mentioned over here. Cationic radius is always smaller than that of atomic radius. Number one. One thing is clear. One thing is clear, guys. One thing is clear. More the effective nuclear charge, more the effective nuclear charge, more is the force experienced by the last electron. More is the effective nuclear charge, more is the force experienced by the valence electron. That means lesser will be the size. Correct? Correct, people? Is this clear? So can I say size is directly or inversely? Directly or inversely? It is inversely proportional to effective nuclear charge. More the effective nuclear charge, lesser is going to be the size. And one thing which you already know, effective nuclear charge is directly proportional to positive charge, inversely proportional to negative charge. Perfect. Similarly, if I talk about the anions, or before talking about the anions, see A positive, A di positive, A tri positive. If I need to give the order of the size here, I'll say more the positive charge, more the effective nuclear charge, lesser the size. So this will have least size, A tri positive. It will have least size. Simple. So the size order is going to be this. This is the ionic size order here. Perfect. Now similarly, if I talk about the anions, then I'll show you certain questions as well. If I talk about the anions, guys, few minutes back, I told you one thing. When a parent atom gets converted into an anion, effective nuclear charge decreases. Effective nuclear charge decreases. If the effective nuclear charge decreases, that means the force of attraction between the nucleus and the outermost electron, that decreases. So automatically size will increase. Yes, size will increase. Perfectly done, guys. Perfectly done. So can I say something like this? More the negative charge, lesser will the effective nuclear charge. Lesser the effective nuclear charge, more is going to be the size. Same thing which I told you right here. Same thing which I mentioned here. Size is inversely proportional to effective nuclear charge. Effective nuclear charge is inversely proportional to negative charge. More the negative charge, lesser Z effective. Lesser Z effective, more size. Okay. Now, guys, for example, what if this question is asked? Arrange them on the base of the atomic. Arrange them on the base of their size. Arrange them on the base of their size. O negative, O di negative. More the negative charge, lesser the effective nuclear charge. Lesser the effective nuclear charge, more the size. So this will have maximum size, followed by O negative, followed by O. Correct? Right? Now similarly, N negative, N di negative, N pri negative. Give the size of the ions. Give the size of the ions. More the negative charge, lesser the Z effective, lesser the Z effective. Lesser the Z effective, more is the size. So this is the order of this ionic size here. Right? Perfect, guys. Is all this clear to you or not? Is all this clear to you or not? So if I summarize it, your size or atomic radius, that is inversely proportional to Z effective. And you know, Z effective is directly proportional to positive charge, inversely proportional to negative charge. Now you can solve these sort of questions quickly in very lesser time, guys. Now understand, N tri negative has got in total 10 electrons. O di-negative, in total 10 electrons. F negative, in total 10 electrons. So all these species have got same electrons. And those species which have same electrons, what do we call them as? We call them as isoelectric species or isoelectronic species. And frequently a question is asked, arrange the following isoelectronic species on the basis of their size. Right? Arrange the following isoelectronic species on the basis of size. What you have to do? More the positive charge, more the positive charge, more the effective nuclear charge, lesser the size. Simple. So more the positive charge means lesser the size. Al tripositive will have least size. And the one that carries maximum negative charge will have the maximum size. Understood? This is the order of the size here. So people, one thing which I believe everyone would already know now, in your periodic table, what happens generally when you move from left to right? Generally, when you move from left to right, what happens? Generally, when you move from left to right, what happens? What happens to the size? Size decreases on moving from left to right, generally. And on moving from top to the bottom. On moving from top to the bottom, since shell number increases, so size increases. So generally, on moving from left to right, size decreases, atomic radius decreases. And similarly, top to the bottom, size increases, or you can say atomic radius increases. This is something general which I believe every one of you would already know. Okay? Perfect, guys. So simple question. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Give the order of the size. They belong to same period. Right? They belong to same period. Along the period, what happens to size? Along the period, size decreases. From left to right, size decreases. Simple. Right? Size decreases. So lithium will have maximum size, followed by beryllium, followed by boron, followed by carbon, followed by nitrogen, oxygen, fluorine. Right? Similarly, guys, in the group, when you move down the group, shell number keeps on increasing. So size keeps on increasing. Atomic radius keeps on increasing. So among lithium, sodium, potassium, rubidium, cesium, they belong to same group. Down the group, size increases. So cesium will have maximum size, followed by rubidium, followed by potassium, followed by sodium, followed by lithium. These are some basic things, guys, which you should know. There is one thing though. What is that? What is that? I told you on moving from left to right, size decreases. On moving from left to right, size decreases. I told you that. So if I talk about the second period, lithium, hydrogen, helium, lithium, then beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. These are your second period elements. Right? Your second period elements. Now, my dear students, tell me, on moving from left to right, what should happen to the size? Size should decrease. So I would say neon should have least size among all. Neon should have least size among all. That's my expectation. But at the same time, neon is a noble gas. For noble gases, we define van der Waals radius. Van der Waals radius is maximum among all. Van der Waals radius is maximum among covalent radius, among metallic radius, right? So remember, it is observed that the size of inert gas is very large as compared to the halogens. If you compare these two, this is due to the van der Waals size measurement in case of inert gas. Okay, so remember, technically neon should have lesser size than that of fluorine, but in reality neon has got far more greater size than that of fluorine. Remember this particular point as well. This can be asked in your examination. Okay. My dear students, one more exception. This was your exception number 1. This neon in the period. Noble gas has got the maximum size. It should have the minimum size as per our rules, but it has got the maximum size. Why is that? The reason is because for noble gases we define van der Waals radius. Now guys, look at this one. Remember one more thing. These are your 3D elements, right? These are your 3D elements. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Let me tell you, when you move from scandium till iron, let me tell you, Z effective is greater than screening. When you move from scandium till iron, Z effective is greater than screening. Due to which, if Z effective is greater than screening, I would say the size decreases from scandium till iron. Now, in case of iron, cobalt, nickel, Z effective and screening, they counterbalance. If they counterbalance, that means iron, cobalt, nickel, their size is almost the same. Their size is almost the same. And when you move afterwards from copper to zinc, what happens? Screening is more than that of Z effective, due to which size again increases. So remember this particular point as well. This can be asked. From scandium till iron, your size decreases. Iron, cobalt, nickel, size is almost the same. Then from copper to zinc, size again increases. I mentioned the reason as well, which can be asked in your examination. Okay? So see, scandium till iron, size decreases. Then iron, cobalt, nickel, almost same. And again, size increases. Again, size increases. Okay? Now guys, there is third exception. First one was the noble gas exception. Second one was your 3D, your D series, right? The third exception, which you will be remembering as exception, and if you know the logic, then you won't be calling it as exception though. Since I'm giving you the logics as well, right? So you won't be calling them as the exceptions. My dear students, these are your D block elements: 3D series, 4D series, 5D series. 3D series, 4D series, 5D series. Now see, if you look at this particular group, scandium, Y, lanthanum. On moving from 3D to 4D, 4D to 5D, what should happen to the size? Size increases. So LA will have maximum size. LA will have maximum size, followed by Y, followed by scandium. This is correct. This is the order of the size. This is the order of the radius, atomic radius. Perfect. Now, my dear students, I'm expecting the similar trend here also. In this particular group. I'm expecting the similar trend. Similar trend matlab, I'm expecting from titanium to zirconium, zirconium to hafnium, I'm expecting size should increase. This should have maximum size, followed by this, followed by this. This is my expectation. But in reality, what happens? See, my dear students, after lanthanum, I hope you remember lanthanum, whose atomic number is 57. After lanthanum, what do we have? After lanthanum, we have got lanthanoids. Atomic number 58, 59, 60, 61, right? So technically, I would say before hafnium, there will be F block elements. In between lanthanum and hafnium, there will be 14 F block elements. There will be 14 lanthanoids. So before hafnium, there are F block elements. Before hafnium, there are F block elements. In between them, there are F block elements, right? And in case of F block elements, the electron goes into F subshell. And your F subshell shows pore shielding. Due to pore shielding, Z effective increases. And if Z effective increases, size, if Z effect increases, that means force of attraction between nucleus and outermost electron increases. So size should technically decrease. Do you understand? See, from here to here, size will increase. Now, from here to here, size should increase because shell number is increasing. But at the same time, due to the ineffective shielding of your F electrons, I would say size should decrease, right? So one parameter, the increase in the shell number, is telling you size should increase. And due to the pore shielding, size should decrease. That is the reason why zirconium and hafnium, they'll have almost same size. That is the reason why this element and this element, they'll have almost same size. Why this and this, they'll have almost same size. This and this, almost same size. But here, among Y and lanthanum will have more size than Y. Because your lanthanoids, they start after this element. Not before this element. Understood? Remember, the size of 3D will be minimum, followed by 4D, and 4D and 5D size will be almost the same. I hope this particular point is clear to everyone. Okay, I hope this particular point is clear to everyone. If this particular point is clear, then you need to answer this question. Answer me this question. Answer me this question, guys, quick. This has been asked in your NEET once. boron, aluminium, gallium, indium, and thallium. Generally, if you look carefully on moving from top to bottom, size should increase. This is the general trend. This is the general trend. Size should increase. Perfect. Size should increase. So order should be like this. Boron, aluminium, gallium, indium, and thallium. This is my expected order of the size. This is my expected order. But if you look carefully, before gallium, there will come your D block elements. D block elements will come before gallium. So before gallium, there will be 10 D block elements. And if there are D block elements before gallium, that means in these D block elements, the electrons will go into D subshell. And your D subshell shows pore shielding. And due to pore shielding, Z effective increases. Due to Z effective increase, the size decreases. So that is the reason why the size of gallium is lesser than that of aluminium. Why the size of gallium is lesser than that of aluminium. Why? Because before gallium, there will come some there will be the D block elements. And due to the pore shielding of D orbitals, right? Due to the pore shielding of D orbitals, I would say the size of the gallium will be less than that of aluminium. So what will be the order then? What would be the order? This is the order. Boron, gallium, aluminium, indium, thallium. Okay? I hope this particular point is also clear. Tell me the order of this question. The species argon K positive, calcium di positive contains the same number of electrons, so isoelectronic. In which order their ionic, their radius increase. So give the order of the radius. More the positive charge, more the effective nuclear charge, lesser the size. That's it. More the positive charge, more the effective nuclear charge, lesser the size. So this is the order of the size. Simple. Okay. Tell me. Be di positive is isoelectronic with which of the following? Be di positive. Hydrogen, helium, lithium, beryllium. Beryllium's atomic number is 4. So it should have technically 4 electrons. But we are converting it into Be di positive. So that means we are removing 2 electrons. So it will just have 2 electrons with it. So Be di positive has got 2 electrons. It is isoelectronic with what? Li positive. Hydrogen, helium, lithium. Lithium has 3 electrons. But it's Li positive. So take 1 electron out. So contains 2 electrons only. Right? So it's isoelectronic with Li positive. Simple. Yes. Tell me the wrong statement in the following. Wrong statement. Quick. What is the wrong statement? What is the wrong statement here? Well, if I read the statements, I can directly tell this is the wrong statement. Why is that? Amongst the isoelectronic species, smaller the positive charge, lesser the positive charge on the cation, smaller is the ionic radius. Is that true? No. Lesser the positive charge, lesser will be Z effective, more will be the size. Okay? More will be the size. But they are saying smaller is the size. So this is the incorrect one. Okay? It's option C, which is most appropriate among all. Tell me the answer of this question. Which of the following statement is correct? You should be giving me its answer quickly, guys, in less than 10 seconds. Ionic radius, size, is inversely proportional to effective nuclear charge. That I mentioned already. Size is inversely proportional to effective nuclear charge. So this is correct. Bas, that's it. Yeah. The correct order of decreasing ionic radius. Correct order of decreasing ionic radius. Again, these are isoelectronic species. More the positive charge, more the effective nuclear charge, lesser the size. So short mein, more the positive charge, lesser the size. More the positive charge, lesser the size. Here the positive charge is maximum, so its size will be least. So it should be option C. Done and dusted? Perfect. I hope all the things still here are absolutely clear to you. If yes, let me know once in the chats. Quickly, people. Let me know once in the chats if all the things are clear. The first break I'll give you once we complete this chapter, that is periodic classification. Okay? Don't ask me the break till then. It is going to take 1.5 hours more, this periodic classification, and we are done. Okay? So I'll be giving you a break after completing this particular chapter, not before that. Not before that. Okay? Perfectly done. Now, my dear students, how do we define this ionization energy? How do we define this ionization energy? Understand one simple thing. Understand one simple thing, guys. This is the nucleus which carries the positive charge. This is the nucleus which carries the positive charge. This is the last electron. This is the last electron. This is the last electron. Okay? Or I can say this is the most loosely bound electron because it's far from the nucleus. It is the most loosely bound electron because it's far from the nucleus. Can I say there will be force of attraction between them? Between nucleus and this? Absolutely. Let's say the atom is isolated. Let's say the atom is isolated. Also, let's say the atom is in gaseous form. Let's say the atom is in gaseous state. Let's say the atom is in gaseous state. Let's say this atom is in gaseous state. Also, the atom is isolated. It's not in bonded state, right? Now, imagine this is the most loosely bonded electron. There is force of attraction between the nucleus and this electron. Now, my dear students, you tell me. If I want to take this electron out, out of the influence of the nucleus, what does that mean? That means I have to break this force of attraction. In order to break the force of attraction, I have to supply energy. The minimum amount of energy which is required, to take out the most loosely bonded electron in the isolated gaseous atom, that amount of energy required is called as the ionization energy. That's called as the ionization energy. So what is ionization energy? It is the minimum amount of energy that's required to remove the most loosely bonded outermost electron in the ground state of an isolated gaseous atom. Okay? So for example, you have got an atom M which is in gaseous state. Now you are giving it ionization energy. That means you are giving it that minimum amount of energy which is enough to take out the most loosely bound electron. So you are giving it that energy. So that means you are taking the electron out, and automatically metal gets converted into M positive. Okay? Now guys, what is important here? Let me talk about that. For example, you have got an atom A. Okay, atom A. From the atom A, you are taking the most loosely bound electron out. So this atom A gets converted into A positive. Okay, the amount of energy required in this process, what I'll be calling as ionization energy 1. Now this A positive which we have, A positive. Let's say now I want to take the electron out. Now I want to take the most loosely bound electron out from this A positive. So I would say it would get converted into A di positive, right? And the amount of energy required in this process is called as second ionization energy. Similarly, for example, I want to take one more electron out from this A di positive. So it gets converted into A tri positive. The amount of energy required in this process is called as ionization energy 3. Now you tell me one thing. Earlier I was taking electron out from A. Now I'm taking electron out from A positive. Now I'm taking electron out from A di positive. Is the positive charge increasing? Absolutely. Positive charge increases. Means effective nuclear charge increases. So when you go from A to A positive, effective nuclear charge increases. When you go from A positive to A di positive, again effective nuclear charge increases. If effective nuclear charge increases, the outermost electron will be experiencing more force. So to take the electron out, you have to supply more energy. So can I say ionization energy third? Here you have to supply the maximum energy because the effective nuclear charge is maximum here. the force of attraction between nucleus and outermost electron will be maximum here. So maximum energy is to be supplied here to take the last electron out of the influence of the nucleus. In short, I would say the third ionization energy, it's always greater than second, is always greater than first. So this is the order which you are going to remember. Am I clear? Am I clear, people? Am I clear? Everyone in the chats? And if this is clear, then there are some more factors which decide your ionization energy. For example, you should be easily giving the answers on your own. Easily, guys. Tell me one thing. More the positive charge. Think logically. More the positive charge. That means more is the effective nuclear charge. If more is the effective nuclear charge, more is the force of attraction between nucleus and the outermost electron. If more is the force of attraction between the nucleus and the outermost electron, more energy is required to take that electron out. That means more is the ionization energy. Right? So in short, can I say ionization energy is directly proportional to Z effective? And Z effective already know, directly proportional to positive charge, inversely proportional to negative charge. Right? So can't you give answer of this question? Tell me, Fe tri positive, Fe di positive, Fe. Which one will have, where do you see the maximum ionization energy? I would say the maximum ionization energy will be here. More the positive charge, more the effective nuclear charge, more the ionization energy. Simple. Yes? Done? This is the order of the ionization energy. Perfect. Now, guys, one more thing. There are sometimes an atom will have fully filled outermost configuration. Sometimes an atom can have half-filled outermost configuration, or sometimes an atom can have partially filled outermost configuration. And I believe all of you would be knowing the stability of completely filled outermost configuration is maximum. If the stability of completely filled outermost configuration is maximum, so that means to take the electron out from that stable configuration, more energy will be required. Yeah? So what does that mean? That means technically more is the ionization energy. So whenever an atom or ion will have fully filled outermost configuration, more energy is required to take the electron out from that fully filled configuration. That means more is its ionization energy. Yeah? So remember, when it comes to your half-filled configurations, your P3 configuration, D5 and F7, they are your half-filled configurations. P6, D10 and F14, they are fully filled configurations. I hope you know. See, if you talk about your P subshell, this is your P subshell containing 3 p orbitals. If you talk about your D subshell containing 5 d orbitals, right? 1, 2, 3. This is called as P3 configuration. This is half-filled, right? 1, 2, 3, 4, 5. This is half-filled. 6, 7, 8, 9, 10. Now this is completely filled. This is half-filled. This is completely filled, right? Remember, half-filled, completely filled configurations, they are more stable. So to take the electron out from those configurations, more energy is required. More energy is required means more will be the ionization energy. So if I want to compare the ionization energy of nitrogen and oxygen, you tell me the answer. You tell me the answer now. Nitrogen, its outermost configuration is 2p3. Oxygen, its outermost configuration is 2p4. So if I want to define ionization energy of nitrogen, so I have to take electron out from this 2p3 configuration. I have to take electron out from this 2p3 configuration. Here I have to take electron out from 2p4 configuration. 1, 2, 3, 4. This is exact half-filled configuration, which is more stable. So to take electron out from here, more energy is required. More energy is required means more would be its ionization energy. So remember, the first ionization energy of nitrogen is more than that of the first ionization energy of oxygen. Reason is in front of you. Reason is in front of you. Now, if I compare the second ionization energies of nitrogen and oxygen, understand it now. If I compare the second ionization energy of nitrogen and oxygen, understand properly what I'm going to say. First of all, let me define first ionization energy of nitrogen. So that means you are taking the electron out. Just a second, guys. Wait. Okay, let me write it separately here. If I talk about nitrogen, its outermost configuration is 2p3, right? If I'm defining its first ionization energy, so I'm taking one electron out from it. its configuration becomes, this becomes N positive, and now its configuration is 2p2. Okay. Now, if I want to define second ionization energy of nitrogen, so I have to take electron out from here. I have to take electron out from N positive. N positive is 2p2 configuration. So from 2p2 configuration, I have to take electron out. It becomes N di positive with 2p1 configuration. So basically, the amount of energy required in this particular process is what I call as ionization energy 1 of nitrogen. The amount of energy required in this particular process is what I call as ionization energy 2 of nitrogen. Right? Similarly, if I talk about oxygen, its outermost configuration is 2p4. So if I want to take one electron out, so it becomes O positive, and this becomes now 2p3 configuration. Right? It becomes 2p3 configuration. The amount of energy required in this process is called as first ionization energy. Now, if I want to define the second ionization energy of oxygen, that means I have to take electron out from this O positive. O positive's outermost configuration is 2p3. So technically, you are taking the electron out from 2p3 configuration now, so that it becomes O di positive. So the amount of energy required in this process, ionization energy 2. Now tell me, compare the second ionization energy of nitrogen and second ionization energy of oxygen. Which one do you think is more? Second ionization energy of nitrogen or the second ionization energy of oxygen? I would say the second ionization energy of oxygen would be more than that of second ionization energy of nitrogen. Why? Because here you are taking electron out from half-filled configuration, more stable configuration. Okay? And to take electron out from more stable configuration, more energy is required. So second ionization energy of oxygen is more than that of second ionization energy of nitrogen. Because when you define second ionization energy of oxygen, you have to take electron out from 2p3 configuration. Just half-filled configuration, 2p3. Here you are taking electron out from 2p2, which is not half-filled, it is partially filled. If I'm clear, tell me once in the chats. Tell me once in the chats. Understand, guys. What if this question is asked? What is this question is asked? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Okay. I have to arrange them on the basis of their what? Ionization energy. So technically, if I see, what should be the logic? This is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Leave neon aside. Okay. So on moving from left to right. On moving from left to right. On moving from left to right. What happens? On moving from left to right, Z effective increases. If Z effective increases on moving from left to right, so ionization energy should increase. So order of ionization energy should be this. This should be the order of ionization energy. This is the expected order. This is the expected order. But is it actual? No, it's not actual. Why is that? Why is that? Have a look. Beryllium, outermost configuration 2s2. Boron, outermost configuration 2s2, 2p1. So if you are defining the ionization energy of beryllium, you are taking the electron out from 2s2. This is 2s2, completely filled. Here it is 2p1. Here you are taking the electron out from this partially filled configuration. To take electron out from completely filled configuration, more energy is required. So I would say, simple. The first ionization energy of which one? The first ionization energy of beryllium would be more than that of boron. Okay? Perfect? Simple. Similarly, if you want to compare oxygen and nitrogen, outermost configuration of nitrogen, 2p3, here 2p4, here 2p4. So 2p3, half-filled configuration. To take electron out from here, more energy is required, right, than that of oxygen. So here also you have to reverse the sign, reverse the order. So oxygen comes first, then comes your nitrogen. Perfect? So this is the actual order. This is the actual order. Am I clear? You can give the answer in terms of penetration power as well, right? S orbitals have got more penetration power. Simple. In case of your beryllium. Perfect, guys? All right. If I'm clear, tell me one more thing in the chats. One thing which is evident. On moving from top to the bottom, what happens to size? On moving from top to the bottom, what happens to size? Size increases. On moving from top to the bottom, size increases. So distance between nucleus and the outermost electron increases. If distance between nucleus and outermost electron increases, force of attraction between them decreases. If force of attraction between them decreases, That means lesser energy is required to take the electron out, right? So what does that mean? That means lesser is the ionization energy. So on moving from top to bottom, ionization energy decreases. Ionization energy decreases down the group. Ionization energy decreases down the group. I hope this is clear. So remember, on moving from top to bottom, ionization energy decreases down the group. Now there are some applications of this ionization energy, guys. Do you know what is a metal? What's a metal? You know, metals, if you would have heard, metals have got the tendency to lose electrons. Correct? Metals have the tendency to lose electrons. Metals have the tendency to lose electrons. Now, which metal can lose electron easily? Which metal can lose electron easily? That metal can lose electron easily in which ionization energy will be less. Because lesser the ionization energy, lesser the energy required to take the electron out. So I would say, in other words, that element can lose the electron easily, which has got lesser ionization energy. And which element loses the electron easily? Metallic element. That's metal basically. So can I say metallic character will be inversely proportional to ionization energy? Can I say metallic character is inversely proportional to ionization energy? Lesser the ionization energy. That means lesser energy is required to take the electron out. That means the electron can be easily lost by the metal. And that metal which loses the electron easily, that metal has got more metallic character. One more important point, remember that. Similarly, if I talk about the non-metallic character, guys, if I talk about the non-metallic character, or leave the non-metallic character aside, talk about the reactivity of metals. See, how do you define reactivity of metals? We say that metal which can lose electron easily, that is more reactive. We say that metal which can lose electron easily, that is more reactive. Correct? That metal which can lose electron easily, that is more reactive. And which metal can lose electron easily? Which has got lower ionization energy. So your reactivity of metal and ionization energy, they'll be again inversely proportional. Just relate things. Lesser the ionization energy. Lesser the ionization energy. That means lesser energy is required to take the electron out. That means technically the metal can lose electron easily. And that metal which can lose electron easily, we say reactivity of that metal is more. Simple. So this is one more important point. Now comes one more application of this ionization energy, guys, from which the question comes. Understand and have a proper eye on the screen. For example, I have got sodium. I am giving sodium its first ionization energy. So it got converted into Na positive. Then I am giving it its second ionization energy. It got converted into Na di positive. Okay. Leave the sodium aside. Here it's Na positive. Here it's Na di positive. What is the oxidation state of sodium here? +1. What is the oxidation state of sodium here? +2. +1 is the lowest oxidation state here. +2 is the highest oxidation state here of sodium. Remember, my dear students, something very, very, very important. What is that? Whenever the difference in the successive ionization energies, ionization energy 1, ionization energy 2, we call them as the successive ionization energies. Whenever the difference between the successive ionization energies of an element is less or equal to, is greater or equal to what? Is greater or equal to 16 electron volt. Remember, at that point of time, lower oxidation state would be more stable. One direct point from which one question, by just closing down your eyes, you can solve. So whenever, this is ionization energy 1, ionization energy 2, we call them as the successive ionization energies. Whenever the difference between the successive ionization energies will be greater or equal to 16 electron volts, at that point of time, the lower oxidation state is considered to be more stable. For example, in case of sodium, the difference between first and the second the difference between the successive ionization energies of sodium is equal to 42.7 electron volt. It is greater than 16 volt. That means the lower oxidation state will be more stable. Lower oxidation state of sodium is +1. So sodium, when in +1 oxidation state, is more stable than the sodium which will be in +2 oxidation state. Okay? I hope it's clear. I hope it's clear. So whenever the difference between the successive ionization energies is greater or equal to 16 electron volts, at that point of time, the lower oxidation state would be considered to be more stable. At that point of time, the lower oxidation state would be considered to be more stable. And remember, if the difference between the two successive ionization energies is less or equal to 11 electron volts, at that point of time, highest oxidation state is considered to be more stable. For example, if I take this particular case, magnesium, if I'm giving first ionization energy to magnesium, it is getting converted into Mg positive. Now, Mg positive, I'm giving it as the second ionization energy. It is getting converted into Mg di positive. Just a second, there is an electricity cut, I think. Just a second, guys. Just a second, people, okay? All right. Okay. How to call the EV? EV is electron volt. So what I was trying to say is, I was telling you, if the difference in the successive ionization energies is less or equal to 11 electron volts, remember at that point of time, higher oxidation state is more stable. For example, magnesium, you gave it the first ionization energy, got converted to Mg positive. Now give it one more ionization energy, got converted to Mg di positive. Now, if the difference between these two values, this value and this value, if the difference between these two values will be less or equal to 11 electron volt, then highest oxidation state is more stable. So first of all, what is the lower oxidation state of magnesium here? +1. What is the higher oxidation state of magnesium here? +2. Right? So in this particular case, higher oxidation state would be considered to be more stable. So that is the reason, since in case of magnesium, the difference between the successive ionization energies here is 7.4 electron volt, which is less than 11 electron volt. So that is the reason why your highest oxidation state, Mg di positive, is more stable. Okay, remember this particular point as well, because this is important. Similarly, we have got its one more application, guys, which you can remember directly. The question can be asked from that. For example, you have got an element whose first ionization energy is 3 electron volt. Second is 10 electron volt. Third is 20 electron volt. Fourth is 200 electron volt. They'll ask us how many valence electrons are there in the element. How many valence electrons are there in the element? Understand what I'm going to say. To take the first electron out, how much energy is required? 3 electron volts. Perfect. Correct. Nice. To take the second electron out, how much energy is required? To take the first electron out, 3 electron volt energy is required. To take the second electron out, 10 electron volt energy is required. To take the third electron out, 20 electron volt is required. To take the fourth electron out, 200 electron volts of energy is required. Means the fourth electron would be closer to the nucleus comparatively. That's why this fourth electron would be experiencing more attraction. More attraction means more energy required, right? So that means this fourth electron will be here in the penultimate shell, right? Fourth electron will be here in the penultimate shell, which you are taking out now. So in the valence shell, there are 3 electrons. So how many valence electrons are there? 3 valence electrons. Did you understand? How do we deal with such kind of the question? Did you understand how to deal with such kind of the question? Everyone, people. Everyone means everyone. Okay, this question we have already solved. This was asked in your NEET 2019. The first ionization energy of lithium, beryllium, boron. And the exception here was, change here was, you had to interchange beryllium and boron, and you were supposed to interchange oxygen and nitrogen. We have solved this question already, so I'm not going to solve it again. You have to tell me the answer of this question. Okay, I'll be waiting for your answers. First ionization energy, second, third, fourth, and fifth. Where is the jump more? Jump is maximum here. So to take first electron out, 7.1 is required. To take second electron out, this much. Third electron out, this much is required. Fourth electron out, this much. Here the jump is maximum. So that means the first 4 electrons, 1, 2, 3, and 4, they should be present in the valence shell. And the fifth electron which you are taking out, it would be present in penultimate shell. That's why the jump here, the ionization energy is more. So I would say there are 4 valence electrons in the atom. And which atom among these has got 4 valence electrons? It's silicon, which has got 4 valence electrons. Understood? These sort of questions can be frequently asked, guys. Okay? Tell me the answer of this question. The second ionization potentials in electron volts of oxygen and fluorine. Second ionization potential of oxygen and fluorine. That means second ionization potential of oxygen. That means you have to take electron out from O positive. The second ionization potential of fluorine. That means you have to take electron out from F positive. What is the configuration of O positive? It was supposed to be 2p4. Now it will going to be 2p3. This was supposed to be 2p5. Now it's going to be 2p4. So technically you are taking electron out from 2p3 configuration. Here you are taking electron out from 2p4 configuration. This is half filled, more stable, more energy required. So second ionization energy of oxygen is more than that of fluorine. Second ionization energy of oxygen is more than that of fluorine, right? So second ionization energy of oxygen is more than that of fluorine. So it's option C. That's the correct answer of this question. Okay. Perfectly done, guys. Is every single thing clear till here? Let me know once in the chats, everyone. I believe these sort of questions you can easily solve from now on. That's my expectation at least. The way I've started, the way I'm teaching you, I believe all of you would be getting all of this. If yes, please and please tell me, all of you, once in the chats, if all these things are super clear to you. Radium is saying how to calculate electron. It will be given to you in the question, like what is the difference in the successive ionization energies. It will be given to you. Ionization energy 1 means the first electron you have to take out. Ionization energy 2 means the second electron you have to take out. Okay? नहीं बासत वैसा कहना सही नहीं रहेगा. So in terms of values आप याद रखो जो मैंने values बताई. Yes, people who are starting from 0, this session is for you as well. Don't worry. Dinner break will be there when we'll be completing this particular chapter, and this chapter will take still some 30 to 40 minutes. Then I'll give you the dinner break. After that, we are going to start the chemical bonding. Yeah. All right, people. All right. आगे स्पैमर सर PW इज द बेस्ट. हाँ भाई बेस्ट होगा, ठीक है, जाओ वहीं जाओ, मेरे को माफ कर दे. So people, is every single thing clear? Is everything clear to everyone? Redox comes in physical chemistry, not in inorganic, okay? Okay, let's move on. Let's move on, guys. Let's talk about electron affinity. This again one important and simple topic. It's not that difficult or something. Not a lot of exceptions are here in this particular one. So let's try to understand. Let's try to understand. Let's try to understand. See, guys. How do we exactly define electron affinity? How do we exactly define electron affinity? My dear students, try to understand one thing. First of all, let's read its definition loud. The amount of energy released when an electron is added to the valence shell of an isolated gaseous atom. For example, This is the nucleus. This is the nucleus, right? And this is the last shell of this atom. This is the last shell of this atom, correct? Which already contains, for example, electron. Which already contains, for example, electron. Now there is one electron coming, which wants to get added to this atom. This is that incoming test electron. I'm calling this as test electron, which wants to be added to this particular atom, which wants to get added to this particular atom. Yeah? Which wants to get added to this particular atom. This is your test electron, which wants to get added to this particular atom. Now, when this electron will be coming closer, first of all, this electron would be experiencing some force of attraction from this nucleus. This nucleus would be trying to attract this particular electron towards itself. So I would say there will be attraction between nucleus and this particular test electron, which wants to get added to the last shell of the atom. Now, between these two, there will be repulsions. Between electron and electron, there will be repulsions. Remember, if attractions are more than repulsions, that means energy will be released. Energy will be released. If attractions are more than that of repulsions, remember, energy is released. Energy is released. Okay? You would have studied, whenever there are attractions, energy is released. Whenever there are attractions, energy is released, right? Now, my dear students, if repulsions are more than that of attractions, energy is absorbed. Remember this particular point first of all. Remember this particular point first of all. If attractions are more than repulsions, electron will get added, energy will be released. Energy will be released, right? Okay? Right? Similarly, if repulsions are more, that means energy is absorbed. Then only the electron will get added. Now, let me tell you, the amount of energy which is released, when an electron is added to the isolated gaseous atom. For example, we have got the atom X. We are giving one electron to it. Let's say attractions are more than that of repulsions. That means this electron will get added here, right? And during the addition of electron, amount of energy will be released. The amount of energy that is released when an extra electron is added to the valence shell of the isolated gaseous atom, that amount of energy released is what you call as electron affinity. That amount of energy released is what you call as electron affinity. And my dear students, remember, generally the first electron addition to the isolated gaseous atom is an exothermic process. So, what does that mean? For example, you have got an atom X, which is in gaseous phase, right? Let's say you want to give it one electron. This you are giving it first electron, right? The first electron addition generally is always exothermic. So when this atom gets converted into X negative, energy will be released here. Right? And the amount of energy released is what we call as electron affinity 1. Now, the X negative which you got here, if you want to give it one more electron, right? Now, this is already X negative. This is electron. There will be repulsions, right? So energy is absorbed in this particular case. Then it will get converted into X negative, which is called as electron affinity 2. So first electron affinity is generally exothermic. Second one would be generally endothermic. Okay, that's what is mentioned over here. Generally, first electron addition to the isolated gaseous atom is exothermic process, right? Except stable electronic configuration. For example, I told you the first electron addition will be exothermic. That means energy will be released. But what if this atom had stable electronic configuration? What if this atom had the stable outermost electronic configuration? Then this atom won't be ready to accept this electron. If it is not ready to accept the electron, that means we have to give this electron to the atom forcibly by supplying energy to the electron. Right? So generally, the first electron affinity is negative, except when the atom has got stable outermost configuration. Right? When the atom has got stable outermost configuration. Perfect. So guys, if I talk about the second electron addition means you are giving electron to X negative, right? This process will be endothermic. That means energy is absorbed during this particular process. Okay, so second ionization energy, that will be endothermic, right? So energy is absorbed in this particular process. Perfect. Now guys, if you look carefully, I had oxygen atom. I'm giving it 1 electron. I had oxygen atom. I'm giving it 1 electron. Just a second. I had oxygen atom. I'm giving it 1 electron. And after giving it 1 electron, it got converted into O negative. Okay. Perfect. So it had 2p4 configuration, which is not half filled or fully filled. So I would say the first ionization energy here would be exothermic. So energy would be released. That's why this sign is coming out to be negative. Because for the exothermic process, delta H is negative. Now this O negative which you are giving it 1 more electron. So it is getting converted into O di-negative. But this process will be endothermic. Energy is absorbed during this process. That's why, since the process is endothermic, so delta H sign is positive. Now, if I add these two reactions, when you add these two reactions, this O negative gets cancelled. So I get O gas, 1 electron, 2 electrons gives O di-negative. O gas plus 2 electrons gives O di-negative. So if they ask you to calculate delta H for this process, for this particular process, what you did, you just added these two reactions and got this. And since you are adding the reactions, you have to add their delta H values as well. So it's going to be minus 141. It's going to be minus 141 plus how much? Plus 744. When you solve this, the value comes out to be 603. Perfect. So sometimes they can give you a question like this. How exactly? They can give you this particular reaction. They'll ask you to calculate delta H for this reaction. And they will give the delta H values for these two reactions. Right? You just have to add these two reactions. You'll get this one. You'll get this one. Right? And since how you got this reaction? By adding these two. You have to add their delta H values simultaneously. You'll get the answer. Right? Am I clear, people? Am I clear? Am I clear, people? Everyone? A lot of spammers have come, guys. It's okay. Let them come. Let them bark. Barking dogs seldom bite. Seldom bite, sorry. You just focus on things, okay? So is it clear, people? Everyone? All clear till here? So sometimes you'll get a question in this particular format. You'll be asked to calculate delta H for this reaction and delta H values for these two reactions will be given. You just have to add these two reactions. You'll be getting this one. And however you get this particular reaction, simple by adding these two, you have to add their delta H values as well. That's it. Okay. Perfect. Let's move on. Now, my dear students, this electron affinity which we are talking about, it is inversely proportional to size. It is inversely proportional to size. Why is that? Why is that? Understand. For example, this is an atom. Its size is this much. This is one more atom. Its size is this much. Now, this is the electron which wants to be added to this atom. This is the electron which wants to be added to this particular atom. This is the nucleus. This is the nucleus. Right? Can I say the distance between nucleus and this test electron which wants to be added? The distance is less. Distance is less is force of attraction means more. If force of attraction is more, that means more energy is released. Right? More the force of attraction, more the energy released. Perfect. So in this particular case, energy released will be more. So I would say lesser the size, more will be the electron affinity. Because what is electron affinity? The amount of energy released when an extra electron is added to the valence shell of the isolate gaseous atom. So remember electron affinity, that's inversely proportional to atomic size. Point number one. Point number one. One more thing, guys. More the effective nuclear charge. More the effective nuclear charge. So for example, you have got atoms. You have got atoms. This atom 1, this atom number 2. Okay. This has got more effective nuclear charge. This has got comparatively less effective nuclear charge. Now, this is the electron which wants to be added to this atom. This is the electron which wants to be added to this atom. This electron has got more effective nuclear charge. That means this electron has got more attractive power. It has got more attracting power. That atom which has got more effective nuclear charge has got more attracting power, right? And more the attraction, more the energy released, right? So remember, more the effective nuclear charge, more is the energy released. That means more is the electron affinity. Correct? And already you know, effective nuclear charge is directly proportional to positive charge, inversely proportional to negative charge. So this is one more important thing which you need to know, guys. And after knowing this particular point, let's try to understand few more things. Electron affinity of elements which have got fully filled or half filled configuration will be less, which I discussed with you already. For example, you have got an atom A which has got half filled configuration. You have got one more atom B which has got partially filled, configuration. Now you are giving one electron to this, even you are giving one electron to this. Since it already has half filled configuration, or let's say it has got fully filled. It can be anything, half filled or fully filled. So it has got already the stable outermost configuration. So why would it want to accept one electron? No. Why would it want to accept one electron? No, because it already has fully filled configuration. It already has half filled configuration. It already has the stable outermost configuration. Do you understand? Perfect. But this one which has partially filled, which has not fully filled or half filled, it can take the electron easily. Okay. So my point is, electron affinity of elements having fully filled or half filled configuration is less, or you can say 0. So for these elements, electron gain enthalpy will be positive. Because they do not want this electron to be accepted. They don't want to add this electron because they already have fully filled configuration. But if you still want this electron to be added to them, then you have to supply energy. It becomes endothermic. If it becomes endothermic, so delta H value will be positive. Simple. Delta H value will be positive. So remember this particular point as well. And people, at the same time, if you look at the general trend on moving from left to right, effective nuclear charge generally increases. And if effective nuclear charge increases, that means attractive power increases. If attractive power increases, that means energy released would be more. That means electron affinity would be more. So in short, from left to right, electron affinity increases. From top to bottom, electron affinity would automatically decrease. Okay, this is one more point which you need to remember directly because this is important. Now the point is, among fluorine and chlorine, this is the first exception which we have, which frequently comes in your exam. Among fluorine and chlorine, which one has more electron affinity, or you can say which one has got more electron gain enthalpy? As I told you, if I talk about fluorine, chlorine, bromine, iodine, astatine, they belong to same group. Down the group, electron affinity decreases. We saw it few minutes back only. If down the group electron affinity decreases, so I would say electron affinity of chlorine should be less than that of fluorine. Electron affinity of chlorine should be less than that of fluorine. But in reality, electron affinity of chlorine is more than that of fluorine. This is the actual order. This was the expected order. Why is that? What is happening here? Why is that? Since, my dear students, if you talk about fluorine and chlorine, fluorine has got, if you talk about fluorine and chlorine, fluorine has got lesser size. If fluorine has got lesser size, you are giving one electron to fluorine, right? It has got lesser size. And since there are lone pairs as well, there are electron pairs as well on fluorine, correct? So it has got more charge density. Lesser size, more charge density. So more repulsions will be experienced by this test electron, which wants to be added, which wants to get added. Again, let me repeat the same thing. Fluorine and chlorine, both have got same electrons, same outermost electrons, right? But the size of fluorine is less. So electron density here is more in fluorine. So the incoming electron will experience more repulsions here. So this fluorine does not want this electron to be added to it. Okay? Perfect. So that is the reason why fluorine has got less electron affinity than that of chlorine, because of the smaller size of fluorine and more electron density on fluorine. The test electron experiences more repulsions, due to which the test electron does not want to get, due to which this fluorine does not want this extra electron to be added. Okay? Same goes for, guys, same is the logic for oxygen and sulfur as well. If you talk about oxygen and sulfur, so technically they are from same group. Down the group, what happens? Down the group, electron affinity decreases. Perfect. So Down the group, electron affinity decreases. So sulfur should have less electron affinity than oxygen. Sulfur should have less electron affinity than oxygen. But in reality, oxygen has got more. In reality, sulfur has got more electron affinity than oxygen. This was the expected order. This is the actual order. Why is that? Why is that? Because in case of oxygen has got smaller size, more electron density, less tendency to accept the incoming electron. Right? Remember this particular point as well. Remember this particular point as well. It can be asked. Or they can show you, they can ask you the direct trends. They can ask you the direct trends here. For example, fluorine, chlorine, bromine, iodine, right? Give the order of electron affinity. This is the order, right? Electron affinity of chlorine is more than of fluorine. Similarly, electron affinity of sulfur is more than of oxygen. So anything can be asked out of these trends. Similarly, silicon has got more electron affinity than carbon. Perfect. So I believe these things are clear to you and you can solve these sort of questions easily. Okay, one more point from which a question comes. What is that? For example, guys, there is a statement which I mentioned. Electron affinity of a neutral atom is equal to the ionization energy of its anion. What does it mean? This is important. Why is it important? For example, you have got neutral atom X. You are giving one electron to it. It got converted into what? X negative gas. Now the amount of energy released in this particular process is called as electron affinity. This is the electron affinity of what? Electron affinity of X gas. Electron affinity of X gas, right? Now this X negative which you have here, if you want to take one electron out from it, it gets converted into X gas plus one electron, right? The amount of energy which is required to take the electron out is what I'll be calling as ionization energy of what? Of this X negative gas. So technically both these processes are same but in reverse manner. Technically both these processes are same but reverse. Here energy is released, here energy will be absorbed, right? So technically both the processes are same but in reverse manner. So I can say electron affinity of X gas would be equal to minus times the ionization energy of this X negative. It is just their signs would be different. This is basically exothermic. If its sign is negative, this is supposed to be endothermic because amount of energy which is required to take the electron out. So it will be endothermic. Delta should be positive. Perfect. So sign wise it will be different. Magnitude wise it's going to be same. So that's why I mentioned this statement. Electron affinity of the neutral atom. Electron affinity of the neutral atom is magnitude wise equal to the ionization energy of its anion. Okay. This is also one very, very, very important point which you should know. Yes. I believe this is clear. Now from this particular point, a question was asked long back. Let me show you that question. What is the value of electron gain enthalpy of Na positive if ionization energy of sodium is given? So that means when sodium is in gaseous state, right? When you take one electron out from it, it gets converted into Na positive gas. The amount of energy required in this particular process called as ionization energy 1 of sodium, and this much is given to me as 5 electron volts. Now what do I need? What is the value of electron gain enthalpy of Na positive? If I want to define the electron gain enthalpy of Na positive, that means the amount of energy released when one electron is added to this, it gets converted into Na gas, right? Can I say this reaction is just reverse of it? If it is reverse of it, the value here would be simple. You just have to change the sign. It will be minus 5 electron volt. But this particular minus 5 electron volt, I'll be calling as what? This would be called as electron gain enthalpy. This would be called as electron gain enthalpy of what? Of Na positive. Na positive here. Perfect. Understood? Similar sort of question that I gave you one concept a few minutes back, and this is a question on it. I hope this is clear. And this is the question which was asked, 2-3 years back in your JEE Mains examination. Since both the processes are same, it is just one would be exothermic, one would be endothermic. So one is going to be positive in terms of sign, one is going to be negative in terms of sign. That's it. All right. Tell me the answer of this particular question quickly. Among halogens, the correct order of amount of energy released in electron gain enthalpy. You have to give the order wherein order of energy released. Order of energy released. See, down the group, in case of halogens, what should happen? Energy released should decrease. Okay, it should decrease. So chlorine should have lesser electron affinity than that of fluorine. But chlorine has more than that of fluorine. We know that already. Chlorine has more than that of fluorine. Yes? So what is the order? Guys, this sort of equation you should be in a position to solve easily. This is the order. We checked it few minutes back only. We checked it few minutes back only. Now the last point, and very simple, it is not going to take more than 10 minutes. Okay? What is that? That is electronegativity. How do we define electronegativity? This is the last point, last term of this particular chapter. Then we'll be moving on. I'll give you the dinner break and then we'll start the chemical bonding also. Okay? So first of all, how do we define electronegativity? Electronegativity is simply defined as the tendency of the atom. The tendency of the atom to attract the bonded pair of electron, shared pair of electron towards itself. For example, there's a covalent bond between A and B. There's a covalent bond between A and B. Covalent bond means mutual sharing of electrons. Covalent bond means mutual sharing of electrons. So this bond got formed by one electron pair. So this electron pair is technically supposed to be at the center because it's a covalent bond. Mutual sharing of electrons is happening. But for example, I'm assuming B is more electronegative than A. What does that mean? That means B has got more tendency to attract this bonded pair of electron towards itself, due to which electron density towards B will increase. Do you see? Electron density towards B has increased. Electron density towards B has increased. And increase in the electron density I represent with delta negative. Decrease in electron density I represent with delta positive. So can I say, due to electronegativity difference, polarity got induced in this bond? Polarity got induced in this bond? Yes? Am I clear? Perfect, guys? Perfect. So electronegativity is nothing. It is the tendency of the atom to attract the bonded pair of electron, shared pair of electron towards itself. Right? Due to which polarity got induced in a covalent bond. Simple. Due to which this bond got polar character. Due to which the bond gets the polar character. For example, talk about HCl. HCl. If you talk about HCl, this is your HCl molecule. Chlorine is more electronegative than hydrogen. If chlorine is more electronegative than hydrogen, that means chlorine has got more tendency to attract the bonded pair towards itself, due to which electron density towards chlorine will increase. And that increase in electron density towards chlorine is represented by delta negative. So this will be automatically delta positive. So again, this bond became polar due to the electronegativity difference. Due to the electronegativity difference. And let me tell you, electronegativity is basically inversely proportional to size. Lesser the size of the atom. This is the first factor on which electronegativity depends. Okay? This is the first factor on which electronegativity depends. Electronegativity depends upon the size. Lesser the size of the atom, more will be the tendency of the atom to attract the bonded pair towards itself. Okay? Attract the bonded pair towards itself. Now tell me one thing. On moving from left to right in the periodic table, what happens to size generally? Size decreases generally. So electronegativity on moving from left to right should increase, right? On moving from top to bottom, what happens to size? Size decreases, right? So what will happen to electronegativity? It will increase. Sorry, it will, size decreases, wait, I give you the wrong thing here. On moving from top to the bottom, size increases. If size increases, that means electronegativity should decrease. So fluorine, chlorine, bromine, iodine, they belong to same group. Down the group, size increases. If size increases, so electronegativity should decrease. So fluorine is more electronegative than chlorine, than bromine, than iodine, than astatine. Okay? Now, this electronegativity, it depends on the effective nuclear charge as well. Tell me one thing. More the effective nuclear charge, more the effective nuclear charge, more the effective nuclear charge of the atom. Can I say more is the pulling power of the atom? If more is the pulling power of the atom, that means more is the tendency of the atom to attract the bonded pair of atom towards itself. Right? So remember, more the positive charge on the atom, more the effective nuclear charge. More the effective nuclear charge of the atom, more is the pulling power of the atom. More the pulling power of the atom, more is the tendency of the atom to attract the shared pair, bonded pair of atom towards itself. As simple as that. So you have got Mn di positive, Mn plus 4, Mn plus 7. Here the positive charge is more. Positive charge more means effective nuclear charge more. Effective nuclear charge more means pulling power more. Pulling power more means more tendency to attract the bonded pair of electron towards itself, due to which its electronegativity would be maximum. Similarly, talk about this one. More the positive charge, more the Z effective, more the electronegativity. This is one more point. I mean, these are questions basically which can be asked. My dear students, this electronegativity, it depends on percentage S character as well. Well, that's something I'll be teaching you in chemical bonding chapter after some time. Just you need to remember one thing. In case of sp hybridization, S character is 50%. In case of sp2, S character is going to be 1 divided by 3, that is 33%. In case of sp3 hybridization, S character 1 divided by 4, that is 25%. Remember directly, more is the S character, more is the electronegativity. So tell me just one thing. How many bonds this carbon is forming? 1, 2, 3, 4. 4 sigma bonds. 4 sigma bonds means its hybridization will be sp3. Tell me about this one. How many sigma bonds it's forming? 1, 2, 3. So it's sp2 hybridized. How many sigma bonds this carbon is forming? 1, 2. So it's sp hybridized. So in case of sp3, sp2 and sp, where is the S character more? S character is more than sp. More the S character, more the electronegativity. In short, remember it like this. Okay? Remember it like this. Okay, guys? Now, can we relate electronegativity with metallic and non-metallic character? Can we relate electronegativity with metallic and non-metallic character? First of all, that metal has got more metallic character, which has got tendency to lose electrons. So technically, I would say that metal will have more metallic character, which would have lesser electronegativity. I'm talking about the metallic character. Okay, talk in terms of non-metallic character. First. See, a non-metal has got the tendency to gain electrons. Now, that non-metal will gain electron easily, which has got more pulling power. More pulling power means more electronegativity. So technically, non-metallic character is basically directly proportional to electronegativity. More the electronegativity of an element, more is the tendency of the element to accept the electrons, right? Because more is the pulling power of the element. So you can relate these two things, non-metallic character and electronegativity, they'll be directly proportional already. Okay? They'll be already directly proportional. And similarly, if I talk about the metals, so metallic character, this was the non-metallic character. If I talk about the metallic character is going to be directly proportional or inversely? It is going to be inversely proportional to electronegativity. Lesser the electronegativity, more is going to be the tendency to lose electrons. That means more is the metallic character. This particular statement also you should remember. Now remember, there are few applications, more applications of this electronegativity. Sometimes you will get the question on the basis of bond energy. And remember, bond energy is nothing but it's directly proportional to electronegativity difference. Bond energy is direct. What is bond energy first of all? The amount of energy required to break this, required to break this bond, right? If I say in short, if I not give you the actual definition of bond energy, I hope you know. The amount of energy required to break 1 mole of bonds. But leave that aside, I'm not going there. I'm not talking about the thermodynamics perspective right now. See, just remember it like this. The amount of energy required to break this bond, break this bond, break this bond, break this bond. You call that as bond energy? In short, okay, just to solve the questions like this. So first of all, more the electronegativity difference between the atoms, more is going to be the energy required to break the bond. Okay, so short man, you can say more is the bond energy. So in short, one clear-cut statement will solve all these questions. Your bond energy, that is directly proportional to electronegativity difference between the atoms. I believe this is clear. And if this is clear, then one more thing. Order of acidic strength. That is again directly proportional to what? That's again directly proportional to what? Tell me. Well, the answer is already mentioned. In case of your HF, HCl, HBr, HI, which one is going to be more stable? I mean, which one is going to be more acidic? How do you check it? It's going to be HI. That's going to be more acidic. Why? See, electronegativity difference here is more. That means more bond energy will be there. If more is the bond energy, that means more energy is required to break this bond. So technically less energy is required to break this bond. So from HI can give away H positive easily. If HI gives away H positive easily, that acid which gives H positive easily is going to be stronger acid. So this is technically your stronger acid. Or if you have studied GOC, you can give the answer in terms of conjugate base as well. I negative is more stable conjugate base. Okay, that's why its acid is more stronger. So remember this. Or whatever I'm telling you right now, you can remember it in this manner as well. See, here the electronegativity difference is less. So bond energy here is less. So this HI will give away H positive easily. If it gives away H positive easily, that means it is going to be more acidic. Okay? Perfect. Similarly, one more thing which you can remember. If you talk about the nature of oxides, of all these elements, oxides of lithium, beryllium, boron, carbon, similarly sodium, magnesium, aluminum, two things you have to remember. Along the period, the acidic nature of the oxides increases. Why? Because the electronegativities increase on moving from left to right. Similarly, down the group, basic nature of the oxides increases. Why? Because the electronegativity decreases. So you can remember these 2 points also directly. Perfect. So along the period, if you talk about the oxides of these elements, along the period, electronegativity increases. So acidic nature of the oxides increases. Down the group, electronegativity decreases. So you can remember acidic nature of the oxides decreases or basic nature of the oxides increases. This is again one more thing, my dear students, which you need to know. Okay, which you need to know. So sometimes questions will be asked from these as well. They'll be giving you oxides of these elements, right? Perfect. So on moving from left to right, electronegativity increases, the acidic nature of the oxides increases. On moving down the group, electronegativity decreases, so acidic nature of the oxides decreases, or you can say basic nature of the oxides increases. This is one more thing which you can take a note of. So for example, this is the oxide of boron, this is the oxide of carbon, this is the oxide of nitrogen. Which one is more acidic over here? Now boron, carbon, nitrogen. On moving from left to right, boron, carbon, nitrogen, electronegativity increases. So nitrogen is more electronegative, then carbon, then boron. So more the electronegativity of the atom here, more acidic is going to be its oxide. So N2O5 will be more acidic than that of carbon dioxide, than that of B2O3. Similarly, these are some more acids over here. Perfect. Their acidic strength also you can check. Similarly, same goes for this one. This is HClO4, this is HBrO4, this is HiO4. Here the central atom is chlorine, here the central atom is bromine, here the central atom is iodine. Chlorine is more electronegative, then bromine, then iodine. More electronegative means more is going to be its acidic nature, right? Same is going to be this one as well. Sulfur is more electronegative than Se, then Te. So more electronegative means more is going to be, more acidic it's going to be, right? And guys, this is one memory-based slide. Questions have been frequently asked from this particular slide. I would want every one of you to remember this particular slide as well. Okay? Your metal oxides are generally basic in nature. Your non-metal oxides are generally acidic in nature, right? Sometimes they'll ask you which of the following is a neutral oxide. The most common examples of the neutral oxide is N2O, NO, H2O, and CO. And sometimes they'll ask you which of the following is the amphoteric oxide. And the examples of the amphoteric oxides are these, right? The oxides of all your oxides and hydroxides of lead, zinc, beryllium, aluminum, gallium, tin, chromium tripositive, all their oxides as well as hydroxides are amphoteric in nature. Similarly, As2S3, As2O3, V2O5, Sb2O3, these are again your amphoteric oxides. So this is the memory-based slide, my dear students, which, right, you need to remember because questions have been asked from this particular slide as well, that too frequently. I hope I'm clear with this, and let me tell you, with this we are done with. Okay, tell me the answer of this question. As you can see, NEET 2018 the question was asked. Which of the following oxide is most acidic? Tell me, which of the following is most acidic? Beryllium oxide, magnesium oxide, barium oxide, calcium oxide. So first of all, beryllium, magnesium, calcium, barium. Beryllium, magnesium, calcium, barium. Down the group, electronegativity decreases. If electronegativity decreases, that means the acidic strength of their oxides will decrease. Decreases. So which oxide is going to be maximum acidic? It's going to be beryllium oxide, which will be maximum acidic among all. Perfect. From the table which I gave you a few minutes back. So with this, we are done with chemical bond. We are done with periodic classification, right? So let me write it over here. Periodic classification over. Periodic classification over. So tell me in the chats if all the things are like very, very, very clear to you. Chemical bonding. I'm giving you the dinner break. So we'll start exactly at 8:30 p.m. We'll start exactly at 8:30 p.m. Okay? So this is your dinner break basically. But I would want every one of you to be back because chemical bonding is again going to take some 4 to 5 hours and we'll be done with your class 11th inorganic chemistry. Perfect. Perfect, people. Perfect. Why fluorine has less electron gain enthalpy than chlorine? I gave you the answer already. Check the session. Because of the smaller size of fluorine and more electron density of fluorine, the electron gain enthalpy of fluorine will be less than that of chlorine. Okay? P block will be done in class 12th inorganic, not here. Class 12th inorganic. That's P block. Chalo. Have your dinner, but come back exactly at 8:30, guys. I'll be waiting for you. What's up, guys? What's up? Are you done? Are you all back? Are you all back? Are you all back? Welcome back, welcome back, welcome back. Are you done with your dinner? आप कहाँ थे सर? मैं खाना खा रहा था. Are you done with your dinner? Yes, even I'm done. So tell me, guys, till now we are done with the periodic classification, right? So tell me, is every single thing clear? Is every single thing clear? I mean, whatever things we have discussed till now, are all the things like super clear to everyone? I just want to know that. Then we'll be starting the next chapter. Tell me quickly. Tell me quickly, guys. Yeah? Perfect. Perfect, guys. Perfect, 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 perfect. Let's move on then. Let's start the chapter chemical bonding, right? So first of all, let me tell you from which all topics questions can be asked in chemical bonding. My dear students, the first topic is going to be how to draw the Lewis structures. Question can be asked from that. Question can be asked from formal charge. Question can be asked from Fajan's rules. Question can be asked from dipole moment. Question can be asked from everything. VBT, valence bond theory. Question can be asked from VSEPR, valence shell electron pair repulsion theory. Question can be asked from hybridization. Question can be asked from molecular orbital theory. Question can be asked from bond angle. Question can be asked from this hydrogen bond, right? So entire chemical bonding chapter is very, very, very important. You cannot skip a single topic from this particular chapter. Let me tell you that very honestly. You cannot skip a single topic from this particular chapter. And from this particular chapter, minimum 4 questions will be asked in the NEET examination. Okay, minimum 4 questions will be asked. And your organic chemistry is incomplete without this particular chapter. I hope you know that. I hope you know that. So let's go on. Let's discuss your chemical bonding from the topic how to draw the Lewis structures of different molecules. How do we draw the structures of different molecules as per Lewis theory is concerned? Okay. Guys, have a proper eye on the screen because whatever things I'm going to tell you now, I'll be utilizing all these things in this particular chapter, right? So try to understand very carefully and properly what I'll be telling you now. So first of all, how do we draw the structures of some simple molecules as per Lewis theory is concerned? As per Lewis theory is concerned. Try to understand. For example, I have to draw the structure of this carbon monoxide, CO. How do I draw its structure? First of all, if I ask you, how many valence electrons carbon has? Your answer will be 4. How many valence electrons oxygen has? Your answer will be 6. Oxygen has got 6 valence electrons. Now, if I add them up, 6 plus 4 makes it 10. So, in total, there are 10 valence electrons in case of CO. In case of CO, there are 10 valence electrons. My dear students, 10 valence electrons means 5 valence electron pairs, because 1 electron pair means 2 electrons. 1 electron pair means 2 electrons. So 10 valence electrons means 5 valence electron pairs. Okay. Now what do? I have to draw the structure of carbon monoxide. This is carbon. This is oxygen. I'll put a single bond first of all. I'll put a single bond. Single bond means 1 electron pair. Single bond means 1 electron pair. A single bond consists of 2 electrons. 2 electrons means 1 electron pair. So basically, I had some 5 valence electron pairs, out of which I've used 1 valence electron pair. So there are still 4 valence electron pairs. Now, which element is more electronegative among the two? Oxygen. So do one thing. Start filling the octet of oxygen. I'll say 2, 4, 6, and these two are already 8. So octet of this oxygen is complete. I had 5 valence electron pairs. Out of 5 valence electron pairs, how many I have used? 1, 2, 3, and 4. 4 I have used. 1 is still left. So 1 valence electron pair I'll keep on carbon. So I had 5 valence electron pairs. I've utilized all 5. I've utilized all 5. Now, no doubt octet of this oxygen is complete. But is the octet of carbon complete? No way. Why is that? 1, 2, and 3, 4. Since it's a covalent bond, this covalent bond is mutually shared by carbon as well as oxygen. So this carbon, 1, 2, 3, 4. Only 4 valence electron pairs. How many it needs? 8. So what do? From oxygen, remove 1 of the electron pair and put a bond instead. From this oxygen, remove 1 more electron pair and put a bond instead. Now check the octet of both the atoms. Octet of oxygen, 1, 2, 3, 4, 5, 6, 7, 8. Complete. Octet of this carbon, 1, 2, 3, 4, 5, 6, 7, 8. Complete. So octet of both the atoms is complete. This is the structure of your carbon monoxide. I believe you got to know how do we draw the structure. Now, do you see any charge on carbon? I don't see any charge on carbon. I don't see any charge on oxygen. Now let's get to know in reality whether there is any charge on carbon or any charge on oxygen. How do we check that? So basically, I want to calculate formal charge on carbon. How do we calculate formal charge? How do we calculate formal charge? Try to understand. My dear students, when carbon is isolated in non-bonded form, how many valence electrons carbon has? 4. In non-bonded state, carbon has 4 valence electrons. Minus. How many valence electrons this carbon has right now in bonded state? 1, 2. Okay. Now. From this bond, just consider 1 electron. From this bond, consider 1 electron. From this bond, consider 1 electron. So 1, 2, 3, 4, 5. So it has got 5 valence electrons in bonded state right now. So 4 in non-bonded, 5 in bonded. So the value comes out to be -1. So technically there is a charge of -1 on carbon, which I call as the formal charge. Okay. Similarly, my dear students, if I need to calculate the formal charge on oxygen. When oxygen is in non-bonded state, isolated, it has got 6 valence electrons. Minus. How many it has right now? 1, 2, 3, 4, 5. So 6 minus 5 comes out to be +1. So the formal charge on this particular oxygen is +1. So you got to know how do we draw its structure. You got to know how do we draw the formal charge on different atoms. Right? I believe it's clear. Let me take a few more examples. With that, things will be more clear to you. For example, I'm taking the case of NO2 negative. Try to understand, people, what I'm going to say. My first thing is calculate the valence electrons in total. Nitrogen has got how many valence electrons? 5 plus. Oxygen has got 6 valence electrons. And there are 2 oxygen atoms, so multiplied by 2. There's a negative charge as well. So you have to add that negative charge. If there was positive charge, you are supposed to subtract that positive charge. Negative charge you have to add, positive charge you have to subtract. Now people, this value comes out to be 5 plus 12 plus 1. Comes out to be how much? 13 plus 5 is 18. So there are in total 18 valence electrons. That means how many valence electron pairs? 18 valence electrons means 9 valence electron pairs. 9 valence electron pairs. Now, which one is less electronegative among the two? Nitrogen. I'm going to keep this as the central atom. Okay, central atom. Oxygen and oxygen. NO2. Now do one thing, put a single bond here also, here also. So out of 9 valence electron pairs, I've used 1, 2. 2 valence electron pairs I've used. So how many I'm left with? I'm left with 7 valence electron pairs. Now start filling the octet of more electronegative element first. So which one is more electronegative among all? Oxygen. So start filling of this oxygen first. Start filling octet of this oxygen first. 1, 2, 3, 4, 5, 6, 7, 8. Octet of this oxygen is complete. What about this one? 1, 2, 3, 4, 5, 6, 7, 8. It's complete. How many valence electron pairs I had in total? 9. Out of 9, how many I've used? 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electron pairs I've used. There is 1 valence electron pair still left, which will be there on nitrogen. Now, my dear students, octet of this oxygen is complete. 2, 4, 6, 8. 2, 4, 6, 8. But is the octet of nitrogen complete? Check it out. 1, 2, 3, 4, 5, 6. No, it's not complete. So do one thing. Select any of the oxygen atoms of your choice. Remove electron pair and just put a double bond here. Now you can check the octet of all the atoms is complete. The octet of all the atoms is complete. Okay. Let me call this as atom number 1. Let me call this as atom number 2. Let me call this as atom number 3. So let's calculate the formal charge on atom number 1. If you talk about atom number 1, that's oxygen. Oxygen in non-bonded state has got 6 valence electrons minus. Right now, how many it has? 1, 2, 3, 4, 5, 6, and 7. So 6 minus 7 comes out to be minus 1. So I would say there's a charge minus 1 on this particular oxygen. What about this particular oxygen? I need to calculate formal charge on second atom. It's going to be oxygen in non-bonded state has 6 valence electrons minus. Right now, how many it has? 1, 2, 3, 4, 5, and 6. So 6 minus 6 comes out to be 0. So there is no formal charge on this oxygen. What about the formal charge on atom number 3? That means your nitrogen. Nitrogen in non-bonded state has got 5 valence electrons minus. How many it has right now? 1, 2, 3, 4, 5. So 5 minus 5 is 0. So the formal charge on nitrogen also is 0. I believe this is clear. I believe this is clear to everyone, people. Let me know quickly in the chats if all the things are clear. Yeah. Let me take a few more examples with that things will be more clear to you. For example, I have got, let's say, Cn negative. I've got Cn negative. I've got Cn negative. I want to draw its structure. How exactly? Carbon. How many valence electrons it has? 4. Nitrogen. How many valence electrons it has? 5. There's a negative charge. So add 1. So 5 plus 1, 6, 6, 4, 10. So there are total 10 valence electrons. That means how many valence electron pairs are there? That means there will be 5 valence electron pairs. Right? Now, put a single bond between carbon and nitrogen first. Done. Now start filling the octet of more electronegative element. That is nitrogen. 1, 2, 3, 4, 5, 6, 7, 8. Done. I had 5 valence electron pairs, out of which I have used 1, 2, 3, 4, and 5. 5 valence electron pairs I have used. Okay. Now, no doubt octet of this nitrogen is complete. But is the octet of carbon complete? No. Why? 1, 2, 3, 4. Only 4. Now do one thing. Remove one of the electron pair from nitrogen and put a bond instead. Remove one more electron pair from this nitrogen. Put a bond instead. Now the octet of both atoms is complete. Octet of this carbon, 1, 2, 3, 4, 5, 6, 7, 8. Octet of this nitrogen, 1, 2, 3, 4, 5, 6, 7, 8. Right? Now, my dear students, I'm asking you to calculate formal charge on carbon. Formal charge on carbon will be equal. In non-bonded state, carbon has got 4 valence electrons minus. In bonded state, how many it has? 1, 2, 3, 4, 5. So the value comes out to be minus 1. Right? Formal charge of nitrogen will be equal. Nitrogen in non-bonded state, 5 valence electrons. Minus, how many it has right now? 1, 2, 3, 4, 5. So 5 minus 5 is 0. So you calculate the formal charge on both the atoms. Got it? I believe this is clear to everyone. I believe this is like super clear to everyone. If yes, let me know once in the chats quickly. Quickly, people, quickly. Can you make the structure of this molecule on your own? I mean, you should be able to. You should be able to do that. For example, you have got O2 di-negative. Oxygen. How many valence electrons oxygen has? 6. Multiplied by 2 atoms. There is di-negative charge. So add this 2 negative here. So 6 to 12, 12 to 14. So in total, there are 14 valence electrons. So how many valence electron pairs are there? 7 valence electron pairs. Now it is O2. This is oxygen. Oxygen. Put a single bond. So out of 7 valence electron pairs, I've used 1. Okay. Now start filling the octet of any of the oxygen. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now check once. How many valence electron pairs I had? 7. Out of 7, how many we have used? 1, 2, 3, 4, 5, 6, and 7. I have utilized all the 7 valence electron pairs. Now tell me one thing. Can we calculate the formal charge on both the atoms? Yes. If I want to calculate formal charge on this oxygen, it's going to be oxygen in non-bonded state has got 6 valence electrons minus how many it has right now? 1, 2, 3, 4, 5, 6, and 1 here, 7. So 6 minus 7 is minus 1. What about the formal charge on this particular oxygen? It is going to be in non-bonded state, oxygen has got 6 valence electrons minus right now 1, 2, 3, 4, 5, 6. So 6 minus 6, sorry, 1, 2, 3, 4, 5, 6, and this is 1, 7. So 6 minus 7 is minus 1. So formal charge on both the oxygen atoms is minus 1 respectively. Is it clear? Is it clear, people? Everyone in the chats, quickly. Quickly, everyone. For example, draw the structure of CO3 dinegative. You can do it easily. How exactly? First of all, calculate the valence electrons. If I talk about carbon, carbon has got 4 valence electrons. Oxygen has got 6 valence electrons multiplied by 3 oxygen atoms. There is dinegative, so add this to negative charge. So this will be 4 plus 6, 3, 18 plus 2. The value comes out to be 18 plus 2 is 20, 20 plus 4 is 24. So in total 24 valence electrons. So that means how many valence electron pairs? 12 valence electron pairs. 12 valence electron pairs means 24 electrons. Now, less electronegative is always your central atom. So this is carbon, this is oxygen, this is oxygen, this is oxygen. So there are 3 oxygen atoms. So carbon and 3 oxygen atoms. Now, put a single bond everywhere. Done. Now start filling the octet of more electronegative element, which is more electronegative oxygen. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I had total 12 valence electron pairs, out of which how many I have used? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've utilized all the 12 valence electron pairs. Now, octet of all the oxygens are complete, but is the octet of carbon complete? Check the octet of carbon. 2, 4, 6. Only 6 electrons. Now select any of the oxygen, remove electron pair, and instead of that, put a bond. Now check the octet of all the atoms. Octet of all the atoms is complete. Now you can easily check the formal charge on this oxygen. In non-bonded state, 6 valence electrons minus right now 1, 2, 3, 4, 5, 6, and 1. That is 7. So its formal charge is minus 1. What about this one? In non-bonded state, oxygen has 6 valence electrons minus 1, 2, 3, 4, 5, and 6. So 6 minus 6 is 0. What about this oxygen? In non-bonded state, oxygen has 6 valence electrons minus how many it has right now? 1, 2, 3, 4, 5, 6, and 7. So 6 minus 7 is minus 1, right? So this is how you draw the structures of simple molecules. At the same time, this is how you calculate the formal charge on different atoms as well. I believe this is clear to everyone. If yes, let me know once in the chats quick. Right, people? Perfectly done. Is it clear? Is it clear? Is it clear? Everyone in the chats. All right. So I believe you got to know how to draw the structures of the molecules and how do we exactly calculate the formal charges as well. Now, my dear students, I'm going to talk about one more topic here first. What is that? That is your dipole moment. Let's talk about the topic dipole moment first. What's the dipole moment exactly? What's the dipole moment exactly? What all things we have to remember about dipole moment? And what kind of questions can be framed out of it? Let's talk about that. First of all, my dear students, whenever you have two equal and opposite charges, whenever you have two equal and opposite charges separated by certain distance, whenever you have two equal and opposite charges separated by certain distance, separated by certain distance. Let me tell you, the system of opposite charges separated by certain distance, the system of charges is what you call as dipole. The system of charges is what you call as dipole. Whenever you have two equal and opposite charges separated by certain distance, the system of opposite charges separated by certain distance is what I call as dipole. And my dear students, for a dipole, we define a term called as dipole moment. For a dipole, we define a term called as dipole moment, which is represented by mu. Okay? And this dipole moment which we are going to talk about, this dipole moment, it is defined as the charge present on the charge, anyone, whichever one you want to take, multiplied by the distance between the charges. Okay? The charge multiplied by distance. The product of charge and distance is what we call as dipole moment. Product of charge and distance is what I call as dipole moment. And this dipole moment which we are going to talk about, this dipole moment, it is a vector quantity. It is a vector quantity. If it is a vector quantity, that means it will be having direction as well. It will be having direction as well. And let me tell you, the direction of dipole moment, is always taken from positive to negative in chemistry. Positive to negative. Or I can say the direction of dipole moment is taken from less electronegative to more electronegative. Less electronegative to more electronegative. Well, if I talk about this dipole moment, which is a vector quantity, I would say the unit of dipole moment, the SI unit of dipole moment is d by. The SI unit of dipole moment is nothing but called as d by. It is the SI unit of dipole moment. Now, my dear students, one more thing. Before making you understand all of this in detail, one more thing. For example, I'm taking a molecule HCl. This is a molecule I've taken, HCl. Now, you already know chlorine is more electronegative than hydrogen. If chlorine is more electronegative than hydrogen, I would say chlorine has more tendency to attract the bonded pair of electron towards itself, due to which chlorine gets delta negative and this hydrogen gets delta positive. If chlorine got delta negative, hydrogen got delta positive, can I say I have got equal and opposite charges separated by certain distance? So this system of charges I'll be calling as dipole. For a dipole, there will be its direction. I mean, for a dipole, we define a dipole moment. We define a term called as dipole moment, right? We define a term called as dipole moment. And the direction of dipole moment is from positive to negative, right? So this is the direction of dipole moment in the molecule HCl. I believe this is clear. Okay. Now, my dear students, one more thing, which I want to mention over here. Let me tell you, lone pair also contributes. Lone pair also contributes towards the dipole moment. Lone pair also contributes towards the dipole moment. Lone pair also contributes towards the dipole moment. And the direction is always towards the lone pair. The direction is always towards the lone pair. For example, if I take the molecule NH3, I am taking the molecule NH3. This is your NH3 molecule. Since nitrogen, it has got one lone pair as well. You must be knowing nitrogen has got a lone pair. Now, my dear students, first of all, try to understand. This bond between nitrogen and hydrogen. Hydrogen is less electronegative, nitrogen is more. The direction of moment is from less electronegative to more electronegative. The direction of moment is from less to more. The direction of moment is from less electronegative to more electronegative. And lone pair also contributes to the moment. And the direction of moment due to the lone pair is towards the lone pair. Remember this particular point as well. Right? Remember this particular point as well. Yeah? Lone pair, it also contributes towards the moment and its direction is towards the lone pair always. And my dear students, at the same time, one more point which I would want you guys to take a note of. Any molecule whose net dipole moment is zero, we call the molecule as the non-polar molecule. And similarly, any molecule whose net dipole moment is a non-zero, we call the molecule as the polar molecule. We call the molecule as the polar molecule. So if I ask you HCl, it has got some dipole moment, so it is basically a non-polar molecule. Sorry, it has got some dipole moment, so it is basically a polar molecule. It is basically a polar molecule. NH3, see, one vector is in this direction, one is in this, one is this, one is in this direction, right? So this will also have some net dipole moment, right? So this is again a polar molecule. This is again a polar molecule. This is again a polar molecule. I hope this is clear to everyone. For example, if I take the molecule as carbon dioxide, CO2. If I take the molecule as CO2, carbon dioxide. If you draw the structure of carbon dioxide, it is like this. C double bond O, right? Now, among carbon and oxygen is more electronegative. This is less. The direction of movement is from less electronegative to more electronegative. The direction of movement is from less electronegative to more electronegative. So both the vectors are equal in opposite direction. So they'll cancel each other. So the net dipole moment here will be zero. And that particular molecule whose net dipole moment is zero, we call the molecule as non-polar molecule. So this CO2 molecule is basically non-polar. Number one. Number two, for example, you have got the molecule BeF2. BeF2. If you draw its structure, this is how your BeF2 looks like. Now, the direction of movement is from less electronegative to more electronegative. Less electronegative to more electronegative. Right? Less to more. So both are again equal in magnitude, opposite in direction. Both the moments. So net dipole moment is zero. And that particular molecule whose net dipole moment is zero, we call the molecule as non-polar molecule. Perfect. For example, take the molecule as BF3. Take the molecule as BF3. This is the molecule BF3 which I'm talking about. The bond angle here, the angle here is 120 degree. The angle here is 120 degree. Now guys, if you look carefully, if you talk about this particular bond, the dipole moment direction is from less electronegative to more electronegative. Less to more. Less to more. Perfect. These two moments are at an angle of 120 degree. So their resultant will be in this direction. And the resultant of the vector, the resultant of these two vectors is this one. And its magnitude will be same as that of the magnitude of this one. So it will cancel out. I would say net dipole moment here is zero. So the molecule is again non-polar. So on the basis of the net dipole moment, we can classify molecules as polar molecules and non-polar molecules. I hope this is clear, right? Now guys, something which I would want you guys to take a note of right now. I'll make you understand this after some time, but take a note of one important point, okay? Whenever you see a molecule of the type AB2L0 or AB3L0 or AB4L0 or AB5L0 or AB6L0 or AB7L0 or AB2L3 or AB4L2. Whenever you see these molecules, first of all, how can I check the types of the molecules like this AB2L0, AB3? That's something which I'll teach you afterwards. I'm just telling you to take a note of one thing right now. Whenever you see molecule of these types, remember, these are the set of the molecules. Their net dipole moment will be always zero, and these molecules are always going to be non-polar in nature. Take a note of this point. I'll make you understand this particular point in some time when I'll be teaching you VSEPR theory. Okay? Right? Perfectly done. I believe this is clear. Now guys, one more thing. As I told you, your dipole moment is basically equal charge multiplied by distance. Charge multiplied by distance. Right? So I can say dipole moment is directly proportional to distance as well as directly proportional to charge. You can say dipole moment is directly proportional to charge. Right? And charge on the atoms is directly proportional to the electronegativity difference between the atoms. Charge on the atoms is directly proportional to the electronegativity difference between the atoms. More the electronegativity difference between the atoms, more the electronegativity difference between the atoms, more will be the charge on the atoms. And more the charge on the atoms, definitely more is going to be the dipole moment. As simple as that. Similarly, this dipole moment, it is also directly proportional to the distance between the atoms. It is directly proportional to the distance between the atoms. Distance means A, right? More the distance between the atoms, that means more is the value of A, more the value of A, more is going to be the dipole moment. As simple as that. Right? Yes? Right, people? Am I clear till here? Am I clear till here? Am I clear till here? Okay. Now, guys, whenever you have to arrange the molecules as per the dipole moment, whenever you will have to arrange the molecules as per the dipole moment, you will prioritize this rule first. After that, you will prioritize this rule. I would say, first of all, 99.9% cases, you'll be prioritizing this rule. You'll be just seeing the electronegativity difference between the atoms. And in terms of electronegativity difference between the atoms, you can give the order of dipole moment. And I'll tell you those cases where you have to prioritize distance as well. I'll tell you those molecules where you have to prioritize the distance as well. But mainly, you'll have to prioritize the electronegativity difference. For example, guys, have a look. Try to understand. Try to understand. Leave this aside. We'll be talking about this afterwards. We'll be talking about this particular case afterwards. Talk about this one, H2O and H2S. Here the bond is between oxygen and hydrogen. Here the bond is between sulfur and hydrogen. You know, in your periodic table, fluorine is maximum electronegative, followed by oxygen, followed by nitrogen. This is something which every one of you will be knowing. Now, the bond is between OH. Here the bond is between sulfur and hydrogen. Where is the electronegativity difference more? Electronegativity difference is more in OH as compared to SH. More the electronegativity difference, more is going to be the dipole moment. Simple. Bond is between nitrogen and hydrogen. Here the bond is between phosphorus and hydrogen. Nitrogen-hydrogen electronegativity difference is more. More the electronegativity difference, more is the dipole moment. Simple. Right? Yes? Now, my dear students, here the bond is between O and H. Here the bond is between N and H. Where is the electronegativity difference more in case of water? So dipole moment is more here. Dipole moment is more here. As simple as that. As simple as that. Now, for example, talk about this particular case first. Nitrogen, hydrogen, nitrogen, fluorine. Where is the electronegativity difference more? Among nitrogen, hydrogen or nitrogen, fluorine? Among nitrogen and hydrogen, electronegativity difference is more. So NH3 has got more dipole moment than that of NF3. Now, if you look at this particular case, my dear students, here the bond is between carbon and chlorine. Chlorine is more electronegative. So the moment is from less electronegative to more electronegative. Less electronegative to more electronegative. Less electronegative to more electronegative. Right? So both the moments are in the same direction. So this molecule will have some net dipole moment. It will have some net dipole moment. Now, less electronegative to more electronegative. Less electronegative to more electronegative. Both are equal and opposite in direction. So cancels each other. So its net dipole moment will be 0. So which one has got more dipole moment? This particular molecule has got more net dipole moment. As simple as that. HF, HCl, HBr, HI. Where is the electronegativity difference more? In the first case, electronegativity difference is more. More the electronegativity difference, more is going to be the dipole moment. Simple. Right? Simple. Now, my dear students, look at this particular case. Look at this particular case. This is important and you have to remember as well. Okay? This is important and you have to remember as well. First of all, here the bond is between carbon and fluorine. Here the bond is between carbon and chlorine. Let me compare these two first. See, fluorine is more electronegative than that of carbon. Right? Chlorine is more electronegative than that of carbon. Right? Now, first of all, as per the electronegativity difference factor is concerned, I would say here the electronegativity difference is more. So that means CH3F should have more dipole moment than CH3Cl. As per which factor? As per electronegativity difference factor is concerned. But at the same time, if you talk about the bond length, CCl bond length is more than that of CF bond length. CCl bond length is more than that of CF bond length. So if CCl bond length is more than that of CF bond length, I would say as per your distance factor. As per your distance factor says that CH3F should have less dipole moment than that of CH3Cl. And let me tell you, among these two cases, distance factor dominates over electronegativity factor. Distance factor dominates over electronegativity factor. So I would say CH3Cl will have maximum dipole moment, then comes your CH3F, then comes your CH3Br, then comes your CH3I. This is the order of the dipole moment here. So take a note of this point. This is important. I believe this is clear to everyone. Yes? Let me know once if it is clear. If it is clear, let me know once in the chats quickly. Everyone, people. Yeah? All right. Now, guys, there are a few more cases which I would want to discuss with you. Talk about this particular case. Talk about this particular case. Before solving this particular equation, tell me one thing. Let's say this is one of the vector in this direction. This is one more vector in this direction, right? Let's say its magnitude is x, this also x. I would say resultant of these two will be in this direction, something which you already would know, right? Now, for example, if you have got one vector in this direction, one vector over here in this direction at an angle of 120, their resultant will be in this direction. You would have studied this already. You would have studied this already, correct? You know this in physics. Now, why am I telling you all this? Why am I telling you all this? Understand. Here you have got CF bond, CF. So less electronegative to more electronegative. Less electronegative to more electronegative. Less electronegative to more electronegative. Right? Okay. Now do you see one thing? If the magnitude of this is x, this is also, for example, x, this is also x. Now look at this one and this one. Can I say they are at an angle of this one and this one? They are at an angle of 120 degree. So their resultant will be in this direction only. And if this was x, this was x, the resultant is also going to be x. Already in the same direction, there is already 1x. 1x and the resultant of these two is also x. So x plus x makes it 2x. So I would say the net dipole moment magnitude here is 2x in this direction. Correct? Similarly, less electronegative to more, less to more, less to more. These two are at the angle of 120, right? So their resultant is in this direction, which will be x. So this x and this x cancels out, right? So net here will be 0. Okay. Now look at this one. Less electronegative to more, less to more, less to more. So this and this cancels out. So resultant is going to be x only. This was x, this was x, this was also x. X cancelled, so this is only 1. Similarly, less to more cancels out. So net dipole moment here is 0. Now, can you give the order of dipole moments? Where do you see the dipole moment maximum? 1 is having maximum. This is 1. 2 and 3, they have got same. 2 and 3, their moment is net dipole moment is same. The last one has got 0 dipole moment, that is 0. So this is the order of the dipole moments net over here in this particular case. Do you understand? Am I clear? Am I clear, people? Let me know once in the chats if all this is clear. All right, one more important thing which I would want to discuss with you. For example, I've got the molecule like this. This is the molecule. What would be its net dipole moment? What would be its net dipole moment? See, less electronegative to more, less to more. So cancels out. So I would say net will be 0. Now tell me the net dipole moment of this particular molecule. This is, for example, OH, and this also, for example, OH. So OH from the top, OH from the top, down from the bottom as well. So it seems as if it seems as if its net dipole moment should be also 0, right? This is OH, this is OH. Net dipole moment should be 0. But what happens? If you look at this particular bond, OH, less to more, are they cancelling out? So because of the orientation of this OH group here, its net dipole moment won't be 0. That is the reason this molecule is polar in nature, whereas this molecule is non-polar in nature. Right? It's not necessary that you'll be having OH only. You can have SH group as well. If this is SH attached, if here also there is SH, due to the orientation of this SH group and this SH group, its net dipole moment comes out being non-zero, due to which the molecule is polar in nature. Now, few more questions which can be asked. Try to understand these sort of questions which we have. Understand properly. First of all, have you ever heard CH3? CH3 is electron donating group. Electron donating group. If I talk about NO2, NO2 is electron withdrawing group, right? For example, cyanide, electron withdrawing group. Okay, this is something which you would have sometimes studied in GOC as well. Which one is electron donating, which one is electron withdrawing? Now try to understand. See exactly what I'll be doing. My dear students, this is electron donating. If this is donating, it will donate electrons. When it donates electrons, when it pushes the electrons, donates electrons, right? It will get delta positive. This will get delta negative. CH3, electron donating, it pushes the electrons. So again, delta positive, delta negative. See, over here, a dipole got created. Over here, a dipole got created. The dipole moment direction is from positive to negative. Again, from positive to negative. Cancels each other. So net dipole moment here is 0. Correct? Net dipole moment is 0. If you look at this one, donating. If this is donating, delta positive, delta negative. So positive, negative. Again, positive, negative. So one moment is going in downward direction. One moment is in this direction. So they are at an angle of what? They are at an angle of 120 degree. Two vectors at an angle of 120 degree. Look at this one. Positive to negative, positive to negative. One vector going in downward direction, one vector going in this direction. The angle here is 60 degree. Whenever the angle between the vectors is less, the resultant has to be more. So among this and this, angle is lesser here. So resultant here will be more as compared to this. Okay. So 3 will have more dipole moment, followed by 2, followed by 1. Correct? Now, if you look at this particular question, if you look at the next question, try to understand. Try to understand what do we do. Try to understand what do we do here. This is electron donating, right? Donating. So this is positive, this is negative. This is positive, this is negative. Now you know this is positive, this is negative. So moment direction is from positive to negative, right? Now this is electron withdrawing. If it withdraws electrons, so it gets negative, this gets positive. And the moment direction is from positive to negative. So basically, one is in downward direction, one is in this direction. Angle here is 120. Correct? Lesser the angle, more the dipole moment. You know it already. Now, positive to negative, positive to negative. One in this direction, one in this direction at angle of 60. Positive to negative, right? Positive to negative. Both going in the same direction, angle here is 0 degree. Lesser the angle, more the dipole moment. So net dipole moment will be maximum in third, followed by 2, followed by 3. So 3 to 1 is the order here. Guys, do you understand how do we deal with such kind of questions? Do you understand what kind of questions can be asked from dipole moment? Yes? Do you understand? Am I clear? Am I clear? Am I clear? Am I clear? If I am clear, then you should be in a position to tell me the answer of this particular question. You should be in a position to answer me this particular question. Quickly, give it a try. Tell me the answer of this question. Absolutely, all of you are perfectly correct. It's going to be BF3. I've shown you already. Its net dipole moment is 0. BF2, already shown you, net dipole moment is 0. Carbon dioxide, already shown you, net dipole moment is 0. 1,4-dichlorobenzene, few minutes back only I showed you, its net dipole moment is also 0. Right? So all these three molecules, they are basically non-polar. They'll be having 0 dipole moment. I believe it's clear. I believe it's clear. Yes. So I hope your dipole moment concept is like absolutely clear to you. Now let's move on to Fajan's rules. Let's move on to Fajan's rules. My dear students, why do we need the Fajan's rules first of all? Well, I'm not going into the details, very much details of Fajan's rule. I'll teach you that stuff that is going to come into your exams. Nothing more, nothing less. Yes? Now see guys. First of all, you should know only one thing. There is no bond. There is not a single bond. There is no bond, not a single bond, which is either 100% covalent or 100% ionic. There is no bond which is either 100% ionic or 100% covalent. Every covalent bond has got some ionic character. Every ionic bond has got some covalent character. This is the first thing which you should remember. There is no bond which is 100% ionic or 100% covalent. Every ionic bond has got some covalent character and every covalent bond has got some ionic character. And let me tell you one thing. As I told you, there is no bond which is 100% ionic or 100% covalent. Every covalent bond has got some ionic character. Every ionic bond has got some covalent character. And let me tell you, covalent character in an ionic bond. It cannot be calculated, but can be compared. Covalent character in an ionic bond cannot be calculated, but it can be compared. Compared with the help of what? Compared with the help of Fajan's rules. Compared with the help of what? With the help of Fajan's rules. I'm not going to go into much of its details. As I told you, I'll just tell you that part which is sufficient to solve the questions which can be asked in your NEET examination. What is that exactly? Have a look. My dear students, as I told you, with the help of Fajan's rules, we can compare the covalent character in an ionic bond. We can compare covalent characters in an ionic bond, in ionic bonds, right? And let me first of all tell you, covalent character. This is the first point which you are going to take a note of. Covalent character in an ionic bond. Covalent character in an ionic bond. That depends on two factors. One is called as polarizing power. Of cation. And one more factor on which this covalent character in an ionic bond depends. That's called as polarizability of anion. So two factors are basically going to be the deciding ones, right? To compare the covalent character in an ionic bond. One is polarizing power of cation, one is polarizability of anion. Now, first of all, this polarizing power of cation. Remember directly, guys. Polarizing power of cation is directly proportional to the charge on cation, inversely proportional to the size of cation. Polarizing power of cation is directly proportional to charge on cation, inversely proportional to size of cation. And similarly, remember one more thing. Polarizability, which is the term defined for anions. Polarizability of anion is directly proportional to the charge on anion, also directly proportional to the size of anions. Let me write it completely. Charge of anion also directly proportional to size of anion. So basically, if you just remember this, you can solve each and every equation almost. Let me first of all tell you again. As I told you, there is no bond which is 100% ionic or 100% covalent. Every covalent bond has got some ionic character. Every ionic bond has got some covalent character, right? Now, covalent character in an ionic bond, it cannot be calculated, but can be compared with the help of Fajan's rules. And as per Fajan's rules are concerned, covalent character in an ionic bond, it's directly proportional to the polarizing power of cation, also directly proportional to the polarizability of anion. Now, polarizing power of cation itself depends on two factors, charge on cation and size of cation, right? Polarizability of anion, directly proportional to charge of anion, also directly proportional to size of anion, right? If you just remember these three things, you're done, you're sorted. Number one. Number two, at the same time, remember your covalent character in an ionic compound. Covalent character is basically inversely proportional to ionic character. Sometimes they'll ask you the question on the basis of covalent character. Sometimes they'll ask you the question on the basis of ionic character. Now, see how easily you can solve the questions. See how easily. You don't have to go for the detailing and stuff. See, check whether you'll be able to solve this question or not. Arrange the following on the basis of polarizing power. Arrange the following as per the polarizing power. Check it carefully. More polarizing power is defined for cations. Polarizing power is directly proportional to charge on cation. So more the charge on cation, more the polarizing power. More the charge on cation, more the polarizing power. More the charge on cation, more the polarizing power. Done. You have arranged all of them as per the polarizing power. Correct? Okay. Arrange these cations as per the polarizing power. Now, lithium, sodium, potassium, rubidium, cesium. They belong to same group. They belong to same group. Down the group, size increases. Down the group, size increases. Polarizing power is inversely proportional to size. Polarizing power is inversely proportional to size. Lesser the size, more the polarizing power. Lesser the size, more the polarizing power. Again, lesser the size, more the polarizing power. Why did I discuss on the basis of size? Because the charge here is same. So I discussed here in terms of size. Okay? Simple? Simple, guys? Now, one more thing I want to tell you. For example, these are the cations. Okay? Now, for example, you have to arrange them on the basis of their polarizing power. Let me tell you, all these are D block elements. All these are D block elements. My dear students, in case of D block elements, remember one thing directly. In case of D block elements, polarizing power is directly proportional to effective nuclear charge. Polarizing power is directly proportional to effective nuclear charge. And you know, on moving from left to right, effective nuclear charge increases. Effective nuclear charge increases. So I would directly say polarizing power will also increase. In case of D block elements, polarizing power depends on Z effective, right? And remember, on moving from left to right, polarizing power, Z effective increases. Therefore, polarizing power automatically will increase. So this is the order of the polarizing powers. As simple as that. Similarly, my dear students, one more important thing which you need to remember. When you move from 3D to 4D, 4D to 5D, when you move from 3D to 4D, 4D to 5D, again, when you move from 3D to 4D, 3D to 4D, 4D to 5D, again, let me tell you, Z effective increases. Z effective increases. And if Z effective increases, polarizing power also increases. Because I told you polarizing power is directly proportional to Z effective. On moving from 3D to 4D, 4D to 5D, Z effective increases, therefore polarizing power increases. Now, I believe you can easily tell me the answer of this question. Zinc dipositive, cadmium dipositive, mercury dipositive. This is 3D element. This is 4D element. This is 5D element. Right? What happens? 3D to 4D, 4D to 5D, Z effective increases. So polarizing power also increases. This is the order of polarizing power. Similarly, if I ask you about the order of polarizability, I already told you polarizability is defined for anions. Polarizability is defined for anions. And my dear students, if I talk about anions, Polarizability is directly proportional to charge on anion, also directly proportional to size of anion. Now, charge on anion is maximum here, polarizability is maximum. Charge on anion is maximum here, polarizability is maximum. Simple, right? Similarly, polarizability also depends on size. As I've already written, polarizability is directly proportional to size on anion. See, fluorine, chlorine, bromine, iodine. Down the group, fluorine, chlorine, bromine, iodine. Size increases. If size increases, polarizability will increase. If size increases, polarizability increases. Size increases, polarizability increases. Simple. Simple, right? I hope I'm clear with this. And people, if I am clear with this, then these are the questions which can be framed from these Fajan's rules. Try to understand what exactly I'm going to say. Let me quickly summarize this. First of all, covalent character in an ionic bond depends on two factors: polarizing power of cation and polarizability of anion. Now, polarizing power of cation is directly proportional to charge of cation, inversely proportional to size of cation. Polarizability of anion is directly proportional to charge on anion, also directly proportional to size of anion, right? That's all. That's enough. We are done. Now see, basically we have to arrange them on the basis of their covalent character. First of all, this is technically zinc dye positive, this is Cl negative. Cadmium dye positive, Cl negative. Mercury dye positive, Cl negative. How am I doing this? Because one zinc, one cadmium, one mercury. Just crisscross. 2 goes here, 1 goes here. 2 comes here, 1 comes here. 2 comes here, 1 comes here. Right? Now people, is the anion same everywhere? Cl negative, Cl negative, Cl negative. So I cannot decide on the basis of anion. I am going to decide as per the cation. Now, this is your 3D element, 4D element, 5D element. Which has got more polarizing power? 5D. More the polarizing power of cation, more is the covalent character. So this is the order of covalent character. Simple. Yes. Now look at the next one. This is technically zinc dye positive, S dye negative. Cadmium dye positive, S dye negative. Mercury dye positive, S dye negative. So S dye negative everywhere is same. So don't decide on the basis of S. Decide on the basis of zinc, cadmium, mercury. Again, 3D element, 4D element, 5D. Polarizing power of this is more the polarizing power, more the covalent character. Simple. Right? Look at the next one. Li positive, F negative. Na positive, F negative. K positive, F negative. Rb positive, F negative. Cs positive, F negative. So F negative everywhere same. I've got nothing to do with it. Now talk about the cations. Lithium, sodium, potassium, rubidium, cesium. Down the group, their size will increase. Right? Lesser the size, my dear students. Lesser the size of the cation, more the polarizing power of cation. More the polarizing power of cation, more the covalent character. Right? BeF2, this is BeCl2, BeBr2, BeI2. Right? So again, you can decide on the basis of size of anion. Since I negative has got maximum size, so polarizability of I negative will be maximum. If polarizability of I negative is maximum, then covalent character will be maximum. And my dear students, one more thing. Whatever is going to be the order of covalent character, opposite to that will be the order of ionic character. Yeah? I hope I'm clear with this. Can you give me the order of all these questions? Arrange the following as per the covalent character. Arrange the following as per the covalent character. This is basically Al tri positive, this is F negative. Again, Al tri positive, Cl negative. Al tri positive, Br negative. Al tri positive, I negative. Al tri positive is same everywhere. Now, talk in terms of anions. The charge on every anion is same. I'll be discussing in terms of size. More the size of anion, more the polarizability of anion. More the polarizability means more is the covalent character. Simple. The Mg dye positive everywhere is same. So talk in terms of anions, more the size of anion, more the polarizability. More the size of anions, more the polarizability. More the size of anions, more the polarizability. And more the polarizability means more the covalent character. Simple. Now, one very important thing. One very important thing. Remember, polarizing power of that cation, which has got pseudo inert gas configuration. Polarizing power of that cation, which has got pseudo inert gas configuration, will be always more than that of that cation, will be always more than that of the cation whose electronic configuration is same as that of noble gas. What does that mean? Again, let me repeat the same statement. Polarizing power of that cation which has got pseudo inert gas configuration is more than the polarizing power of that cation which has got inert gas configuration. For example, what is first of all pseudo inert gas configuration? Whenever you see configuration like this, for example, I've got Cu positive. I've got Cu positive. Can you tell me what will be the outermost configuration of this Cu positive? Let me see what will be your answer. Outermost configuration of Cu positive will be, it will be first of all xenon, and then it will be 3d10. This is the configuration of Cu positive. And if I talk about Na positive will have the same configuration as that of neon. So it is neon, just that's it. These are their electronic configurations, right? Whenever you see this kind of the configuration, what configuration exactly? Noble gas configuration followed by D10. Noble gas configuration followed by D10. This is called as pseudo inert gas configuration. This is called as pseudo inert gas configuration. This is simply the inert gas configuration. Na positive has got the inert gas configuration. What you have to remember, polarizing power of the cation, which has pseudo inert gas configuration, is always more than the polarizing power of the cation which has got inert gas configuration. So Cu positive here will have more polarizing power than that of Na positive. And what is pseudo inert gas configuration? Pseudo inert gas configuration is noble gas configuration, inert gas configuration followed by D10 configuration. Noble gas configuration followed by D10 configuration. This is what you call as pseudo inert gas, right? Here you are not going to talk in terms of size, you are not going to talk in terms of charge, nothing. Just pseudo inert gas configuration, that cation which has got pseudo inert gas configuration, which has got the configuration of inert gas followed by D10, its polarizing power will be more than that of that particular cation which has got inert gas configuration. That's all. That's all, guys. And if you remember this, then you can give me the answer of this question easily. CuCl and NaCl. What do you think? CuCl and NaCl. Over here, this is Cu positive, this is Cl negative, this is Na positive, this is Cl negative. Cl negative is same everywhere. Now Cu positive, pseudo inert gas configuration, Na positive, inert gas configuration. Polarizing power of this cation will be more. More the polarizing power, more the covalent character. Simple. Right? Okay. I did one mistake, guys. This is argon here, yes. It's argon 3d10. Okay? Now clear? My bad. It's okay. Perfect. Perfect. One more thing, guys. One more thing. What are the applications of this? Fajan's rules. Where do we apply it? There are few things which you need to remember. Simple, basic things. What is that? My dear students, first of all, you need to remember one thing. Solubility of ionic compounds is generally more than that of covalent compounds. When the solvent is polar, solubility of ionic compounds is more than that of the solubility of covalent compounds. If the solubility of ionic compound is more than that of the solubility of the covalent compound in polar solvent, I can say simply one thing. I can say solubility is directly proportional to ionic character and inversely proportional to covalent character. Solubility is directly proportional to ionic character, inversely proportional to covalent character. Because we know solubility of ionic compounds is more than that of covalent compounds in polar solvents generally. Therefore, I can summarize one thing: solubility is directly proportional to ionic character, inversely proportional to covalent character. Now, for example, if you take Ag2S and Ag2O. See, this is Ag positive, this is S di-negative. Ag positive, O di-negative. Ag positive, same. Now, S di-negative, O di-negative. S di-negative, O di-negative. Charge is same. Size of this is more. More the size of anion. More the polarizability of anion. More the polarizability of anion. More the covalent character. More the covalent character. Lesser the ionic character. So, this is the ionic character order. And whatever is the ionic character order, same is the order of solubility. So, I would say Ag2S is less soluble than that of Ag2O. That is something which is mentioned here. Ag2S is less soluble than that of Ag2O. This is the order of solubility. Do you understand this? Do you understand all this, people? Similarly, if you need to compare FeOH whole thrice and FeOH twice, if you need to compare their solubilities, this is basically Fe tri positive, this is OH negative, this is Fe di positive, this is OH negative. So OH negative is same. So I cannot decide on the basis of OH negative, but I can decide on the basis of Fe, right? This is tri positive, this is di positive. So if I talk about FeOH whole thrice and FeOH whole twice, so the anion is same. Talk in terms of cations. More the charge on cation, more the charge on cation, more is the polarizing power of cation. More the polarizing power of cation, more is the covalent character. More the covalent character, lesser the ionic character. So this is the order of ionic character. And whatever is the order of ionic character, same is going to be the order of solubility. So that's why we have mentioned here, FeOH whole thrice is less soluble than that of FeOH whole twice. Okay? I believe this is clear. And people, if this is clear, then comes one more thing. One more application. Remember, some questions are asked based on melting point as well. And remember, melting point of ionic compounds is again more than that of covalent compounds. Melting point of ionic compounds is more than that of the melting point of covalent compounds. And remember, my dear students, you can say melting point is, since ionic compounds are more melting point than that of covalent compounds, so you can say melting point is directly proportional to ionic character, so automatically it will be inversely proportional to covalent character. Automatically it will be inversely proportional to covalent character. Now, I believe you can easily solve this question. For example, you have got BeCl2, you have got MgCl2, you have got CaCl2, beryllium, magnesium, calcium, strontium, and barium. Tell me down the group, what happens to the order of the melting point? Melting point order down the group. Will it increase or decrease? You are going to use the same concept, whatever I'm telling you right now. This is Be di positive, Mg di positive, calcium di positive, strontium di positive, barium di positive. Down the group, size increases. So the size of this cation is least. If the size of this cation is least, it will have more covalent character. More covalent character, lesser ionic character. Lesser ionic character, lesser melting point. So this will have least melting point. That means down the group, melting point increases here. Down the group, melting point increases here. Am I clear? Say yes or no once. Am I clear, guys? And if I am clear, then there is one more thing. That means one more application. Questions are asked based on thermal stability as well. Questions are asked based on thermal stability as well. And let me tell you again, thermal stability of ionic compounds is more than that of covalent compounds. Thermal stability of ionic compounds is more than that of covalent compounds. So I can say simply like this, thermal stability is directly proportional to ionic character, inversely proportional to the covalent character. Thermal stability is directly proportional to ionic character, inversely proportional to what? Covalent character. Right? So again, if this is the question, Li2CO3, Na2CO3, lithium, sodium, potassium, K2CO3, rubidium, Rb2CO3, CS2CO3. Tell me one thing. This is Li positive here, Na positive, K positive, Rb positive, CS positive. Charge on every cation is same. Now talk in terms of size. This lithium has got least size. Lesser the size of the cation. Lesser the size of the cation. More the polarizing power of cation. More the covalent character. Lesser the ionic character. So this has got lesser ionic character. This has got lesser ionic character. Lesser the ionic character. Lesser the ionic character. Lesser the thermal stability. Right? So down the group, thermal stability will increase. So this will have least thermal stability. Down the group, thermal stability is automatically going to increase. I believe it's clear to everyone. Yes? Am I clear to everyone? Say yes or no once in the chats. Everybody. Everybody, people. Everyone means everyone. Yeah? Correct? Let's do one thing. Let's take a break for 15 minutes now. Okay? Let's take a break for 15 minutes. I'll join back exactly at 10 now. Okay? At 10 p.m. I'll start again. A quick break. A quick break of 15 minutes we are going to take, and we'll start exactly at 10 p.m. The valence bond theory. All right? But make sure everyone is back exactly at 10 p.m. Or there's no need to leave. You guys can talk in the chats. See you in a while. See you in 15 minutes. Is everyone back? Is everyone back? Yes. All right, people. Now we are going to start one more important topic of the chapter. What is that? That is your valence bond theory. Okay, one of the important topics. Valence bond theory. So first of all, let me tell you this valence bond theory, it explains the formation of covalent bonds. It explains the formation of covalent bonds. This particular theory is going to tell us how exactly a covalent bond is formed. This particular theory is going to tell us how exactly a covalent bond is formed. So how a covalent bond is formed as per VBT? My dear students, as per valence bond theory is concerned, a covalent bond is formed by the overlap of atomic orbitals of the bonding atoms. As per your VBT is concerned, as per your valence bond theory is concerned, a covalent bond is formed by the overlap of atomic orbitals of bonding atoms. What does that mean? For example, I've got two atoms, atom A, and this is one more atom A, for example. Okay. Let's say this is the atomic orbital of this particular atom, and this is the atomic orbital of this particular atom. Okay. Now, my dear students, as per VBT is concerned, if these two atoms have to form the bond, if these two atoms have to form a covalent bond, what exactly should happen? What exactly should happen? These atomic orbitals should merge into each other. These atomic orbitals should merge into each other. Okay? And the merging of electron clouds into each other, the merging of atomic orbitals into each other is something which you call as overlap. And let me tell you, in order to show the overlap, I should say these atomic orbitals must approach each other. These atomic orbitals must approach each other so that their electron clouds will merge into each other. And let me tell you, this merging of electron clouds into each other, the merging of atomic orbitals into each other is what you call as overlap. Is what you call as overlap. And due to the overlapping, which bond gets formed? Covalent bond gets formed. Due to the overlapping, which bond gets formed? Covalent bond gets formed. So first of all, let me again repeat the same thing. Valence bond theory explains us the formation of covalent bond. My dear students, for the covalent bond formation, atomic orbitals of bonding atoms, they must come close so that their electron clouds will merge into each other. Merging of electron clouds into each other is what you call as overlap. And due to the overlap, which bond gets formed? Covalent bond gets formed. And at the same time, when the atomic orbitals merge into each other, when these electron clouds merge into each other, what happens after that? What happens after that? What happens after that? I would say, once the electron clouds merge into each other, I would say the electron cloud will arrange in such a way, the electron cloud will arrange in such a way that it comes under the influence of both the nuclei. So this is the final structure which I'm showing. So first of all, this was atomic orbital of this atom. This was atomic orbital of this atom. Now, they have to form a covalent bond. So they should come close. When they are coming closer, what is going to happen? Their atomic orbitals will merge into each other. When the atomic orbitals merge into each other, this merging of electron cloud into each other is called as overlap. Due to overlap, covalent bond gets formed. Now this electron density comes under the influence of both the nuclei, right? And due to the overlapping, which bond got formed? It is basically the covalent bond that got formed. So one thing which we have to remember, what is that? A covalent bond is formed by the overlap of atomic orbitals into each other. In order to show the overlap, the bonding atoms must come close such that their orbitals can overlap. Okay? And how do we define this overlap? Overlapping is nothing but penetration of atomic orbitals into each other, as I showed you. Penetration of atomic orbitals into each other, right? And my dear students, one more important thing. Remember, more the extent of overlap, remember, stronger is going to be the covalent bond. Stronger is going to be the covalent bond. So more the overlapping between the bonding atoms, stronger is going to be the covalent bond which gets formed. Okay. And as I told you already, as a result of overlapping, the electron density will arrange itself in such a way that it comes under the influence of both the nuclei. Okay. So quickly, if we have the overview of VBT, VBT explains the covalent bond formation. So in order to form the covalent bond, the bonding atoms must close so that their atomic orbitals will merge into each other. Merging of electron clouds, merging of atomic orbitals into each other is what you call as overlapping. And due to overlapping, a covalent bond gets formed. More the overlapping, more the extent of overlapping, stronger is going to be the covalent bond formed. And as a result, the electron density arranges itself in such a way that it comes under the influence of both the nuclei. I believe everything is clear till here. Now let's talk about this overlapping in detail. My dear students, overlapping is basically of two types. One is called as axial overlap. One is called as parallel overlap. One is called as axial overlap. One is called as parallel overlap. First of all, this axial overlap is also called as head-on overlap. It is also called as head-on overlap. So atomic orbitals will overlap along the axes, which I'll show you in some time. I would say the electron clouds, or let me write it, the atomic orbitals will overlap along the axes. What does that mean? You'll understand it in some time. First of all, you take a note of these points. First of all, overlapping is of two types. Axial overlapping, which is also called as head-on overlapping. And during axial overlapping, the atomic orbitals are going to merge into each other along the axes. And due to this axial overlapping, remember, a covalent bond gets formed. And what is the name of that covalent bond which gets formed due to axial overlapping? The name of the covalent bond is called as, it is the sigma bond. So due to axial overlapping, it is the sigma bond that gets formed. Number one. Number two, parallel overlapping, or you can call it as the sideways overlapping. In parallel overlap, atomic orbitals will overlap. By keeping their axes parallel. What is meant by that? That will be understood in some time. Okay. But before that, let me tell you, due to parallel overlap, again a covalent bond gets formed. And what is the name of the covalent bond? And let me tell you, due to parallel overlap, covalent bond gets formed, right? It can be either pi bond or it can be delta bond. Right? But what we are going to discuss, we'll be discussing only pi bond. Delta bond is not in our syllabus basically, right? So let's discuss this parallel overlapping and axial overlapping in detail. Yeah? Let's understand this parallel overlapping and axial overlapping in detail. So my dear students, first of all, if I talk about the axial overlapping, due to axial overlapping, what happens? A sigma bond formation takes place. Sigma bond gets formed. Due to axial overlapping, sigma bond gets formed. Sigma bond is formed. Now let's try to understand it. The first type of axial overlapping which we have, that's called as SS overlap. The first type of axial overlapping which we have, we call it as the SS overlap. Now, what is this SS overlap? Let's try to understand. For example, this is the s orbital. For example, this is the s orbital of a bonding atom. Let's say this is the s orbital of a bonding atom. And this is again s orbital of one more bonding atom. Since s orbitals are spherical in shape, so this is s orbital of one bonding atom. This is also s orbital of one more bonding atom. Perfect? Right? Now, my dear students, what's going to happen? Let me consider an axis over here. This axis, which is passing through the center of both these nuclei. This axis is called as the internuclear axis. This axis is called as internuclear axis, and generally internuclear axis is considered as it is basically z axis, which is generally taken as internuclear axis. So this is your internuclear axis basically, which I'm keeping z axis, right? Which I'm giving z axis. Now, what's going to happen? What is going to happen? These atomic orbitals, they are going to come closer. They'll merge into each other. They'll come closer. They'll merge into each other like this. They'll merge into each other like this, right? And these electron clouds will penetrate into each other. So if I ask you, are these electron clouds merging into each other? Are these electron clouds, are these atomic orbitals overlapping along the axis? Yes, the atomic orbitals are overlapping along the axis. This is the head-on overlap. This is the head-on overlap, right? And head-on overlap is what you call as axial overlap. And due to axial overlap, which bond gets formed? It is a sigma bond which gets formed due to the axial overlap. And as I told you already, what happens? My dear students, once the overlapping is done, this common electron density, it will arrange itself in such a way that it comes under the influence of both the nuclei. So the final shape of it, I'm going to show like this. This is the nucleus of one atomic orbital. This is the nucleus of one more atom, right? And this is the electron density, which comes under the influence of both the nuclei. So which bond got formed here? It is a sigma bond that got formed in this particular case. Okay? Perfect. Am I clear till here? One more important thing, guys, which you are going to remember. When it comes to SS overlap, it always shows positive overlap. It is never going to, there will be never negative overlap in case of SS. What is meant by negative overlap? That's something you'll understand in some time. First of all, you remember one thing. When it comes to SS overlap, it's always going to be positive overlap. It is not going to be negative overlap. Yeah? Now, people, the second type of axial overlap, what is that? The second type of axial overlap is what you call as PP overlap. The second type of axial overlap is what we call as PP overlap. Let's try to understand how this PP overlap looks like. This is, for example, the internuclear axis, which is generally taken as Z axis. For example, since p orbital is dumbbell shaped, so this is a p orbital of a bonding atom. This is also a p orbital of one more bonding atom. Perfect? P orbital of one more bonding atom. Now, these p orbitals, they are going to overlap. It's again going to be head-on overlap along the axes, right? Now, one thing which I'm going to do over here is, let me give this as the positive sign. Let me give this as the negative sign. Let me give this as the positive sign. Let me give this as the negative sign, right? Do you see same sign on same sides? Same sign on same sides. Same sign, same sides means positive overlap. It means positive overlap. Or you call it as the in-phase overlap. You call it as the in-phase overlap. And what happens due to this in-phase overlap? Due to positive overlap, bond formation takes place. So these lobes, they are going to merge into each other. And when they merge into each other, this is how they look like. This is how they look like. This is how they look like. Positive, positive. In the middle, I'll be showing positive sign here. So this is the common electron density. This is the common electron density which came under the influence of both the nuclei. So what is this, the head-on overlap? Absolutely is the head-on overlap. And due to head-on overlap, which bond got formed? It is the sigma bond that got formed here due to head-on overlap. Now, for example, if I have to show pp negative overlap, see how I'm going to show pp negative overlap. This is p orbital of one bonding atom. This is p orbital of one more bonding atom. I'll show positive, negative. Here I'll show negative, positive. Opposite sign on same side. Opposite sign on same side means negative overlap. Opposite sign on same side means negative overlap, or you call it as out of phase overlap. And due to negative overlap, there is no bond formation. Bond formation happens due to positive overlap. Okay? Bond formation happens due to positive overlap. I believe this is clear. So this was your PP axial overlap, right? This was your PP axial overlap. Am I clear with this? Did you understand, people, what I said? Am I all clear with this? Am I all clear with this? Okay, am I all clear with this? Now, similarly, the third overlap, the third axial overlap is what you call as SP overlap. SP overlap. SP overlap. Now, for example, again, this is, for example, your internuclear axis, which is generally taken as Z axis. So this is your Z axis, first of all, right? Let's say this is the S orbital of a bonding atom. This is P orbital of one more bonding atom. Correct? Perfect. Right? Let me give this positive sign. Let me give this negative sign. Okay, just to show you whether positive overlap is happening or negative overlap is happening. Now, my dear students, what happens exactly? What happens exactly? So, I'm right now showing you the positive overlap, in phase overlap. So, these atomic orbitals will merge into each other. When they merge into each other, how it finally looks like? This was your S, and this is the lobe of P that has merged into S. So, this is basically overlapping here. It is again head-on overlapping, and due to head-on overlapping, which bond got formed? It is a sigma bond that gets formed. It is a sigma bond that gets formed. Okay? It is a sigma bond that gets formed. If I have to show the negative overlap, how will I show the negative overlap? I'll keep just negative here. Negative, positive. Opposite sign on same side. Right? That will show you the negative overlap. Perfect. So due to head-on overlapping, due to axial overlapping, it is always the sigma bond that gets formed. Perfect. Now, my dear students, there is one more overlap. You call it as the parallel overlap. What happens in parallel overlap? What happens in parallel overlapping? First of all, due to parallel overlapping, which bond gets formed? If I ask you due to parallel overlapping, which bond gets formed? It is basically the pi bond that gets formed due to parallel overlapping. Or sometimes delta bond can also get formed. Okay, let's try to understand. For example, the first type of parallel overlapping which I'm going to show, that is your PP overlap. PP parallel overlap. PP parallel overlap. Now, what happens in PP parallel overlap? First of all, I'm going to make the internuclear axis, which is your Z axis. Generally, you know that. So this is your, for example, Z axis. This is your Z axis, right? If this is Z, let me do one thing. Let me call this p orbital as py. Let me call this p orbital as py as well. This is p orbital of one bonding atom. This is p orbital of one more bonding atom. Let me give them sign as well. Positive, positive, negative, negative. So, same sign, same side. Same sign, same side. It's going to be positive overlap. Positive overlap means in phase overlap, due to which bond will get formed. Now, how is the bond formation going to take place? This was your p orbital, and this your one more p orbital. Okay, so what happened here? Merging of electron clouds into each other happened. Perfect. Merging of electron clouds into each other happened. So is this head-on overlap or parallel overlap? It is parallel overlap. These two atomic orbitals are overlapping by keeping their axes parallel. So how do I show it at the end? At the end, I'm going to show it like this. At the end, I'm going to show it like this. Since here, I'll be drawing a plane like this. I'm drawing a plane over here. I'm drawing a plane over here. Above the plane and below the plane, I'll show the electron density. Above the plane and below the plane, I'll show the electron density like this. This is the electron density, for example, above the plane. And this is the electron density which I'm showing below the plane. Okay. Now, if I would want to give the signs as well, on the top positive, on the bottom negative. I'll keep positive here, I'll keep negative here, right? So basically on this plane, there is no electron density. The electron density is above the plane and below the plane, right? On the plane, there is no electron density. So I'll be calling this particular plane on which there is no electron density. I'll be calling this plane as the nodal plane. So which overlap this is? This is the parallel overlap. Due to parallel overlap, which bond gets formed? Due to parallel overlap, it's the pi bond that gets formed. It is the pi bond that got formed. And this pi bond got formed by the parallel overlap of P and P. So this pi bond you'll be calling as P pi bond. You'll be calling it as P pi bond. By the way, if you want to show the negative overlap, you can show the negative overlap as well. For example, this is the p orbital of a bonding atom. One more p orbital of one more bonding atom. This is positive, this is negative. This is negative, this is positive. Right? Now, this will represent negative overlap. This will represent negative overlap. Opposite sign on same side. Zero, no bond formation. No bond formation. Yeah? So this was your PP parallel overlap. Similarly, if you talk about PD parallel overlap, how it looks like. Now, again, it's going to be similar. For example, this is, let's say, one of the p orbitals of a bonding atom. And let's say this is the d orbital of one more bonding atom. Now, in order to show the positive overlap, what should I show? Positive, positive. Negative, negative. If this is positive, this will be negative. If this is negative, this will be positive. Perfect. So this represents positive overlap. This represents in-phase overlap. And due to positive overlap, due to in-phase overlap, bond gets formed. So what happens basically? This was your p orbital. And the lobes of d orbitals would have merged into the p, due to which this overlap has happened. And this overlap, is it head-on overlap or parallel overlap? It's parallel overlap. Due to parallel overlap, which bond gets formed? It is a pi bond that gets formed. What should I be calling this pi bond as? This called as P and D. So I'll be calling this pi bond as P pi D pi bond. Perfect. Now, people, at the same time, if I have to show the negative overlap, I can show that too. If I have to show the negative overlap, this for example P and this is D, right? If I have to show the negative overlap, this for example positive, this negative. So positive with positive, I'll write negative here. With negative, I'll write positive here. Then this becomes negative and this becomes positive. So opposite sign on same side. Opposite sign on same side means negative overlap. That means out of phase overlap, due to which bond does not get formed. Bond gets formed by positive overlap only. Yeah? Perfect. Similarly, guys, the third type of parallel overlapping. Is what you call as DD overlap. DD overlap. How it looks like. This is the d orbital of one bonding atom. For example, this is the d orbital. Since d orbitals are double shaped, this is positive, this is negative. Let's say this is negative, this is positive. Now again, one more d orbital of one more d orbital of one more bonding atom is going to come and will show overlap like this. Now, for example, this was also positive, this was also negative, this was negative, this was positive. So what happened? Again, parallel overlapping happened, due to which a bond got formed. Which bond gets formed due to parallel overlapping? You call it as the pi bond. What should I be naming this particular pi bond? This pi bond I'll be calling as d pi bond. Correct? Was it positive overlap or negative? It was positive overlap. Why? Because same sign on same side. So is it in phase overlap? Yes, it is in phase overlap. Okay. Now you can show out of phase overlap on your own, I believe, right? Let's say this is one of the d orbitals. This is positive, this is negative, right? This is positive, this is negative. Now, for example, this is one more d orbital. This is negative, this is positive. This is positive, this is negative. So opposite sign on same side. Opposite sign on same side means negative overlap or out of phase overlap, which does not form the bonds. Okay. This overlap, this interaction is also called as two-lobe interaction. As you can see, two lobes are interacting. You call it as two-lobe interaction. You call it as two-lobe interaction. You call it as two-lobe interaction. Now, there can be four-lobe interaction as well. There can be four-lobe interaction as well. So, let me show the four-lobe interaction here only. There can be four-lobe interaction as well. And through four-lobe interaction, delta bond gets formed. And how do I show this four-lobe interaction? Let's have a look. This four-lobe interaction, let's have a look. How am I going to show it? For example, this is a d orbital of a bonding atom. This is one more d orbital of one more bonding atom. Now, for example, imagine it like this. Imagine this is the d orbital. Now, this particular d orbital is coming on the top of it. This particular d orbital is coming on the top of it. So that this lobe and this lobe will interact, right? This lobe and this lobe will interact. And similarly, this lobe and this lobe will interact, and this lobe and this lobe will interact. This particular overlapping is called as four-lobe interaction, due to which a bond gets formed, which you call as the delta bond. Which you call as the delta bond. My dear students, one more important thing. Let me tell you, since we got to know to the axial overlapping, which bond gets formed? It is the sigma bond. To the axial overlapping, it is the sigma bond that gets formed. And due to the parallel overlapping, which bond gets formed? It is the pi bond that gets formed, and at once your delta bond also can get formed. Now my point is, if I ask you among sigma bond and pi bond, which bond will be comparatively stronger among sigma and pi? Let me tell you, sigma bond is formed first. Sigma bond is formed first and is stronger than pi bond. And is stronger than pi bond. Reason is simple. What is that? Reason is, if I talk about the reason is extent of overlap. Reason is extent of overlap in axial is more than that of extent of overlap in parallel. This is one of the common reasons, right, by means of which you can say why sigma bonds are stronger than your pi bonds. Yes? Is it clear, people? Is it clear? Sigma bonds are stronger than pi bonds. Reason being? What is the reason? Reason is pretty much simple. In case of axial overlapping, extent of overlap is more. Right? Extent of overlapping is more. Now guys, try to understand whatever things we discussed. Let's see how we can draw, how we can show an F2 molecule is getting formed through VBT. O2 molecule is getting formed through VBT. N2 molecule is getting formed through VBT. Let's talk about that. Understand properly. Let me show you how F2 molecule gets formed as per VBT, as per valence bond theory. Try to understand very carefully. Okay. For example, this is one of the fluorine atoms. This is one more fluorine atoms. What is the outermost configuration of fluorine? It is 2s2, 2p5. 2s2, 2p5. Correct? So this is 2s basically having 2 electrons and 2p having 5 electrons. 1, 2, 3, 4 and 5. This is again this 2s having 2 electrons and this 2p having 1, 2, 3, 4 and 5. 5 electrons. Let me call this as pz. Let me call this as py. Let me call this as px. Let me call this as PZ. Let me call this as PY. Let me call this as PX. Okay, perfect. Now, my dear students, what's going to happen? If I talk about this fluorine, for example, this is your internuclear axis. This is your internuclear axis. Okay. If I talk about this PZ, since Z axis is your internuclear axis, so this is Z axis. So this is, for example, the PZ of this atom. Similarly, for example, this is PY of the same atom containing 2 electrons. PZ was containing 1, so let me show 1 over here. And similarly, there will be PX as well. PX is having 2 electrons. So this is PX, let's say, which is having 2 electrons. Perfect. Now, my dear students, if you talk about this particular fluorine, again, it has got PZ having 1 electron. So that PZ will come from this side and will do the head-on overlap. Right? Now, it has got PY as well. This is its PY having 2 electrons. And this is its PX having 2 electrons as well. So, do you see over here what happened? What happened? Head-on overlapping, axial overlapping took place. And due to axial overlapping, which bond gets formed? Sigma bond. So, between 2 fluorine atoms, sigma bond has got formed. And how do you represent it at the end? Simple. F, single bond, F. This single bond is your sigma bond. Do you understand? Do you understand this? Similarly, guys, for example, let me show you how O2 molecule gets formed. How O2 molecule gets formed as per VBT. How O2 molecule gets formed as per VBT. See, this is one oxygen atom. This is one more oxygen atom. Its outermost configuration is 2p4. Its outermost configuration is also 2p4, right? So this is basically 2p having 4 electrons. 1, 2, 3, and 4. This is also your 2p having how many electrons? 4 electrons. 1, 2, 3, and 4. Now, my dear students, I'm calling this as PZ. I'm calling this as PY. I'm calling this as PX. Similarly, this I'm calling as PZ. This I'm calling as PY. This I'm calling as PX. Now, for example, this is again your internuclear axis, which is generally kept as Z axis. So this is your Z axis, which is your internuclear axis, right? So this is PZ here. This is PZ. So let's say this is your PZ containing 1 electron, right? Now, people, PY also containing 1 electron. Let's say this is PY containing 1 electron. Let's say this is PX, and over here, for example, this is PX containing how many electrons? 2 electrons. Now talk about one more oxygen atom. This oxygen atom. It also has PZ containing 1 electron. So this is its PZ containing 1 electron, which has done the head-on overlap, right? Which has done the head-on overlap. Similarly, it has got PY having 1 electron. So this is PY having 1 electron, right? Do you see this PY unpaired, this PY unpaired, they are parallel? Yes, they are parallel. And if they are parallel, they are going to show parallel overlap. So they'll show parallel overlap. Also, this has PX as well, having 2 electrons. So this is PX having 2 electrons. So first of all, sigma bond got formed first. Then your pi bond got formed. So how do I show it at the end? How do I show it at the end? This is oxygen. First sigma bond got formed. Then your pi bond got formed. Got it? Is it clear? Is it clear, people? Everyone in the chats? What should I be calling this pi bond as? This will be called as p pi bond. This will be called as p pi bond. I believe this is clear. I want everyone to let me know in the chats once if all this is clear to everyone. Similarly, you can form the N2 molecule as well, as per your VBT is concerned. As per your VBT is concerned. Got it? As per your VBT is concerned. I hope your valence bond theory is properly clear to everyone. Now I am moving on to something called as hybridization. Hybridization. N2 you can form on your own, right? There'll be single bond and two pi bonds, right? There'll be PZ actual overlap, PY parallel overlap, and PZ parallel overlap. Okay? Got it? Am I clear to everyone? Exactly. In N2, there will be one axial overlap and two parallel overlaps, due to which one sigma and two pi will be there. Should I move on? Should I move on? All right. Now, my dear students, when it comes to hybridization, the questions that will be asked to you is, what is the hybridization? You'll be given the molecule. You'll have to check its hybridization. You'll have to check its geometry, right? So how do we check the hybridization? How do we check the geometry? Let's get to know about that. See, guys. First of all, let me show you how do we calculate the hybridization? How do you check the hybridization? How do you check the hybridization? How do you check the hybridization? There's a method to check the hybridization. You call that method as the steric number method. You call the method as the steric number method. Now, what happens in steric number method? My dear students, in this particular method, we are going to define a number called as steric number. Steric number is nothing but it is defined as the sum of sigma bonds that central atom forms plus lone pairs present on central atom. Steric number is the number of sigma bonds which the central atom forms plus the number of lone pairs which are there on the central atom. The first point which all of you would remember from now onwards, what is that? That is, if steric number comes out to be 2, the hybridization involved is going to be sp, number 1. Number 2, if steric number comes out to be 3, the hybridization is going to be sp2. If steric number comes out to be 4, the hybridization is going to be sp3. If steric number comes out to be 5, hybridization is going to be sp3d. And if steric number comes out to be 6, hybridization is going to be sp3d2. And if the steric number comes out to be 7, hybridization is going to be sp3d3. Now, in case of sp hybridization, what happens? S and p orbital of an atom, they mix. In case of sp2 hybridization, it's going to be s orbital and 2p orbitals of an atom. They are going to intermix. In case of sp3 hybridization, it's going to be s plus p plus p plus p, right? So these 4 atomic orbitals of an atom, they are going to intermix. In case of sp3d, it's going to be s, similarly px, py, pz, and with it dz square. These are the orbitals which will participate in the intermixing when it comes to sp3d hybridization. In case of sp3d2, it is s, px, py, pz, then it's going to be dx square minus y square and dz square. These are the atomic orbitals which will take part in the intermixing in case of sp3d2 hybridization. And in case of sp3d hybridization, it is going to be s plus px plus py plus pz plus dxy plus dx square minus y square plus dz square. These are the atomic orbitals which will take part in the intermixing, which will take part in the hybridization in case of your sp3d3 hybridization. Now, when the hybridization is sp, the geometry that is predicted through hybridization, that's linear. The geometry which is predicted through hybridization, that is linear. In case of sp2 hybridization, it is going to be trigonal planar geometry. Trigonal planar. In case of sp3 hybridization, the geometry involved is tetrahedral. sp3d, it's going to be trigonal bipyramidal geometry. Trigonal bipyramidal geometry. And sp3d2, octahedral geometry. Octahedral geometry. sp3d3, pentagonal bipyramidal geometry. Pentagonal bipyramidal geometry. So now, let's try to check one by one about the hybridizations and the geometries of different molecules. Okay? All right? For example, people, try to understand. Let's say I'm taking the simplest case. Simplest case. For example, I am taking your CH4 molecule. I want to check the hybridization of this carbon. I want to check the hybridization of this carbon. I want to check the hybridization of this carbon. Understand. First of all, if I ask you how many valence electrons carbon has, your answer will be 4. Carbon has 4 valence electrons. My dear students, one more thing. How many surrounding atoms this carbon has? This carbon has 4 surrounding atoms. Remember, the number of surrounding atoms is equal to the number of sigma bonds. Number of surrounding atoms is equal to the number of sigma bonds, right? Since carbon had 4 valence electrons, and it is utilizing all the 4 valence electrons to form 4 sigma bonds. Carbon had 4 valence electrons, and it is utilizing all the 4 valence electrons to form 4 sigma bonds. So there will be no lone pair on carbon. Carbon had 4 valence electrons, and it is utilizing all the 4 valence electrons to form 4 sigma bonds. So there will be no lone pair. There will be no lone pair on carbon. What is a lone pair? Lone pair is that electron pair which belongs to the valence shell of the atom but does not take part in the bonding. So carbon, it had 4 valence electrons, and all the 4 valence electrons are utilized. So there is no electron pair left on carbon. So that means there is no lone pair. If there is no lone pair, if I check the steric number is nothing but sigma plus lone pair. Sigma plus lone pair, 4 plus 0 is 4. When the steric number is 4, hybridization is sp3. When the hybridization is sp3, geometry which is predicted through hybridization is tetrahedral. It is tetrahedral. Okay? It is tetrahedral. For example, people, let's say you have got the molecule BF3. Again, a simple molecule I'm taking. One by one, I'll be taking different molecules. Just a second. For example, I'm taking, happened here. Let's say I'm taking BF3 into consideration. Which one is my central atom here? Boron. How many valence electrons boron has? 3. How many surrounding atoms are there? 3. 3 valence electrons, 3 sigma bonds. So no lone pair. Steric number, 3 plus 0 is 3. Hybridization, sp2. Geometry predicted through hybridization, trigonal planar. Simple. Correct? For example, I am taking BeCl2. Talk about this beryllium. How many valence electrons beryllium has? 2. How many surrounding atoms are there? 2. So 2 valence electrons, both the valence electrons utilized to form 2 sigma bonds. So there is no lone pair. Steric number, sigma plus lone pair, 2. Hybridization, sp. Geometry predicted through hybridization is linear. For example, talk about your PCl5. Phosphorus. Phosphorus belongs to nitrogen family. And nitrogen family has got 5 valence electrons basically. 5 valence electrons. How many surrounding atoms? 5. 5 sigma bonds. How many lone pairs? 0. What about the steric number? Sigma plus lone pairs, 5. What is the hybridization? sp3d. What is the geometry predicted through hybridization? That is trigonal bipyramidal. Do you understand all this? Yeah. For example, I've got SF6, sulfur. How many valence electrons? Sulfur comes in oxygen family, 6 valence electrons. How many surrounding atoms? 6. So 6 sigma bonds. How many lone pairs? All the 6 valence electrons have been utilized to form 6 sigma bonds. So 0 lone pairs. Steric number, 6 plus 0, 6. Hybridization, sp3d2. Geometry predicted through hybridization, that's octahedral. That is octahedral, right? Perfect. So like this, you can check the hybridization of different molecules. Now let me take some more cases so that you get used to it properly. For example, NH3. I want to know the hybridization of nitrogen. Let's say I've got NH4 positive. I want to know the hybridization of this nitrogen. For example, I've got XCF2. I want to know the hybridization of this xenon. Let's say I've got XCF4. I want to know the hybridization of this xenon. For example, I3 negative. I want to know the hybridization of iodine. Let's say I3 positive. I want to know the hybridization of iodine. For example, I've got water. I want to know hybridization of oxygen. For example, I've got XeOF4. I want to know the hybridization of this xenon. Let's say these are some cases. One by one we'll take and we'll check their hybridizations. Okay? Understand how exactly am I going to do it. Nitrogen has got how many valence electrons? 5. How many surrounding atoms? 3. So out of 5 valence electrons, 3 electrons have been utilized to form 3 sigma bonds. Out of 5 valence electrons, 3 valence electrons have been utilized to form 3 sigma bonds, right? So there'll be 2 electrons left as such on nitrogen in the form of 1 lone pair. If sigma are 3, lone pair is 1. So steric number is 3 plus 1, 4. Hybridization will be sp3. Simple. Correct? For example, NH4 positive. How many valence electrons with nitrogen? 5. But there is a positive charge. Positive charge means subtract it. If you subtract it, it becomes 4. Surrounding atoms are 4. That means sigma bonds are 4. 4 valence electrons, 4 sigma bonds. No lone pair. Steric number is 4 plus 0, 4. If steric number is 4, hybridization involved will be sp3. Yes, Nitin, you can follow. You can follow. All right. XCF2. Xenon. Xenon is a noble gas. Has got 8 valence electrons. How many surrounding atoms? 2. That means 2 sigma bonds. If it had 8 valence electrons and 2 have been utilized, so there are 6 electrons left as such on xenon in the form of 3 lone pairs. So sigma 2 lone pairs 3. Steric number is sigma plus lone pair. 3 plus 2, 5. Hybridization is going to be sp3d. And which d orbital is involved here? It is going to be dz square. Okay. XCF4. Valence electrons in xenon 8. Surrounding atoms 4. Lone pairs on xenon 2. Steric number 4 plus 2, 6. Hybridization involved sp3 d2. Which d orbitals are involved here? It's again dz square and dx square minus y square. Right? Okay. I believe it's clear. And if it's clear, let's talk about this I3 negative. Can I simplify this I3 negative like this? Can I write it as I2 negative? I can write it as I2 negative. I2 negative, yeah? Now guys, how do we deal with this? If you talk about this particular iodine, how many valence electrons it has? 7. There's a negative charge as well, so 7 plus 1 makes it 8. Okay? How many surrounding atoms? 2. Surrounding atoms means sigma bonds, so 2 sigma bonds. Out of 8 valence electrons, 2 are used. So there are 6 electrons left as such on this iodine in the form of 3 lone pairs. So 3 lone pairs. Steric number is 3 plus 2, 5. Hybridization is simply going to be sp3d. Yeah? sp3d. Right, baby? One of my friend, engineer Wassim, is in the chats. An amazing physics educator. An amazing physics teacher. Yeah? An amazing physics teacher he is. ER Wassim, who you see in the chats. He has been the gold medalist in his BTech also, and he has qualified IES examination also. That's something very, very, very huge. Yes, I'm not kidding. I'm not kidding. He has those achievements under his banner. Okay, should we move on now? Should we move on? Should we move on? All right, people. So let's talk about this I3 positive now. So if I simplify this a bit, I3 positive, I can write it as I2 positive. Correct? I2 positive. What about this iodine? It has got 7 valence electrons, but there is a positive charge as well. So 7 minus 1 makes it 6. If I ask you how many sigma bonds do you see? 2 surrounding atoms means 2 sigma bonds. So out of 6, 2 are used. 4 are left as such in the form of 2 lone pairs. Right? 4 are left as such in the form of 2 lone pairs. Perfect. So my dear students, steric number comes out to be 2 plus 2, 4, and hybridization involved is going to be sp3. Okay. Talk about this water, oxygen. How many valence electrons oxygen has? 8. How many sigma bonds do you see? 2. How many lone pairs will be there on oxygen? 3. Steric number, 3 plus 2. Wait, I made some mistake. It's not 8 valence electrons. It is oxygen has 6 valence electrons. How many sigma bonds it's forming? 2. So out of 6, 2 are used. 4 are left as such in the form of 2 lone pairs. So there are 2 lone pairs on oxygen. 2 sigma, 2 lone pairs. 2 plus 2 comes out to be 4. If steric number is 4, it's going to be sp3. Right? Now people, talk about this xenon. How many valence electrons forming? 8. I mean, it has got 8 valence electrons. How many surrounding atoms do you see? 4 plus 1, 5. How many lone pairs will be there? Understand. Oxygen is divalent. Oxygen is divalent. Right? Out of 8, 4 and 2 of oxygen. Oxygen is divalent. So 4 plus 2, 6 will be utilized. Out of 8, 6 are utilized. So 2 will be left as such on xenon in the form of a lone pair. So steric number, 5 plus 1, 6. Hybridization, sp3, d2. Clear? Now they can ask you which d orbitals are involved here. It is going to be d, x square minus y square, and dz square. Perfectly done. Perfectly done, people. Okay, for example, if I ask you about this NO3 negative, NO2 positive, can you tell me the hybridization of and this XeO2F2? Tell me the hybridizations of all of this. Now you should be in a position to do all of this on your own. Yeah. So first of all, if I talk about this nitrogen, how many valence electrons it has? 5. There is a negative charge, so 5 plus 1 makes it 6. How many sigma bonds do you see? 3 sigma bonds. How many lone pairs are there? Since oxygen is divalent, so 3 2s are 6. So out of 6 valence electrons, all the 6 will be utilized. So no lone pair. Steric number 3 plus 0, 3. Hybridization sp2. Similarly, this nitrogen, how many valence electrons? 5. There's the positive charge, so subtract 1, so make it 4. How many sigma bonds are there? There are 2 sigma bonds. Oxygen is divalent, so 2 2s are 4. All the 4 are utilized. No lone pair. Steric number is 2 plus 0, 2. Hybridization is sp. XeO2F2. Valence electrons on xenon 8. How many surrounding atoms? 2 to 4. How many lone pairs? Oxygen is divalent, so 2 2s are 4. 4 and 2 is 6. Out of 8, 6 are used. 2 are left as such on xenon in the form of a lone pair. Steric number is 4 plus 1, 5. Hybridization involved is sp3d. Got it? Got it, people? So this is how you check the hybridization. Okay, this is how you check the hybridization. This is how questions are asked. This is how questions are asked when it comes to hybridization. Okay. Wassim, there is no need to make the structure. Why do you want to make the structure through hybridization? They'll just ask you the hybridization or the d orbitals which are involved in hybridization. Now the shapes and all we are going to make in VSEPR. Okay. Shapes and all we'll be making in VSEPR now. All right. Perfect. Am I clear with this? Quickly, guys. Okay. I think every single thing is clear till now. So let's move on. All right. Do you want to see it's okay? See here only. This is XC, double bond O, double bond O. There will be one lone pair here at the axial position, right? Sorry, this is equatorial position. It's not axial. This is equatorial, this is also equatorial, this is equatorial. And this is F at the axial position, F at the axial position. This is its structure if you see. It is basically your AB4L1, seesaw shaped. Okay? Done? All right, guys. Now let's move on to one more important theory which we have to discuss. What is that exactly? That is your valence shell electron pair repulsion theory. VSEPR. Valence shell electron pair repulsion theory. Now, first of all, this valence shell electron pair repulsion theory, what kind of information is going to give me? It's going to give me the idea about the actual shape of the molecule. It is going to give me the idea about the actual shape of the molecule. My dear students, for example, if you talk about NH3, this is how your NH3 looks like. And this nitrogen has got a lone pair as well. Okay. Since nitrogen has got in total 5 valence electrons. Okay. These 3 valence electrons are utilized for bonding. And these 2 are non-bonding. These non-bonding are what you call as lone pairs. Or you call them as non-bonding electrons. Non-bonding electrons. And these 3 over here, you call them as the bonding electrons. And let me tell you, bonding electrons plus non-bonding electrons. Bonding electrons plus non-bonding electrons. I'll be calling them as the valence shell electrons. I'll be calling them as the valence shell electrons. Now, as per your VSEPR theory is concerned, VSEPR theory says that a molecule tries to acquire that shape. Let me write it. Molecule acquires that shape in which the repulsions between valence shell electron pairs are minimized. And once the repulsions are minimized, therefore I can say stability is maximized. Therefore, I could say stability is maximized. As far your VSEPR is concerned, molecule acquires that particular shape in which the repulsions between the valence shell electron pairs are minimum. And once the repulsions are minimum, we can say stability is maximum. And remember, my dear students, if you talk about the order of the repulsions, remember the repulsion between lone pair is considered to be maximum, followed by lone pair, bond pair, followed by bond pair. This is the order of repulsion. Okay? This is the order of repulsions. Now, there are few things which I would want to tell you over here. My dear students, first of all, whenever you see a molecule, for example, in a molecule, if the central atom does not have any lone pair, let's say you have got a molecule wherein the central atom does not have any lone pair, at that point of time, whatever is the geometry which is predicted through hybridization, that is going to be the actual shape of the molecule. That particular molecule wherein the central atom does not have any lone pair. Remember, my dear students, at that point of time, whatever is the geometry predicted through hybridization, that's going to be the actual shape of the molecule. And remember at the same time, if you have got a molecule in which the central atom has a lone pair, or pairs, at that point of time, whatever geometry is predicted through hybridization is not the actual shape of the molecule. That is not the actual shape of the molecule. Okay? I believe I'm clear. Now let's try to analyze and understand all of this in detail, one by one. For example, let's talk about those molecules. Which have got steric number. Let's talk about those molecules which have got steric number equal to 3. Let's first of all talk about those molecules which have got steric number equal to 3. You know, if steric number is 3, that means hybridization involved is sp2. And when it comes to sp2 hybridization, the geometry which is predicted through hybridization, what is that? It is trigonal planar. That's trigonal planar. So I'm going to talk about these molecules first of all. Okay, let's talk about those molecules wherein the central atom has got the steric number of 3. If steric number is 3, hybridization involved will be sp2. Geometry predicted through hybridization is going to be trigonal planar. Okay. Now, people, if I ask you how many possibilities are there to have the steric number 3? How many possibilities are there to have the steric number 3? If I ask you, the first possibility is if the central atom is forming 3 sigma bonds and it has 0 lone pairs. This is the first possibility to have steric number 3. Second possibility, if the central atom has got 2 sigma bonds and it is forming 2 sigma bonds and it has got 1 lone pair. Now, first of all, if there are 3 sigma bonds, 0 lone pair, I would say the type of the molecule is going to be AB3L0. AB3L0, where A is the central atom, These are the 3 sigma bonds, and there is no lone pair on the central atom. This is the type of the molecule, Ab3L0. Okay, Ab3L0. And in case of Ab3L0, since there is no lone pair on the central atom, there is no lone pair on the central atom, and whenever there is no lone pair on the central atom, I told you a few minutes back, whatever is the geometry which is predicted through hybridization, that is the actual shape. And geometry predicted through hybridization is equal to the actual shape. And what is the geometry predicted through hybridization right now? It is trigonal planar. It is trigonal planar. So how do you represent it at the end? This is your A, this is B, this is B, and this is B. So all these 4 atoms, they are present in the same plane. All these 4 atoms are present in the same plane, and this angle over here will be 120 degree. So sp2 hybridization angle will be 120. Perfect. Now similarly, look at this particular case. If the central atom forms 2 sigma bonds, 1 lone pair, what is the type of the molecule? The type of the molecule is going to be Ab2L1. Ab2L1. Perfect. Now, what is going to be the hybridization first of all? Since Ab2L1, 2 sigma, 1 lone pair, steric number is 2. Steric number is 2. Hybridization is sp2. So hybridization is sp2 right now. But I want to know the actual shape. I want to know the actual shape of the molecule. So in order to make the actual shape, let's draw the geometry first of all. The geometry is like this. This is the perfect geometry, AB3. But do I have to make AB3 or AB2L1? I have to make AB2L1. I have to make AB2L1. So I'll remove one of the bond pair, and instead of that, I'll put a lone pair. I'll put a lone pair. Now this is AB2L1. Now if you want to have a look on its actual shape, if you hide this lone pair, how it looks like? It looks like bent shaped. So this shape is called as bent shaped. This shape is called as bent shape. Okay? This shape is called as bent shape. So this was the first case wherein the steric number is 3. Let's talk about the second case. Second case is where the steric number can be 4. Steric number 4 means hybridization sp3. Geometry predicted through hybridization is tetrahedral. Tetrahedral. And in case of tetrahedral geometry, the bond angle is 109 degree 28 minutes. Let me tell you that too. Okay? In case of tetrahedral geometry, the bond angle is 109 degree. And in case of trigonal planar geometry, the bond angle is, a few minutes back I told you, the bond angle is 120 degree. In case of trigonal planar geometry. Now guys, what are the possible cases to have steric number 4? What are the possible cases to have steric number 4? The first case is when there are 4 sigma bonds and 0 lone pair. Second possibility, when there are 3 sigma bonds, 1 lone pair. When there are 2 sigma bonds and 2 lone pairs. These are the 3 possibilities. The type of this molecule is going to be Ab4L0. The type of this molecule is going to be Ab3L1. The type of this molecule is going to be Ab2L2. Okay. Now, hybridization in each of these cases is going to be sp3 only. Now, if I talk about the actual shape, in each molecule, how it looks like, this is Ab4L0. Since central atom does not have lone pair, so geometry predicted through hybridization is going to be its shape. So it's Ab4L0 like this. A, this is B, this is one more B, this is one more B. You call this shape as the tetrahedral shape. This is tetrahedral. And in case of tetrahedral geometry, the bond angle is how much? 109 degree 28 minutes. Right? Now, Ab3L1. Do one thing. From the geometry, remove one of the bond pair and place a lone pair. So this is A, this for example B, this is one more B, this is one more B, and you can place a lone pair here. Perfect. This shape is called as pyramidal shape. You call this as the pyramidal shape. Now, Ab2L2. From Ab4L0, just remove 2 bond pairs and put 2 lone pairs. So this A, this is B, this is B. Let's say this is a lone pair, and here also there's a lone pair. So this shape is also called as bent shape, or you call it as V-shaped. Okay? Got it? So this was steric number 4 category. Now, for example, if I talk about steric number 5 category. Steric number 5 means hybridization is sp3d. Geometry predicted through hybridization is trigonal bipyramidal. Trigonal bipyramidal. Trigonal bipyramidal. How many possible cases are there to have the state number 5? Tell me that first. So the first possibility is going to be, first possibility will be if the central atom is forming 5 sigma bonds and there is 0 lone pair. Second possibility, 4 sigma bonds, 1 lone pair. Third possibility, 3 sigma bonds, 2 lone pairs. Next possibility, 2 sigma bonds, 3 lone pairs. These are all the possibilities which I've shown. What is the type of this molecule? You call this as AB5L0 type. This is called as AB4L1 type. This is called as AB3L2 type. This is called as AB2L3 type. Now, what about the shape of each molecule? If I talk about the shape of each, since the central atom does not have a lone pair, so geometry which is predicted through hybridization is the shape. So it's trigonal bipyramidal shape. How this trigonal bipyramidal shape looks like? For example, this is A, this is B, this is one more B, and this one more B. All these 3 bonds, they are present in the same plane. All these 3 bonds, they are present in the same plane. Now, perpendicular upwards, there is one B, perpendicular downwards, there is one more B. And if you connect them, it looks like a pyramid from the top and the pyramid from the bottom. You call this shape as the trigonal bipyramidal shape. You call it as a trigonal bipyramidal shape, right? Now, let me tell you, this bond, and this bond, these 3 bonds, they are called as equatorial bonds. Okay. Now, this yellow colored, these 2 yellow colored bonds, this one and this one, they are called as axial bonds. That's called as axial bonds. And remember, bond length in axial will be greater than the bond length in equatorial. Bond length in axial will be greater than that of bond length in equatorial, right? Because these atoms, they will be showing some repulsions towards this B, due to which this bond will stretch. And if this bond stretches, this bond length will be more. Okay. Now, at the same time, how many types of bond angles do you see here? How many types of bond angles do you see here? My dear students, angle between this bond and this bond. So, equatorial. Angle between equatorial and equatorial. Equatorial is how much? It is 120 degree, right? Now, angle between axial and equatorial. Axial and equatorial will be 90 degree. Angle between axial and axial will be 180 degree. Got it? Now, if I ask you, how many 90 degrees will be there? How many 90 degree angles will be there? How many 90 degree angles will be there? See, this is 190, one more 90, one more 90. So basically, these 3 bonds, this bond, this bond, this bond, they are present on the same plane. Perpendicular upwards is 1, perpendicular downwards is 1. So 390 degrees from the top and 390 degrees from the bottom, right? So there are 690 degrees basically. The 690 degrees, right? How many 120 degrees do you see? First, second, and third. So there are 3 120 degrees. How many 180 degrees do you see? There is only one 180 degree. Okay. Now look at this one, AB4L1. AB4L1 is called as seesaw shape. It is called as seesaw shape. How do we make it exactly? See, just remove this bond pair and instead of this place a lone pair. Rest keep everything same. Rest keep everything same. This shape is what you call a seesaw shape. If you hide the lone pair, it looks like a seesaw type, right? AB3L2, 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 AB3L2. Now do one thing, remove these 2 bond pairs and place 2 lone pairs here. How it looks like? This A, this is B, this is B, this is one more B, and there is a lone pair here, there is a lone pair here. If you hide these lone pair, it looks like a T shape. If you hide these lone pairs, it looks like a T shape. So this shape is called as T shape. Okay. AB2L3. AB2L3. So you can remove all these 3 equatorial bonds and place 3 lone pairs instead. So it will be like this. A, B at the axial, B at the axial, At all the three equatorial positions, you'll have three lone pairs, right? If you hide these lone pairs, it's going to be looking like a linear shaped. This is a linear shaped molecule, right? AB2L3 type. AB2L3 type. Perfect. So these were all the cases wherein the molecule can have steric number 5. Now, what about the molecule wherein the steric number can be 6? Steric number 6 means hybridization sp3d2. Geometry predicted through hybridization is going to be octahedral. Octahedral. Octahedral, okay? Now, the possible cases wherein steric number is going to be 6. So first case is 6 sigma bonds, 0 lone pairs. Second case is 5 sigma bonds, 1 lone pair. Third case is 4 sigma bonds and 2 lone pairs. These are the only 3 cases which we have wherein the molecule can have steric number 6. Okay? Now, try to understand. What is the type of this molecule? It is AB6L0. What is the type of this molecule? It is AB5L1. What is the type of this molecule? It is AB4L2. Over here, the central atom does not have a lone pair. So whatever is the geometry which is predicted through hybridization, that is going to be the actual shape of the molecule, which is going to be octahedral only. And how this octahedral geometry looks like? This is A, right? This is B. This is one more B, one more B, and one more B. All these 4 bonds are present on the same plane. So they are present on the same plane. And perpendicular upwards, there will be one B. Perpendicular downwards, there will be one more B. Now, if you join, what kind of shape it will have? It will look like an octahedron. It will look like an octahedron, people, right? It will look like an octahedron. Okay? Now, first of all, if I ask you, first of all, in octahedron geometry, all the bond lengths are same. In octahedron geometry, all the bond lengths are same. Remember this, number 1. Number 2, what is the angle between axial and axial? Sorry, equatorial and equatorial. This angle and this angle. Equatorial, equatorial, this particular one I'm showing. This particular one. This particular one. Right? It's going to be 90 degree. 90 degree. Okay? What is the angle between axial and equatorial? Axial and equatorial. It's going to be again 90 degree. What is the angle between axial and axial? It's going to be 180 degree. Now, if I ask you how many 90 degrees are there? This is 190, second 90, third 90, fourth 90. So 4 90 degrees on the same plane. On the top, 4 more 90 degrees, which this axial is forming with this one, this axial forming with this one as well, this one. Siri is working. Okay. So 4 on the same plane, 4 from the top, 4 from the bottom. So in total, there are 12 90 degrees here. Okay. There are 12 90 degrees. 4 on the same plane. See, on the plane, there are 4 bonds. On the plane, there are 4 bonds, right? Now, there is one perpendicular upwards. So, it's forming 190, second 90, third 90, fourth 90, right? Similarly, 4 from bottom, right? So, 12 90 degrees will be there. Now, AB5L1, 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 what do we have to do? If we have to make its actual shape, do one thing. Remove one of the bond pair from the axial position, place a lone pair. Rest, keep everything same. This is A, this is B, this is B. This is one more B. This is one more B. So all these are present on the same plane. Now from one axial position, I'm keeping a lone pair and another axial position as such. So it is square pyramidal. The shape is called as square pyramidal. This is square pyramid. AB4L2. This will be called as square planar. This will be called as the square planar shape. So this is A. This will be 1B. One more B, one more B, one more B. So all these are present on the equatorial plane. Perpendicular upwards is a lone pair. At the axial position, here also a lone pair. So if you hide these lone pairs, it will look like a square planar to you. It will look like square planar to you. I believe it's also clear to every one of you. Perfect. All clear, guys? Now, there is one last case here. That is steric number 7. That is steric number 7. Steric number 7 means sp3d3. Geometry predicted through hybridization is going to be pentagonal bipyramidal. Pentagonal bipyramidal. And there are two possible cases over here. One is your 7 sigma bonds, 0 lone pairs. Second is 6 sigma bonds, 1 lone pair. Type of this molecule is going to be AB7L0. Type of this molecule is going to be AB6L0. Now here, since central atom does not have lone pair, so shape and geometry are same, which is pentagonal bipyramidal. And how this pentagonal bipyramidal looks like, this for example A, this is B, one more B, one more B. Okay, and similarly, here you have got one more B, and all these bonds, they are present on the same plane, equatorial plane. Now, perpendicular upwards, there will be one B, and perpendicular downwards, there will be one more B. Okay, if you look at this particular bond angle here, it's going to be 72 degree between equatorial and equatorial. Between axial and equatorial, it's going to be 90. Between axial and equatorial, it's going to be 90. Okay, now, this is called as pentagonal bipyramidal. So pentagon on the plane, upwards one pyramid, downwards one more pyramid. Okay, this is called as pentagonal bipyramidal geometry. Now AB6L1, its shape is called as distorted octahedron. It's called as distorted octahedron. And how do you make it? Just remove this bond pair and place a lone pair here. Remove this bond pair and place a lone pair. Distorted octahedron. Now guys, from all this, can you tell me the shapes of the molecules, shapes of these molecules? Just a second. See, NH3. Tell me what is the type of the molecule. Type of the molecule is going to be 3 sigma 1 lone pair. So AB3L1. AB3L1 means it's going to be pyramidal shaped. Okay. 4 sigma bond 0 lone pair. AB4L0. So it's going to be tetrahedral. Correct? 2 sigma bonds 3 lone pairs. It is AB2L3. AB2L3 means linear. 4 sigma bonds 2 lone pairs. So the type is AB4L2. AB4L2 is square planar. Square planar, right? I3 negative. 2 sigma bonds, 3 lone pairs. AB2L3, linear. Few minutes back only we discussed. I3 positive. 2 sigma bonds, 2 lone pairs. The type is AB2L2, bent. Okay. Water. 2 sigma bonds, 2 lone pairs. The type is AB2L2, bent. V-shaped. 5 sigma bonds, 1 lone pair. AB5L1, square pyramidal. So I believe you can talk about the shape of any molecule from now onwards, right? If you just know the type of the molecule, you are done. You are sorted. Am I clear with this? Am I clear with this, people? Is this particular point clear? Is this particular point clear? Am I clear till here? Should we take a break for 10-15 minutes? I think I should take. Then only I'll be teaching you all of this in a good way, okay? Small tea break, okay? So, and the session will go for like 1.5 hours more, because this is the last chapter. In our class 11th Inorganic Chemistry, there are 2 chapters only, periodic classification and bonding. But from both the chapters, you will get like 7-8 questions for sure. Okay. So break till 11:45. Okay. But be back on time, because we have to discuss MOT, we have to discuss hydrogen bonding, and we have to discuss this. We have to discuss bond angle. I'll not take more than like 1 hour after this. 1 hour is sufficient. But be back on time, huh? Please. Be back on time. I'll also have tea and come back. Sir, AB5L1. AB5L1 means a square pyramidal. Square pyramidal. AB5L1 means square pyramidal. I don't know what have I written there. You can check it out. So I'll be back in like exact at 11:45. I'll also be back. Are you all back? Yes. Are you all back, people? All right, perfect. So, my dear students, now, let's move on to one more important topic from which questions can be frequently asked. What is that? That is questions which are related to bond angle, right? Questions which are related to bond angle. How do we solve the questions which are related to bond angle? Basically, in the question, you will be given with 2-3 molecules, right? And you will have to arrange them on the basis of their bond angle. In the question, you'll be given with 2-3 molecules and you will have to arrange them on the basis of their bond angles, right? And how do we do that? For that, this is the diagram which you have to follow. And what this diagram suggests, let's have a look. First of all, I'm going to read out this diagram loud, right? Then I'll show you how this particular diagram is applied in the questions. Try to understand properly. So first of all, whenever you will be given with 2-3 molecules, okay? Whenever you'll be given with 2-3 molecules, and you will have to arrange them on the basis of their bond angle. The first thing which you will do, you will use VSEPR theory. You will check if there is any molecule of the type AB2L0 or AB2L3. Your first point is, whenever you'll be given with 2-3 molecules, right? You'll be using VSEPR theory. You will check if there is any molecule of the type AB2L0 or AB2L3. If there is any molecule of the type AB2L0 or AB2L3, its bond angle will be maximum, that will be 180. You know, AB2L0 is linear, AB2L3 is also linear. So bond angle will be maximum, that will be 180. Number one. Number two, if you are not able to decide as per VSEPR, that means if there was no molecule of the type AB2L0 or AB2L3, then the next step is go to hybridization. Check the hybridization of the central atom. If the hybridization of the central atom comes out to be different, for example, hybridization in one of the molecule comes out to be sp, in one more sp2, in one more sp3. You know, in sp hybridization, the bond angle is 180. In sp2, the bond angle is 120. And in sp3, the bond angle is 109 degree 28 minutes. So if you are not able to decide as per VSEPR, then you will go to hybridization, right? If hybridization comes out to be different, then that molecule which has got sp hybridization will have maximum bond angle 180, followed by sp2, 120, followed by sp3, 109 degree 28 minutes. Now, if you are not able to decide as per hybridization, what does that mean? That means if in all the molecules hybridization is same, then two cases will arise. Number one, if lone pair is absent on the central atom, and if lone pair is present on the central atom. My dear students, if lone pair is absent on the central atom, then you will give your answer as per hybridization. If lone pair is absent on the central atom, that means you'll give your answer as per hybridization. For example, you have got BCl3, you have got BBr3, for example, you have got BI3. In each case, hybridization is same, sp2. Right? In each case, there is no lone pair on the central atom. So you'll give your answer as per hybridization. sp2, the bond angle will be same. That means 120 degree. But if there is lone pair present on the central atom, then remember, bond angle will be inversely proportional to number of lone pairs. If lone pair is present on the central atom, then remember, bond angle is inversely proportional to number of lone pairs. Right? And my dear students, remember, if hybridization as well as the number of lone pairs are same, in all the molecules, if hybridization is same as well as the number of lone pairs are same, then remember, bond angle is directly proportional to the size of surrounding atom, and bond angle is inversely proportional to the size of central atom. Bond angle directly proportional to the size of surrounding atom, and bond angle is inversely proportional to the size of central atom. Now let me use this particular table. Let me use this particular table in the question so that you can understand and analyze the questions which can be asked from it. First of all, let me recap. The first thing, you'll be checking VSEPR. If there is any molecule of the type AB2L0 or AB2L3, bond angle maximum 180. If you are not able to decide as per VSEPR, then go for hybridization. If hybridization is different, then SP hybridization maximum bond angle followed by SP2 followed by SP3. Now, if hybridization is same, then check if lone pair is present on central atom or not. If lone pair is absent on the central atom, your answer will be as per hybridization. If lone pair is present on the central atom, then remember bond angle is inversely proportional to number of lone pairs. If hybridization as well as number of lone pairs are same, then remember bond angle is directly proportional to size of surrounding atom, or you can say bond angle is inversely proportional to size of central atom. Now let me utilize this in the questions. First of all, look at all these cases. The first thing which I'll be doing, I'll be checking the type of the molecule as per VSEPR. Carbon dioxide, AB2L0. I've already shown you how to check it. AB2L0. This is also AB2L0. This is your AB2L3. And your AB2L0, AB2L3. Bond angle is maximum 180 degree. So they will have equal bond angles and it's going to be 180 degree. Perfect. Right? Now, my dear students, the type of this molecule is AB2L0. The type of this molecule is AB3L0. The type of this molecule is AB4L0, right? Since AB2L0 is there, that means it's linear, its bond angle will be maximum. So carbon dioxide will have maximum bond angle. Carbon dioxide will have maximum bond angle. Now, since I'm unable to decide as per your VSEPR, now I'll check the hybridization. This is SP hybridized, this is SP2 hybridized, this is SP3 hybridized. So hybridization is different. Now directly give your answer as per hybridization. In SP hybridization, the bond angle is maximum 180, SP2 120, SP3 109 degree 28 minutes. So this is the order of the bond angle here. Okay. Now look at this one. See, if you look at the hybridization, this is SP3, this is also SP3, this is also SP3. So hybridization is same. Hybridization is same. Now, there is no lone pair on the central atom. There is a lone pair on the central atom. There are two lone pairs on the central atom. When hybridization is same, then if lone pair is present on the central atom, remember bond angle is inversely proportional to number of lone pairs. So more the lone pairs, lesser the bond angle. More the lone pairs present, lesser the bond angle. So this is the order of the bond angle here. I hope you're understanding how I'm utilizing this. Now, this is sp2 hybridized, this also sp2 hybridized, this also sp2 hybridized. So hybridization is same and there is no lone pair on the central atom. So give your answer as per hybridization. Both will have equal bond angles and it's going to be 120 degree. Right? Perfect. Similarly, my dear students, for example, these are the molecules. First of all, if you look at the hybridization, this sp3, no lone pair on the central atom, no lone pair. When you check them out, okay? When you check them out. So hybridization is same, no lone pair on the central atom. Give your answer as per hybridization. So sp3 means all will have bond angle of 109 degree, 28 minutes. NCl3, PCl3, AsCl3, SbCl3. So first of all, hybridization, sp3. Hybridization, again sp3. When you check, hybridization, sp3. Hybridization is same. Okay? Lone pair present on nitrogen, 1. This is 1. This is 1. This is also 1. So hybridization as well as number of lone pairs are same. Yeah? Hybridization as well as number of lone pairs on the central atom is same. When hybridization as well as the number of lone pairs on the central atom is same, then check whether the central atom is same. No, central atom is different. So my dear students, when hybridization and number of lone pairs are same, then remember bond angle is inversely proportional to the central atom and bond angle is directly proportional to the surrounding atom. Bond angle is directly proportional to the surrounding atom. Bond angle is directly proportional to the surrounding atom. Bond angle is inversely proportional to the size of central atom, right? Size of central atom is minimum here, right? So its bond angle will be maximum. So this is the order of bond angle. Yeah, I believe this is clear. Since Hybridization as well as the number of lone pairs on the central atom are same. You know, when hybridization as well as the size as well as the number of lone pairs on the central atom is same, then we know bond angle is inversely proportional to size of central atom, right? So lesser the size of central atom, more is the bond angle. As simple as that. The next one. First of all, this is sp3 hybridized. Even this is sp3 hybridized. Even this is sp3 hybridized. Okay. Lone pairs on the central atom same. Lone pairs on the central atom same. Now, surrounding atoms are different here. And you know, bond angle is directly proportional to size of surrounding atom. So Br has got maximum size. So it will be having maximum bond angle. Cl2O, Br2O. Cl2O, Br2O. Right? So if I talk about the hybridization sp3, this one will also have sp3 hybridization. Perfect. sp3 hybridization. Number of lone pairs on oxygen 2. Number of lone pairs on oxygen 2. So hybridization same as well as number of lone pairs are same. But surrounding atoms are different. Surrounding atoms are different. And we know bond angle is directly proportional to size of surrounding atom. Bond angle is directly proportional to size of surrounding atom. Bromine has got more size than that of chlorine. So this is the order of bond. I believe this is clear to everyone. Yes, I know Yavarsu took 16 hours straight. That was amazing. That was great. So guys, is it clear? Now I believe you can easily solve the questions which are based on bond angle. Just you need to remember the table which I gave you. That's all. That's more than sufficient. Okay. Now guys, before talking about the last topic, that is molecular orbital theory, you should, first of all, I'll tell you what hydrogen bond exactly is. Before going into our last topic, that is MOT, molecular orbital theory, let's get to know what hydrogen bonding exactly is all about. Okay, let's try to understand. Let's try to understand the hydrogen bonding. So first of all, if you look at the statement which I mentioned over here, nitrogen, oxygen and fluorine, they are highly electronegative elements. Perfect. When they are attached to hydrogen atom to form a covalent bond, when they are attached with hydrogen to form a covalent bond, the electrons of a covalent bond are shifted towards more electronegative element. The partial positively charged hydrogen atom forms bond with another more electronegative element. Now, what does that mean? What does that mean? Try to understand what it means. For example, I've got a molecule HF. This is a molecule HF, right? Let me take one more molecule HF. So first of all, there's a covalent bond between hydrogen and fluorine. Again, there is covalent bond between hydrogen and fluorine. Now, fluorine is more electronegative than hydrogen. So this electron pair will be shifted towards fluorine, due to which fluorine gets delta negative, hydrogen gets delta positive. Again, this fluorine also gets delta negative, this gets delta positive. Now, these are two molecules, right? Look at this fluorine, it gets delta negative. Look at this hydrogen, it gets delta positive. Now, between this fluorine and this hydrogen, there will be force of attraction. And this force of attraction I'll be representing with 3 dashes. And these 3 dashes represent your hydrogen bond. So this force of attraction is what I call as hydrogen bond. Perfect. For example, you have got water. You have got water. Let's say this H2O. This is H2O, right? For example, this is one more H2O molecule. Let's say this is one more H2O molecule, right? Just to make you understand. If I talk about this particular bond, oxygen is more electronegative. So delta negative, delta positive. Again, delta negative, delta positive, delta negative, delta positive, delta negative, delta positive. So I would say, first of all, there can be force of attraction between these two. There can be force of attraction between these two, right? So this particular bond, you call them as the hydrogen bonds. Yeah. Now this hydrogen bond is actually of 2 types. One is called as intermolecular hydrogen bond and one is called as intramolecular hydrogen bond. As far as the name is concerned, inter means between the molecules. Intra means within the molecule. Intra means within the molecule. One is your intermolecular hydrogen bond, one is intramolecular hydrogen bond. So what is inter and what is intra? Look at this HF molecule. Again, if I make HF, if I make HF molecule, so this first of all HF, this is one more HF. Now you know this will have delta positive, this will have delta negative, delta positive, delta negative. Now between these two molecules there is hydrogen bond. whenever hydrogen bond is present between two molecules, between means inter. Same in case of water, which I showed you right now, Between two molecules, there is hydrogen bond, right? So this again, intermolecular hydrogen bond. So this also inter. Carboxylic acids. If you talk about this particular bond between oxygen and hydrogen, oxygen carries delta negative, hydrogen delta positive. Oxygen delta negative, this carbon delta positive. Oxygen delta negative, hydrogen delta positive. Oxygen delta negative, this carbon delta positive, right? So between negative and positive, there will be hydrogen bond. Between negative and positive, there will be hydrogen bond. Perfect. So this is hydrogen bond between two molecules. So this is intermolecular hydrogen bond. Now look at this particular case. Among oxygen and hydrogen, oxygen will have delta negative, hydrogen will have delta positive because of electronegativity difference, right? Similarly, nitrogen, oxygen will have delta negative, right? Nitrogen will have delta positive. Now between this oxygen and this hydrogen, there can be force of attraction between oxygen of this, hydrogen of this. You call this bond as the hydrogen bond, and this hydrogen bond is within the molecule. If it is within the molecule, that means intramolecular hydrogen bond. Similarly, between this hydrogen and this oxygen, there can be again hydrogen bond, and this is called as intramolecular hydrogen bond within the molecule. And due to intramolecular hydrogen bond, you get a closed ring, right? You got a closed ring, and the process called as chelation if you have studied in your coordination chemistry, right? Perfect. Similarly over here, OH and chlorine. This will have delta positive, this will have delta negative. So there is again hydrogen bonding within the molecule, due to which a ring got formed, chelation happened here. So basically we have got two types of hydrogen bondings. One is your inter, one is intra. Inter is within the two molecules. Inter means between two molecules, intra means within the molecule. Okay. Now my dear students, few things. What kind of effect this hydrogen bonding produces? Okay. What kind of changes this hydrogen bonding produces? Let's have a look. First of all, solubility is directly proportional to intermolecular hydrogen bonding. Solubility is directly proportional to intermolecular hydrogen bonding. What does that mean? If you talk about alcohols or glucose, your alcohols are soluble in water. Why? Because alcohols, they form hydrogen bonds with water. Alcohols form hydrogen bonds with water. So it's inter, between two molecules, between alcohol and water. There is intermolecular. Hydrogen bonding. And more the intermolecular hydrogen bonding, more is going to be the solubility. So basically, more the hydrogen bonding between water and alcohol, more is going to be the solubility of alcohol in water. Yeah? Similarly, your glucose, again it's soluble in water. Why? Because glucose forms hydrogen bonds with water. So again, hydrogen bond between glucose and water, between two molecules. So intermolecular. And more the hydrogen bonding means, more is going to be the solubility of glucose in water. So glucose and alcohol, they are soluble in water because of intermolecular hydrogen bonding. Number one. This solubility is inversely proportional to intramolecular hydrogen bonding. It is inversely proportional to intramolecular hydrogen bonding. What does that mean? Just a second. The solubility is inversely proportional to intramolecular hydrogen bonding. If there is already intramolecular hydrogen bonding in the molecule, intra means within the molecule. If there is already hydrogen bonding present within the molecule, that means if that molecule, which already has hydrogen bonding in it, if that is introduced in water, will it form new hydrogen bonds with water? No. Why? Because all the sites which were for hydrogen bonding with water, they are already exhausted for the intramolecular hydrogen bonding. Okay? Perfect. So remember directly, your solubility is inversely proportional to intramolecular hydrogen bonding, right? And that is the reason why your para-hydroxybenzaldehyde is more soluble than that of orthohydroxybenzaldehyde. Because in orthohydroxybenzaldehyde, there will be intramolecular hydrogen bonding. Within the molecule, there will be hydrogen bonding. So all the sites will be already exhausted. All the sites of hydrogen bonding are already exhausted. Because in the molecule, there is already intramolecular hydrogen bonding. If all the sites are already exhausted, then there'll be no formation of other hydrogen bonds right? Which we call as intermolecular hydrogen bonds. Yes? Perfect. Well, if you talk about the para-hydroxybenzaldehyde, in para-hydroxybenzaldehyde, there is no intramolecular hydrogen bonding. So all the sites are available for intermolecular hydrogen bonding. So remember it like that. Similarly, if you talk about viscosity, viscosity is directly proportional to intermolecular hydrogen bonding. So basically, more the intermolecular hydrogen bonding, right? More is going to be the viscosity. First of all, if I ask you, among water and honey, which one has more viscosity? Honey has more viscosity, right? Honey is more viscous. You know that. Now, if I compare water CH3OH and CHOCH3, where will be the hydrogen bonding maximum? Hydrogen bonding will be maximum in water. Yes, extent of hydrogen bonding in water will be more because of the electronegativity difference between oxygen and hydrogen. Perfect. More electronegativity here. Perfect. Right? So I would say simply extent of hydrogen bonding in water is more, due to which water is more viscous than all these three. Similarly, if you look at all these three cases, there is there can be more intermolecular hydrogen bonding, comparatively lesser intermolecular hydrogen bonding, and more the intermolecular hydrogen bonding, more is the viscosity, right? Similarly, when it comes to your melting points, boiling points order, remember again, melting point, boiling point is directly proportional to what? Intermolecular hydrogen bonding. Okay, so this is the order. If you have HF, HI, HBr, HCl, for example, if you have HF, you have got HCl, you have got HBr, you have got HI. Generally, on moving from top to bottom, van der Waals force of attraction increases, due to which boiling point should increase. So HI should have maximum boiling point, followed by HBr, followed by HCl, followed by HI. Right? This should be the boiling point order. But, this should be HF. But in case of HF, there is intermolecular hydrogen bonding. Due to intermolecular hydrogen bonding, its boiling point increases. So HF comes to the front. So this is the actual order of the boiling points. HF, HI, HBr, HCl. Same goes with this particular case. For example, you have got H2O, you have got H2S, you have got H2SE, you have got H2TE. Right? Again, down the group, van der Waals force of attraction increases, boiling point should increase. So expected order of boiling point is H2TE should have maximum boiling point, followed by H2SE, followed by H2S, followed by H2O. This should be the boiling point order. But in case of water, there is intermolecular hydrogen bonding. Due to intermolecular hydrogen bonding, its boiling point becomes maximum. So this is the new boiling point order, right? In case of the hydrides of group 16. Okay? I believe this is also clear to everyone. Tell me the answer of this question. Does not have inter-hydrogen bonding. First of all, between two water molecules, there will be inter. Between two water molecules, there will be hydrogen bond. Between two water molecules, so it's intermolecular. Orthonitrophenol. If you talk about orthonitrophenol, it has got hydrogen bond within the molecule, right? So this has got intra. HF, between two HF molecules, there will be hydrogen bond, so this is inter. CH3OH. So answer of this particular question is this one. Does not have inter-hydrogen bonding. This does not have inter, it has intramolecular hydrogen bonding. What is the boiling point order here? Boiling point is directly proportional to intermolecular hydrogen bonding, right? So generally, I give you the order a few minutes back only. HF will have maximum, followed by HI, followed by HBr, followed by HCl. This is the boiling point order, right? H2O, HF, NH3. Now, first of all, water simultaneously can form how many hydrogen bonds? 4 hydrogen bonds. Water simultaneously can form 4 hydrogen bonds, right? So, extent of hydrogen bonding is more in water. And more the hydrogen bonding, more is going to be the boiling point. More the extent of hydrogen bonding, more is going to be the boiling point. So, this is the order here. Perfect, guys. So these sort of questions can be asked from hydrogen bonding as well. I believe this is clear. Now, if you talk about your molecular orbital theory now, if you want to talk about your molecular orbital theory, the questions from molecular orbital theory will be the questions based on bond order, the questions based on bond length, the questions based on bond strength, the questions based on stability, right? Questions based on stability. All these can be asked when it comes to your molecular orbital theory. So let's have a look what this molecular orbital theory says and how we are going to apply it in the form of questions. See guys, understand properly what we are going to do. First of all, this molecular orbital theory is the extension of VBT. It is the extension of VBT. VBT says that the atomic orbitals of bonding atoms, they must overlap. They must overlap. That's your VBT. And your molecular orbital theory says that the atomic orbitals of the bonding atoms, they must combine. They must combine to form new orbitals which are called as molecular orbitals. In short, I would say, as per molecular orbital theory is concerned, atomic orbitals of bonding atoms, they must combine and they will lead to the formation of new orbitals, and those new orbitals are called as molecular orbitals. Right? Those new orbitals are called as molecular orbitals. And remember, number of atomic orbitals of bonding atoms, number of atomic orbitals of a bonding atoms combining is equal to the number of molecular orbitals formed. Number of atomic orbitals combining is equal to the number of molecular orbitals formed. For example, this is 1s atomic orbital of one atom. This is 1s atomic orbital of one more bonding atom. Now they are going to combine. Since two atomic orbitals are combining, they will lead to the formation of two molecular orbitals. They will lead to the formation of two molecular orbitals. One is called as bonding molecular orbital. One is called as anti-bonding molecular orbital. Let me tell you, energy of bonding molecular orbital is less. Energy of anti-bonding molecular orbital is more. And if energy of bonding molecular orbital is less, stability of bonding molecular orbital will be more, and stability of this will be less. Okay? So again, when it comes to molecular orbital theory, it is the extension of your valence bond theory. Right? As per molecular orbital theory is concerned, the atomic orbitals of bonding atoms, they must combine to form molecular orbitals. And number of atomic orbitals combined is equal to the number of molecular orbitals formed. If two atomic orbitals of bonding atoms are combining, they will lead to the formation of two molecular orbitals. One is called as bonding, one is called as anti-bonding. Energy of bonding is less, stability is more. Energy of anti-bonding is more, stability is less. Okay? Now guys, try to understand. For example, this is the s orbital. This is s orbital of a bonding atom. This is one more s orbital of a bonding atom. As per MOT, these atomic orbitals, they must combine. They will lead to the formation of molecular orbitals, right? Now, SS overlap in VBT, SS overlap forms sigma. So, one is called as sigma 1s, one more molecular orbital I'll be calling as sigma star 1s. This is called as bonding molecular orbital. This is what I'll be calling as anti-bonding molecular orbital. Perfect. For example, this is your 2p atomic orbital of a bonding atom. This is one more 2p atomic orbital of one more bonding atom, right? Now, as per VBT, 2p, when they do axial overlap, they lead to the formation of sigma, right? For example, this is 2pz, this is 2pz. So two atomic orbitals are combining, they will lead to the formation of two molecular orbitals, right? Since it's head-on overlapping, so sigma gets formed. So one will be called as sigma 2pz, one will be called as sigma star 2pz, right? This is bonding, this is anti-bonding. Now similarly, if this is a p orbital of one bonding atom, this is the p orbital of one more bonding atom. Let's say this is 2py, this is 2py. So this in VBT says they are going to show parallel overlapping. Through parallel overlapping, which bond gets formed? Pi bond gets formed. So since two atomic orbitals are combining, they will lead to the formation of two molecular orbitals. One will be called as pi 2py, one will be called as pi star 2py. Perfect. So the atomic orbitals of bonding atoms, they are going to combine and they will lead to the formation of molecular orbitals, out of which some will be bonding, some will be anti-bonding. Energy of bonding will be less, energy of anti-bonding will be more. Okay. Now, my dear students, as when the atomic orbitals of bonding atoms combine, they will lead to the formation of molecular orbitals. Now, once molecular orbitals are formed, then what are we supposed to do? Once molecular orbitals are formed, then we are supposed to arrange these molecular orbitals. We are supposed to arrange these molecular orbitals as per the increasing energies. Then we are supposed to arrange these molecular orbitals as per their increasing energies. And we will start filling electrons in these molecular orbitals. And then we'll start filling electrons in these molecular orbitals. So first of all, when bonding atoms are formed, when molecular orbitals are formed, after that, you will start filling electrons in these molecular orbitals as per the increasing order of the energies. And once you are done filling electrons in these molecular orbitals as per the increasing order of energies, then there's a rule by means of which you can calculate the bond order. What is the rule? Bond order is calculated as half of number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital. This is the rule by means of which you can calculate the bond order. Now, my dear students, if the bond order comes out to be less or equal to 0, that means molecule does not exist. If the bond order comes out to be 1, that means there is a single bond between two atoms. If bond order comes out to be 2, there is a double bond. If bond order comes out to be 3, there is a triple bond between the atoms. Remember that. Okay? Perfect. Now, my dear students, one more important point. I told you already, the atomic orbitals of bonding atoms, they are going to combine. They will lead to the formation of molecular orbitals, out of which some will be bonding, some will be anti-bonding. Correct? Energy of bonding is less than that of energy of anti-bonding. Energy of bonding is less than that of energy of anti-bonding. Once we get molecular orbitals, then we are supposed to arrange those molecular orbitals as per the increasing order of their energies. So technically, I must say, once we get molecular orbitals, we will start filling electrons in those molecular orbitals as per Abba's principle, as per Hund's rule, and as per Pauli's exclusion principle. How we are going to fill them, I'll let you know that in some time. First of all, you remember all this. The point is, once molecular orbitals are generated, then we are supposed to fill electrons in those molecular orbitals as per Abba's principle, as per Hund's rule, as per Pauli's exclusion principle. And once you fill electrons in the molecular orbitals, then there is a formula to calculate bond order. That is half of number of electrons in bonding minus number of electrons in anti-bonding. Okay? Number of electrons in bonding minus number of electrons in anti-bonding. And as I told you, if the bond order comes out to be less or equal to 0, the molecule does not exist. If the bond order comes out to be 1, single bond, 2, double bond, 3, triple bond. Right? My dear students, remember one more thing. Bond order, it represents number of bonds between the atoms, as you saw. And remember, bond order is directly proportional to bond dissociation energy, right? Or you can say it is directly proportional to stability. And yes, the same bond order is inversely proportional to bond length. Because more the bond order, that means more will be the bonds between the atoms. That means more is the attraction between the atoms. And if more is the attraction between the atoms, lesser will be the bond length definitely. Yes? Lesser will be the bond length definitely. One more important point. As I told you, bond order is directly proportional to stability. More the bond order, more the stability. Now, if the bond order is same, if the bond order of two species is same, we have got two molecules. For example, we have calculated their bond orders, and bond order is coming out to be same for both the molecules. Then how can we arrange them on the basis of stability? Then, my dear students, you will be counting the number of anti-bonding electrons. More the number of anti-bonding electrons in the species, lesser is going to be the stability. Remember this particular point as well. From this point, a question will be asked. If the bond order is same, then how do we compare the stability? We'll be calculating the number of anti-bonding electrons. More the anti-bonding electrons, lesser is going to be the stability. Okay? Lesser is going to be the stability. Now, let's try to use all this in the form of questions so that you can analyze and understand it properly. First of all, if I quickly recap it, as per MOT is concerned, the atomic orbitals of bonding atoms, they are going to combine. They will lead to the formation of molecular orbitals, out of which some will be bonding molecular orbitals, some will be anti-bonding. Energy of bonding molecular orbitals is less. Energy of anti-bonding molecular orbitals is more. Stability of bonding is more. Stability of anti-bonding is less, right? Now, as the molecular orbitals are generated, then we are supposed to fill electrons in those molecular orbitals as per our Bose principle, as per Pauli's exclusion principle, as per Hund's rule. And once we are done filling electrons in these molecular orbitals, then we can use a formula to calculate bond order. That is half of number of electrons in bonding minus number of electrons in anti-bond. If the bond order comes out to be less or equal to 0, the molecule does not exist. If the bond order comes out to be 1, single bond. Bond order comes out to be 2, double bond. Bond order comes out to be 3, triple bond. If the bond order of two molecules comes out to be same, then how do you compare their stability? More the antibonding electrons, lesser the stability. That's all. Okay? Now try to understand. My dear students, these are all the molecular orbitals, and this is the increasing order of the energies, increasing order of the energies of these molecular orbitals. What Bose principle says? Bose principle says that electrons are to be filled in the orbitals on the basis of their increasing energies. So that's the reason why we have arranged these molecular orbitals as per their increasing energies. As per their increasing energies. Right? Yes? Right? This is the increasing order of the energies of these molecular orbitals. Now we are going to fill the electrons in these molecular orbitals as per the increasing energies. Okay? And this particular increasing order of energies is valid only for those species which have got electrons equal to or less than 14. So this is valid for those species which have got electrons less or equal to 14. Which have got total number of electrons less or equal to 14. Now try to understand. Try to understand, guys. For example, you have got hydrogen, H2. In one hydrogen atom, there is one electron. In two hydrogen atoms, there will be two electrons. So there are two electrons basically. Now, fill these two electrons in these molecular orbitals. Every molecular orbital can accommodate maximum of 2 electrons. Every molecular orbital can accommodate maximum of 2 electrons. So both these electrons will go here. So the configuration becomes sigma 1s2. Sigma 1s2. This is the molecular orbital configuration of H2 molecule. Now, if you want to calculate bond order, it is half of number of electrons in bonding, 2, minus number of electrons in anti-bonding. There is no electron in anti-bonding. So 2 by 2 comes out to be 1. So bond order is 1. That means between two hydrogen atoms, there is a single bond. Okay. If you look at this molecular orbital configuration, every molecular orbital can accommodate a maximum of 2 electrons. And both the electrons are here. So do you see any unpaired electron? No. If there is no unpaired electron, that means we say the molecule is diamagnetic. The molecule is diamagnetic. There is no unpaired electron. If there was unpaired electron, the molecule is paramagnetic. Okay. For example, He2. One helium atom has got 2 electrons. So 2 helium atoms, 4 electrons. Now arrange these 4 electrons in these molecular orbitals. So 1s2. This is 2 more here. So its molecular orbital configurations will be sigma 1s2 and sigma star 1s2. Perfect. So if you want to calculate its bond order, it is half of number of electrons in bonding, that's 2, minus number of electrons in anti-bonding, that's 2. So the bond order comes out to be 0. That means the molecule does not exist. He2 does not exist. Okay. If I talk about Li2, there are 6 electrons in total. So 2, 4, 5 and 6. So it's going to be sigma 1s2, sigma star 1s2, sigma 2s2. Now, bond order will be equal to half of number of electrons in bonding. 2 plus 2 is 4. Minus number of electrons in anti-bonding. That's 2. 4 minus 2 is 2. 2 by 2 is 1. So bond order is 1. Do you see any unpaired electron? Since every molecular orbital can accommodate a maximum of 2 electrons. So all have accommodated those 2 electrons. Right? So there is no unpaired electron. So this again diamagnetic. Talk about Be2 molecule. In Be2 there are in total 8 electrons. So 2, 4, 6, 7 and 8. So now you can calculate its bond order. Bond order is half of number of electrons in bonding. 2, 4 minus number of electrons in anti-bonding. 2, 4. So 4 minus 4 is 0. Bond order is 0. Molecule does not exist. Okay. I hope you know these starred ones, these stars. Star ones are anti-bonding and without stars are bonding ones. Yes. I hope this is clear. Similarly, for example, you have got these molecules. Let's say you have got B2 molecule. In B2, how many electrons will be there? 10 electrons. So this is 2 here. 1, 2, 3, 4, 5, 6, 7, 8. Now, these are degenerate. Their energy is same. And pairing won't be done. Pairing won't be done until each degenerate orbital gets 1 electron, as per Hund's rule is concerned. So 1 electron here, 1 electron here. Pairing won't be done until each degenerate orbital gets 1 electron. So that's why I've given 1 here, right? So if I want to calculate bond order, it is half of number of electrons in bonding, 2, 4, 5, 6, minus number of electrons in anti-bonding, 2, 4. So 6 minus 4 is 2, 2 by 2 is 1. So bond order is 1. That means there is a single bond between 2 boron atoms. Now at the same time, do you see unpaired electrons? Yes. This is unpaired, this is unpaired, right? Unpaired electrons means it's going to be magnetic. It's going to be paramagnetic. Okay. Now C2 molecule. If I talk about C2 molecule, there are in total 12 electrons, right? So 2, 4, 6, 8, 9, 10. Now pairing will be done 11 and 12. So if I want to calculate bond order, it's going to be half of number of electrons in bonding, 2, 4, 6, 8, minus number of electrons in anti-bonding, 2, 4. 8 minus 4 is 4, 4 by 2 is 2. So bond order is 2. That means there's a double bond between 2 carbon atoms. Remember, in case of C2 molecules, both these bonds are pi bonds. Remember, in case of C2 molecule, both these bonds are basically your pi bonds, right? Do you see any unpaired electron here? There is no unpaired electron. So this particular species is again going to be diamagnetic only, right? Talk about your N2 molecule. Talk about your N2 molecule, 14 electron species. When you check, its bond order it will come out to be 3. When you write its molecular orbital configuration, or you can check it out, 14 electrons we have to fill. So 2, 4, 6, 8, 10, 12. This is 11 and this is 13 and 14, right? So its bond order, when you use the equation, it will come out to be 3. N2 positive, total 13 electrons. 13 electrons. When you calculate its bond order, it's going to be 2.5, right? This N2 negative means 15 electrons. 7 2s are 14, 14 and 15. Its bond order will be also 2.5. Now you must be thinking, if there are 15 electrons, why we are using this particular order for this particular species? As I have told you, this particular order of filling the electrons is valid only up to 14 electrons. But this has 15 electrons. Why we are using the same order for N2 negative? My dear students, remember, we are using the same energy order to N2 negative because its parent molecule N2. Because its parent molecule N2 comes into this particular category. That's why N2 negative also came into this particular category. That's why I used this electron filling order for N2 negative as well. Okay? Yes? I believe this is clear. Perfect. Am I clear, guys? Am I clear? Similarly, if there are electrons more than 14, then this is the order of filling the electrons which you have to follow. For example, if I take one of the cases, O2. O2 contains how many electrons? 16 electrons. Now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Right? 16 electron species. If you want to calculate its bond order, it is simply going to be half of number of electrons in bonding, 2, 4, 6, 8, 10, minus number of electrons in anti-bonding, 2, 4, 5, 6. So 10 minus 6 is 4, 4 by 2 is 2. That means in O2 molecule, there is a double bond. Perfect. Do you see unpaired electrons? Yes. So the molecule is paramagnetic. Right? Similarly, when you check this O2 positive, it will be a 15 electron species. O2 negative will be 17 electron species. O2 di-negative will be 18 electron species. When you calculate their bond orders, let me tell you, this will have the bond order of 1.5 when you calculate. Okay. Sorry, not 1.5, it will have 2.5. If this is having 2, this 2.5. 17 electron species will have the bond order of 1.5. 18 electron species will have the bond order of 1. You must be thinking, how come I'm directly writing the bond order? Well, in order to calculate the bond order, there is one trick also which you can remember. See, remember that. Remember, my dear students, 14 electron species always will have bond order 3. 13 electron species, or let's talk about 15 electron species. 15 electron species will have the bond order of 2.5. 16 electron species will have the bond order of 2. 17 electron species will have the bond order of 1.5. 18 electron species will have the bond order of 1. So you have to reduce by 0.5, 0.5, 0.5, 0.5. Similarly, 13 electron species will have the bond order of 2.5. 12 electron species will have the bond order of 2. 11 electron species will have the bond order of 1.5. 10 electron species will have the bond order of 1. So again, reduce by 0.5, reduce by 0.5, reduce by 0.5. So this is how you can remember directly your bond orders. Right? You can directly remember the bond orders. Perfect. Okay, one more important thing from which questions can be asked. When it comes to your isoelectronic species are the ones which have same number of electrons, right? In case of isoelectronic species, remember, bond order is also same. In case of isoelectronic species, bond order will be also same. For example, I've got CN positive and I've got CO. These are two species which I have. Okay? Or let me keep it as CN negative. CN negative and CO. Calculate the electrons here. In nitrogen, 7 electrons. In carbon, 6. So 7 plus 6 is 13. 13 plus 1 is 14. So it's a 14 electron species. 8 plus 6 is also 14. It's also a 14 electron species. Right? And 14 electron species directly, they have the bond order of 3. So their bond order will be same. Their bond order is same, which is equal to 3. So remember, whenever you see isoelectronic species, in case of isoelectronic species, the bond orders will be the same. Okay? Bond orders will be the same. Yes? Perfect. Bhaskaran, I am not understanding what you are trying to ask. And understand. All right, people. Now, at the same time, one more important thing which I want to ask you. For example, if you have got the question asked like this, N2 positive, N2 negative. You have to arrange them on the basis of the stability. You have to arrange them on the basis of the stability. And I've told you already, bond order is directly proportional to stability. Bond order is directly proportional to stability. So first of all, this is a 14 electron species. This is a 13 electron species. This is N2 negative here, sorry. This is N2 negative. And this will be how much? 7 to 14, 115 electron species. 14 electron species will have the bond order of 3. This will have bond order of 2.5. This will have bond order of 2.5. Now, more the bond order, more the stability. So N2 is maximum stable. N2 is maximum stable because its bond order is maximum. But what about N2 positive and N2 negative? Their bond order is same. Their bond order is same. Now, my dear students, I told you a few minutes back, if the bond order is same, then how do you arrange the species on the basis of stability? You will write their molecular orbital configuration. You will see which one has got more antibonding electrons. And when you write the molecular orbital configuration of this one as well as this one, you will find out in N2 negative, there will be more antibonding electrons. And more the antibonding electrons, lesser the stability. So remember, N2 positive would be more stable than N2 negative. Because in N2 negative, there will be more antibonding electrons. More antibonding electrons than that of N2 positive, which will comparatively have less antibonding electrons. Okay. So with this, my dear students, with this, your class 11th Inorganic Chemistry is done and dusted. Okay. Your class 11th Inorganic Chemistry consists of 2 chapters. One is your periodic classification, one is your chemical bonding. Both are very, very, very important chapters, right? So 4 plus 3, almost 7 questions will be asked from these 2 chapters. And I've discussed all the things which can be asked from these 2 chapters, that too in detailed manner. Tomorrow at 8 p.m. Tomorrow at 8 p.m. Tomorrow at 8 p.m. There's a question practice session of both these chapters, right? Would want every one of you to join that session as well. Okay? I would want every one of you so that your preparation becomes complete. It gets completed with that question practice session, which is tomorrow at 8 p.m. Okay? Tomorrow at 8 p.m. on the same channel. And the session PDF of this particular The handwritten PDF of this particular session, I'll be sharing on my Telegram. If you do not know my Telegram channel, this is the name of the Telegram channel. This is Wassim, but Chemistry Official. Chemistry Official. This is the name of the Telegram channel on which I shall be sharing the PDF of this particular session and all the important things. Okay? And people, with this, I'll be taking a leave. Do let me know in the comment section of this particular video right after the session how much you liked the session, because more the comments which we see on our videos from your side, better is going to be the feeling as the teacher. Yeah. All right, people. So tomorrow I'll see you exactly at 8 p.m. and do let me know in the comment section whether you liked the session or not. Would want the comments from everyone. Everyone means everyone.